So in this video, we will be covering the basis of Leetcode, which is space and time complexity. We will also be going through all the questions below. There are around 70 questions, and this is the exact same presentation I created and the exact same questions I went through in my preparation. And why you should take my advice? First of all, I have solved hundreds of Leetcode and data structure style problems, which led me to my first job at a big fan company. So if you're completing these questions to prepare for an interview, I'm someone who's gone through the process as a candidate and is now on the other side hiring. I've also helped many friends and people in online communities to become software engineers and get into companies like Apple and Amazon. So hopefully all the information and tips I provide will be super useful from that point of view. I know you are here for Leetcode, but it's important to remember why we are doing this in the first place. So I'll run through this section very quickly. And I don't want this to be a FANG interview type channel, so I've uploaded all the information you see here on my Patreon. Step 0 is to be able to sit down and work for at least 2 hours straight uninterrupted. I cannot stress enough the importance of this and just how much working on this has helped me in my life. Just take a look at the world today. The most viewed content in the world has camera cuts every 2 to 3 seconds. On top of that, a large number of people struggle to carry out activities without interruption on their phones or something similar, whether it be programming or taking a break with a walk. And sometimes this can be very damaging to our progress. I'm not perfect, even I fall victim to this sometimes too. But when I became aware of the problem and put steps in place to help myself work with focus, I noticed a big improvement in my progress and how far ahead it puts you. For example, this Leetcode video has over 100 slides, and I'm sure 98% of people will not make it to the end completing every single question. I could talk on this topic for ages, but that's not what this video is about, so instead I'll play this clip to summarize my thoughts. Quick bit of context, this guy Chamath was a vice president at Facebook in the early years, focused on user growth, helping grow the platform to 1 billion users, so he knows a thing or two about the effects of constantly using our phones on our ability to focus.
It's hard. Think about how all this stuff plays together. How does trying to get, posting your fucking waffles online relate to me starting a business and accumulating capital? This is wiring your brain for super fast feedback. It's the same brain you're using to build a company. Don't think they're not the same. Do you know what I'm saying? No? Yes? No? Yes. Yes, right? You have one brain. So you're training your brain here, whether you think it or not, whether you know it or not, whether you acknowledge it or not. Acknowledge that these things where you're spending hours a day are rewiring your psychology and physiology in a way that now you have to use to go and figure out how to be productive in the commercial world. So if you don't change this, you are going to get the same behaviors over here. Change this. There's a reason why Steve Jobs was like anti-social media. I am telling you I'm not on these fucking apps. I'm not him by any stretch of the imagination. But I am proactively trying to rewire my brain chemistry to not be short-term focused. I'm telling you they're linked.
Okay, so let's move on to step 1, which is to learn a programming language. If you're watching this video, I hope you already know a programming language, but if not, I would suggest Python. It's the easiest language to learn and the best to work with when solving problems. It also offers a wide range of specialities. You can use Python to transition to web development, data analysis, machine learning, really most other specialities. I have linked the course that I took when I first started, and wherever you're watching this, I'll make it available. I'm not affiliated in any way, I just think it's a great course, and from my experience, paid courses are generally better. The content is more in depth, there's a community, the creators held accountable, and since I've put some investment in them, I usually convince myself to finish them. Once you know what object-oriented programming is, including concepts like classes, inheritance, and abstraction, you're good to go. You should be able to build something small without following a tutorial like a rock, paper, scissors game in the terminal, and be able to add new ideas yourself. For example, randomizing who starts the game, you or the computer, or like in this example, keeping score. And if I told you to create a parent class choice, you should understand how to add rock, paper, or scissors to implement that choice, and maybe you can have an abstract method which returns that choice as a string. It doesn't have to be good, just a small project done solo to make sure you get the hang of the language. And honestly, that's it for learning Python. Step 2, data structures and algorithms. I definitely think data structures is the more important of the two. You're much more likely to be asked to write a data structure than an algorithm from scratch in an interview. Plus, you will be using data structures every day on the job, which is not the same for algorithms. And as you'll see, you indirectly cover a lot of the algorithms by doing these Leetcode questions. Step 3 is this video. Step 4 is super important. It's your foundations as a software engineer. There's a 20-page doc I put together covering everything from bits to the cloud using what I think is needed from the job. I always refer back to this even now and keep adding to it. It's like my personal cheat sheet and I recommend everyone have one. And steps 5 to 7 are all interview related information. And finally, before we get into the technical stuff with big O notation, I have one last message. Please do not just watch this video or other content without doing the real thing. If you want the best possible chance to do well and remember how to answer Leetcode questions and how to write out data structures, you need to make your own notes. Write out your data structures multiple times. Solve the Leetcodes. Go back and solve them again without looking at the answers. Participate in mock interviews, timed coding challenges. Do the real thing and you'll be surprised at how much more you can remember by doing this. So now we should be ready to get into the fun stuff. Big O notation. We use time complexity to describe the amount of time it takes to execute a certain algorithm or program. Not hard time like seconds or minutes, but a mathematical generalization of the time taken. And we use space complexity to describe the amount of memory used by the algorithm. Of the two, time complexity is a lot more likely to be focused on. Space is cheap and memory is more readily available. Improvements in time are generally the more often bottleneck and felt more by the users. And when we talk about these complexities, we are referring to them as the size of the input grows. And this is technically where the big O definition comes from. You don't need to remember this technical definition, but it's good to know the origin. So, big O is a mathematical notation that describes the limiting behavior of a function when the argument tends towards a certain value or infinity. And finally, the reason we use big O is to help us describe the performance of an algorithm in relation to the size of the grown input. This provides us with a simple way to compare and analyze different algorithms' efficiencies. So let's look at an example. Let's say we are given a problem where we have a list of n numbers of unknown length and we do not know what numbers are in the list. We are asked to use code to find and return true if the number 2 is in the list and false if the number 2 is not in the list. Our solution could be to go through every position in the list and check if the number at that position is equal to the number 2. So here is our code, and let's take this list for example. 4 number in list, so we begin at the first index. If the number is equal to 2, then return true. If it's not, then we just continue. And we keep going along our list until we find 2, and then we return true. If 2 was not in the list, then we would reach the end of our loop, and we would break out and return false. And the time complexity for this problem is linear. As you can see, as the input size grows, the time taken grows in a straight line. To loop through the entire list of n numbers and make sure that 2 is or is not in the list, it would take n time, or the amount of numbers that are in the given input. We need to check every number in the list once, making this solution O of n, linear time. The longer the list, the bigger n is, and the longer it would take to complete our solution. And it's important to remember here that we are looking at the worst case scenario. If 2 was always at the start of our list, the operation would take constant time, one quick operation. But in our problem, 2 could also be at the end of the list, so we would need to iterate over our entire list to find 2, which as the list of n numbers grows, will take n time to check each number and find 2 at the end of the list, in our worst case scenario. What you're looking at here is 3 different graphs of the same thing. We are plotting the different types of complexities that you must know. We have around 7 complexities to cover, and we'll take a look at them more in the next slide. For now, the best thing you can do is add a graph like this to your notes. Pick the one that you find easiest to remember and refer to. Quickly, we can see that constant operations are the fastest, and this makes sense, right? If we were to pull an item from a list using its index, for example, the 5th item in a list, it will not matter if the list is 5 items or 5,000 items long. It's a constant operation. Logarithmic operations are the next fastest. Some graphs might show log n starting off faster than constant operations, and this might be true in some edge case practical applications due to the mathematical aspects of it, but I would really suggest focusing on the tail end of these graphs, because remember, big O is concerned with, as the input size grows, what happens to the speed of the operations. So we have constant, and then log n or logarithmic, linear, n of log n, which is linearitmic, quadratic, and subsequently cubic, so x to the power 3 and so on. And then we have exponential and factorial. So what you see here is a table of all of the complexities from the previous graph in the fastest to slowest order. I've also linked some more examples, but feel free to pause the video, do your own note taking and understanding. Right now, these concepts are probably still abstract to you, and that's expected. you'll only really grasp them once you put it into practice or do the real thing. And it's like driving a car. You can read everything there is about driving and changing gears, but you won't understand how it's done until you get in the car and drive it. So let's go through this table, and hopefully we should be somewhat aware of the different time complexities that exist before going on to solve problems. So the first one is constant time complexity. And this is where the time taken remains constant regardless of the input size. And this is the example we gave earlier by accessing an element in an array or list by the index. Next up is logarithmic, and this is where the time taken increases logarithmically as the input size grows. Operations are typically halved at each step. Time increases linearly as n goes up exponentially, and this is what gives us that curved shape which looks as if it's becoming a straight line, right? This one here. Next up we have linear, which is a straight diagonal line, and this is where the time taken increases proportionally to the size of the input. So if n doubles, the time taken doubles, and this was the first example that we showed. Next up we have n log n. And this is where the time taken increases in a linearithmic manner. So we often see this in divide and conquer algorithms. And if you're not familiar with what these are or some of these operations on the right here, it's fine. It's to be expected at this point. Next up we have quadratic, so n to the power 2, and the time taken increases quadratically as the input size grows. So each element needs to be compared with every other element, so we could have a for loop within a for loop, for example. After that we have exponential, where the time taken doubles with each addition to n, leading to rapidly growing execution times. So imagine if we had a list, and every time we added an item to that list, the time taken to complete our operation doubles. So this is extremely slow. And the slowest of all is factorial, so the time taken increases factorially with each increase in the input size. And if you're unfamiliar with what factorial is, it's something in maths where, for example, if we had 5 factorial, so 5 followed by the exclamation point, this would be 5 times 4 times 3 times 2 times 1, which is equal to 120. And so if we had 10 factorial, this equals 3,628,800. So you can see the rapid time increase going from just 5 to 10 factorial and how slow factorial operations are. So that's big O notation. There will be more material and detailed examples linked in this document, but this will definitely get easier with practice. So for now, let's move on to problem solving. We have all the theoretical knowledge in place. It's time to get practical. We need a framework for solving problems. I see many people fail in interviews because they don't have their own familiar process for problem solving. Not only does this help with solving the problem, but it gives an interviewer confidence in your critical thinking skills, and it allows them more opportunities to guide you on the right path. So step 1 is always to read the problem twice and understand it. If you're in an interview, take the opportunity to ask clarifying questions. For example, is there a range of numbers in the problem, or can it go from positive to negative infinity? It might not help you directly, but it helps you understand the problem space and get a bit more comfortable. And again, it shows the interviewer that you have critical thinking skills. Next, you want to think and verbalize different ways of solving the problem. At this point, you want to think of high-level approaches. And to get you started and feeling more comfortable, you can always start with the brute force approach. This might be the slowest complexity solution you can think of, but you can voice the fact that you know the solution is not ideal and that you just have one rough idea to get you started. You can think of more solutions, and for the best 1 or 2 solutions, take it more deeply and think about the solution end to end, from input to output, and the steps between. It's important to take all of these steps before coding out, because remember, even Einstein said if he had 1 hour to solve a problem, he would spend 55 minutes thinking about the problem and 5 minutes on the solution. So if you're not in an interview setting, I'd really recommend putting pen to paper and drawing out the problem and drawing out potential solutions with the pseudocode to go with it. And we'll see this in practice when we come to look at the questions. This will help you visualize your solution and see any steps that you might be missing. This is good when practicing because the more you draw things out, the more you begin to see the same patterns in different questions, and the solutions become second nature. So draw out the answer you think is the best, step by step, and write the pseudocode, from which you can now start coding out your answer. Once you have the answer and you can get it to work, see if you can improve it, or think of faster solutions that might take a different approach. After that, go through other solutions, even if you answered correctly. Leetcode lets you see the top solutions. However, be careful. A lot of the top answers take the competitive programming approach of writing the answer, chaining together several operations in one line in an almost non-readable fashion. I would suggest completely ignoring these answers because you want your code to be readable. This is something interviewers look out for. So look for the answers which seem logical and readable, and the comments will often include time complexities and good discussions around the solution which you can benefit from. So with all that being said, we now have a system in place for answering coding problems, and we have the foundation of the time and space complexities in our heads. Let's finally get our hands dirty and get into the fun stuff, answering some questions. I'd suggest pausing the video and trying to solve each question by yourself and coming back to discuss the solution. Follow the link in the titles or look for the same named question on Leetcode and try to solve it. You should also have your notes page ready where you can write the solution out and notes about what you've learned. So when you come back to practice, it's all there and it triggers your memory. If it takes you longer than 15 to 20 minutes to come up with an answer or you're not working through one, I'd suggest going straight to the solution in the interest of working efficiently. Then try to write out the solution and later in the day, come back to the question without looking at the solution. So this is the arrays section and duplicate values is our first question. And while I was making these notes, I added this banner here as a guide where it shows the percentage of people who have passed this question successfully on the first try. It's not something to take note of honestly because anyone can look up the questions or go straight to the solution and write their answer, but it was just a good way for me to try and hit a range of difficulties in questions when working through each section. So let's take a look at this question. Given an integer array nums, return true if any value appears at least twice in the array, and false if every element is distinct. And we have some examples down here. So because 1 is in this list twice, we return true. And because there is no double or duplicate value in this list, we return false. So immediately I can think of one solution where we loop through the list and at each point we loop again to check if the number exists twice. So at 1 we would loop and we would go a nested loop to find this one, and if this one did not exist then we would go to the 2 and then we would send out another loop forward. This solution is quite slow however because we have a nested loop and it would take around quadratic time or n squared time complexity. A better solution would be to use our Python skills and use a set. A set in Python is a built-in data type which does not allow for duplicates amongst other properties. So if we take a set of the given list and we check the length of it against the length of the original list, we will know for certain that any difference in the numbers means there was at least one pair of duplicate numbers. This solution is O of n, a lot faster than the nested loops. And down here you can see I wrote some notes to myself at the time that I was practicing on how to create a set in Python and the lookup time for sets. And I encourage you to do the same. So fairly simple, and I don't think it's worth whiteboarding this solution. Next up in arrays, we have missing number, and without even reading the question, I have left a little reminder to myself as to what the question is. And this will be super useful for when you're practicing later and you keep coming back to do the same question and you don't want to come over here and read the whole dialogue. So it tells us, given an array of nums containing n distinct numbers in the range 0 to n, return the only number in the range that is missing from the array. So quite a wordy description. Here we have 301 and the output is 2. So it looks like we just return the missing number. However, we also need to be careful here because the question tells us from 0 to n. And we can see in the second example that we are looking at the length of the array. So if we have two numbers in the array, 0 to n becomes 0 to 2. And we want every number, 0, 1, and 2, even though it looks like this is a complete array here from 0 to 1. Initially, I created this solution where I sorted the numbers and looped through the enumerated list. This gives us I and v, where I is the index and v is the value inside the loop. So for this example, in each loop, we would sort the list, and at index 0, we would have the value 0. At index 1, we would have the value 1. And at index 2, we would have the value 3. So next I have an if statement to check if I is not equal to v, because at some point the value would be 1 greater than the index. And at that point, we can return the value that should have been at that index, which is v minus 1. Returning the index here would have worked also. And finally, we can cover the edge case in example 2. This solution is n log n, which is relatively slow. And the reason being is that sorting in Python is n of log n. And so that slows our entire solution down. Otherwise, the rest of it would have been linear. And we can see from the submissions that I made how slow my initial solution was in comparison to others. A better solution would be to take two values, the first value being the expected sum of our list, and minus from it the actual sum of the list. And the difference will give us the missing number. And to get that first value, we take the length of the list and plus 1 to it. The reason we plus 1 is because next we take the sum of the range, and the range in Python excludes the last value. So range 3 would only give us 0, 1, and 2. If we plus 1 and take range 4, that would give us the expected range, which is 0, 1, 2, 3. So we add 1, take the range and the sum. From there we have our value and we can do our calculation to find the missing number. And this gives us an O of n answer, because you can see in my notes the relative time complexity it takes for each operation in this solution. If our list or input grows by double, for example, we only have to do double the additions. And so this summation here would be our bottleneck. I'll put on the screen a good explanation on doing more of the same operation in a linear fashion, and how we can look at multiple operations in the same solution to figure out the time complexity. So bear in mind that doing multiple of n operations sequentially, like we have here, and not nested, in the same algorithm or solution would still equal O of n. And so that's our solution for the missing number. In these next two slides, I've left some raw notes to show you guys the type of reminders I would leave for myself. Here I was playing around with the different ways to iterate through dictionaries and the difference between sorted and sort functions in Python. I also had a look at Lambdas after seeing them in some solutions, and I played around with the code. I wouldn't recommend getting too far deep into Lambdas because in my opinion you can do the same things using plain code like loops, and Lambdas are slightly less readable. But this did make me more comfortable with the language, and the next time I saw Lambdas I could rewrite the solution to my style. Anyway, on to the next array question. Find all missing numbers. In this problem, we have to check the given list for missing numbers in the range 1 to length of numbers. So this is a nice little reminder for myself because I've seen this question before. But if you've not seen this question, let's read the official description. Given an array nums of n integers where nums I is in the range 1 to n, so essentially we're given a list of numbers from 1 to n, return an array of all the integers in the range 1 to n that do not appear in nums. So we have a list of nums here, and I can see we have some numbers repeated like 3 and 2, and we need to return the numbers that are missing from the range of 1 to n, where n is the number of items in our list, or the length of the list. And we return 5 and 6 because they're the ones that are missing. And this looks to be true in the second example also. So whenever we're looking at duplicates, my mind immediately goes to if we can use sets. So let's go over to our whiteboard and have a look at the solution. This is the nums that was passed in the first example. And here I've written out our solution. The first thing we want to do is take a set of our numbers. So this means we're going to have the same list as a set where all of the duplicates are removed. And it's not relevant here, but just a reminder that sets in Python are unordered also. So we have 4, 3, 2, 7, 8. We already have 2, we already have 3, so let's add the 1. And we're going to create a list called ret so that we can return this. And in here, we're going to put the numbers that are missing. And then we're going to loop through the range from 1 to the length of our numbers plus 1. So the first value is the first number that we will loop from. If we do not include this, the range will start from 0. But the question tells us we're starting at 1. And the length of our list here is 8. And remember that the end of the range in Python excludes that number. So we want to add 1. So this value becomes 9, and our range is from 1 to 9. And the 9 will be excluded, so it's from 1 to 8. And simply for each I, or each number from 1 to 8, we're going to check if it's in our set. And if it's not, we're going to add it to our list here. And at the end, we're going to return this list. So 1 is in our set, 2 is in our set, 3 is in our set, keep looping, 4 is in our set, but 5 is not. So here, we're going to add I, or 5, to our return list. Loop again in our range, and the next number is 6. 6 is also not in our set, so we can add this to our return list. And 2 more loops, we see 7 and 8 are in our set. And finally, we can return this list, and that is our solution. We've solved this in linear time because we're iterating through our range and appending to the new list. If the size of our list doubled, the number of operations would double also. And we're using O of n space because we've created our list in our set. Again, if our input doubled, then the length of the set might double depending on how many numbers are missing. But remember complexity and worst case, so in the worst case, 1 or no numbers are missing, so the set will definitely double. And the return list, if we had more numbers missing, would also grow in a linear fashion. I've also included a solution which had O of 1 space. Right now, I don't think it will be beneficial to go through it, but if you're looking to improve your Python skills and understanding of these questions, it will definitely be useful to go through this constant space solution, so here it is. And so that covers everything on this find all the missing numbers question. Next up, we have twosum, one of the most popular questions on Leetcode. Given an array of integers, nums, and an integer target, return indices of the two numbers such that they add up to the target. And we can assume that each input would have exactly one solution. You may not use the same element twice. You can return the answer in any order. So if we have an array of numbers here, and there are some large constraints on the numbers, so pretty much the list can have any numbers inside, and we're given a target, we need to return the indices of the two numbers that add up to that target. So 2 and 7 are in position 0 and 1, and they equal 9. Let's take a look at our whiteboard. So our brute force solution could be to go through each position in the list and check against the rest of the numbers in the list if the addition equals our target. So if we started at number 2, we would then send out a second loop to check 7, 11, and 15 if they equaled our target. And if we did not find a solution, then we would loop to the next number and send out another loop, and we would do this again. So this is an example of nested loops. And in our example here, even though we would achieve this on the very first nested loop, it's important to remember that when we look at time complexity, we're looking at the worst case scenario. So if these two numbers here were not in the first two positions, there is the potential to loop through our list of length n, and for each number we would do n more loops, giving us O of n squared. So this is a very slow solution, but it's a good start. A better solution would be to pass through our array once. And the way we're going to do this is using a trick which might be difficult if you've never seen this question before. So if we were being smart about this, we could base our solution on the fact that for each number, our target minus the current number gives us the only value that works. So 9 minus 2 gives us 7, and we need to find 7 in our list to be able to return a solution. And this works for every number. If we took 9 minus 11, we would have minus 2 as our solution, and we would have to find minus 2 in our list. The best way to do this is to create a hash map, also called a dictionary in Python, of our numbers in the input array and their positions as we loop through our array one time, value and index. So I'm just going to change the order of our input array here so that we can fully understand the question and we pass through one more number before getting our solution. So our solution here would be 0 and 2. And I'm just going to add the indexes on top of each number so that we don't get confused. Okay, so initially we take our value 2 away from the target 9 and we realize that we need to check our hash map for the number 7. Initially our hash map starts off empty, so we don't find 7. In that case, we add 2 to the hash map and the position of 2 in our array. And then we move on to 11. We check the values of our hash map for minus 2. That doesn't exist, so we add 11 and index 1 to our map. And we move along in our loop to the second index, or the third item in our list. We do 9 minus 7, and we realize we need to check our hash map for the value 2. 2 is in our hash map, so we can return the indices 0 and the current pointer, which is 2. And there's our solution. The reason we keep our hash map empty initially instead of populating it and then checking is to avoid using the same number twice. On an abstract level, let's say we had an array here where each box represents a number. And let's say these two numbers are our solution. At any point in our solution, we have checked the left side of our array, and hash map only includes the values that we've looped over. And when we finally reach the second element of our solution, we know for certain that we're going to find the previous element, which gives us our solution, because the hash map has now been populated with the value and the index of that first element. But if we had an array which only contained the number 2, so we only have 2 at index 0, if the target was 4 and we had pre-populated our hash map, we would end up using that 2 twice. And that's why we fill the hash map while iterating over our array. Since we are only iterating once, which is linear O of n, and adding each value to our hash map, which is a constant time complexity, and looking up in our hash map or dictionary, which is also a constant time complexity, our solution is O of n. In terms of space, we are creating our hash map, and if our two values were the last two in our array, we would have a hash map of length n minus 1, which we can simplify down to O of n space. So if you've not yet looked at the code, I would recommend pausing here and giving the code a go now that you know the theoretical solution. Otherwise, let's look at the code. On the left is the solution that I first wrote out. I added a note to myself that we can clean up repeated code by creating a variable, for example, target minus v, and reusing that instead of the same operation twice. And we're doing this on the right here, creating the variable diff. So we have our hash map, and for each index and value in our enumerated array, we find the difference of the target. So for example, 9 minus 2, which gives us 7. We check if the difference is in our hash map, which initially starts off as empty, so the value 7 is not in our hash map, so we can add the value 2 to our hash map with the current index, which is 0. Eventually, we would reach 7 and find our target value 2 in our hash map, which is the difference between 9 and 7, and then we can return the current index, which would be 2, alongside a lookup in our hash map based on the current diff, which is 2 or 9 minus 7. We check the keys of our hash map for 2, we find 2 and return the value 0, which denotes the index of the second number of our solution, which adds up to the target, 9. And that is the solution to 2SUM. After completing this solution, I looked at other solutions and I found one in Java. Now, typically I wouldn't recommend looking at other languages, but it was just from my experience and being able to say that I kind of understand another language and how it works. And you can tell which solution I wrote was in Python and which one was in Java. Typically, Java runs faster than Python because it is a compiled language versus Python, which is interpreted. And if you're not sure what that is, go ahead and look it up. Or you can check out the material provided on software engineering concepts, which has everything you need to know covered inside. Over here on the right, we can see the difference in Java and Python for a different problem, which is called final value after operations. Now, I'm not going to go into this problem too deeply because the focus of this is the difference in the languages. Essentially, all we have to do is return the value after a string list of additions and subtractions. So we start off with 0, and for each minus or plus in a string that we're given, we either add or minus 1 to x or 0. So it's a fairly simple problem, and you can see 90% of people passed it. But over here on the right, you can see why I recommend Python over Java, because the same problem is so much more convoluted. We have to set the types of our input and our variables as an integer or a number, and a string list, which is the plus and minuses. And there also goes a lot more into creating a loop. We have to say the number we start at and the conditions for breaking out of our loop and what happens at the end of each loop. So just something to be aware of in terms of the differences between languages, and something that you can refer to if you're ever asked about Java and Python, or typed languages and interpreted and compiled languages. So take a look at these and maybe make a table and add the differences to your notes. Next up, we have how many numbers are smaller than the current number. And the question tells us, given the array nums, for each nums I, find out how many numbers in the array are smaller than it. That is, for each nums I, you have to count the number of valid j's such that j does not equal I and nums j is less than nums I. Return the numbers in an array. So this description is quite confusing, and it's typically only when I read the examples that I understand what the question is telling me. So example 1, 81223, and we return 40113. So I can see now that 8 is bigger than 4 numbers in our array, so we return 4 for that index. 1 is not bigger than any other number, so we return 0. 2 is only bigger than one other number. The second 2 is also only bigger than one other number. And 3 is bigger than 3 other numbers. Immediately, you should recognize that similar to the question 2sum, we could do a nested loop solution, checking for each number, all the other numbers, and seeing if it's bigger or smaller than it. However, this solution would be quite slow, giving us O of n squared. Instead, a better solution I found is to start by sorting the list, which is n of log n, and this allows us to avoid the nested loops. So let's take the first example and go over to our whiteboard. First up, we would create a temporary variable, which is our nums array but sorted. So we would have 1, 2, 2, 3, and 8. We then create an empty dictionary, and then we would loop through the enumerated sorted list that we called temp. And the reason I was able to come up with this solution is because I had just completed 2sum, and while drawing out the solution, I began to see the same patterns in this question. So at this point, we check if the number is not in our dictionary, then we can add that value to the dictionary. And before carrying on with the rest of the solution, let's go ahead and give this a go. So initially, we will have an I, or an index of 0, and the number 1. Our dictionary is empty, so we can just add the two values to our dictionary. Next up, we have 2 at index 1. And next we have 2 at index 2. And so 2 already exists in our dictionary, so we don't do anything. And this will be key later, and the reason that we sorted it in terms of figuring out the other numbers that are larger than the current number. So we continue, and we have 3 at index 3. And then finally, we have 8 at index 4. After that, we create our return list, and we do one final loop. For I in nums, we're going to add to our return list the value for that index. So for I in nums, so this list here, 8 is our first value. We will append to our return list the value of the key I, which is 8. So simply put, we check our dictionary for I, which is 8, and add the value 4. Next up, we check our dictionary for the number 1, and we find it in this key pair value and add the value 0 to the return list. Next up, we have 2, and we check our dictionary and we find it has a value of 1, so we add that to our return list. And here is where the magic of the solution comes in, because we have the duplicate value 2, which we're checking next. In our dictionary, 2 has the value 1, so we add 1 to our return list. This 2 is also only bigger than one other number, which is the 1. And we managed to keep our solution intact by checking if the number was not already in the dictionary at that point. And if you remember, we skipped adding the second 2 to our dictionary or updating its value. This way, the values of each number in our dictionary represents the previous numbers it's bigger than, avoiding any duplication issues. And finally, we have the number 3, which gives us a value of 3 also. So we would return this solution here, which is the correct answer. In my notes, I added a reminder to myself that time complexity is more important than space, because when I completed a mock interview with an engineer who was already in a big tech company, he told me that space is cheap, and so we focus on time complexity. And that became an important reminder for me. Finally, I also added an O of n time complexity solution. So this would be an improvement on my solution. However, I found this answer quite convoluted, and I thought to myself, it would be pretty difficult to come up with this on the first try. And as an interviewer, you would be pretty impressed, and if not, a bit skeptical if someone could come up with this answer on the spot. However, it was good practice to go through the solution and see how it works. So I'm not going to go through the solution, but feel free to give it a go yourself. Next up, we have minimum time visiting all points. And I really like this question because it's slightly different from your typical array type question, and the solution is quite unique and it taught me some key lessons. So if you want to give it a go, pause now. On a 2D plane, there are endpoints with integer coordinates, points I equal to x and y. Return the minimum time in seconds to visit all points in the order given by points. You can move according to these rules. In 1 second, you can either move vertically, horizontally, or diagonally by 1 or square 2 units. So we can either move diagonally in 1 move, or 1 second, or vertically, or horizontally. You have to visit the points in the same order as they appear in the array. You are allowed to pass through points that appear later in the order, but these do not count as visits. So if we were given these points, our result would be 7 seconds, which is the minimum time to visit these points. And one thing that I think the question misses is our starting point. And for example, if you're in an interview setting, this might be a good opportunity to ask a clarifying question. Do we have to start at 0, 0, or can we start at the first point in the array that we're given? In this question, we can start at the first point. So we start at 1, 1, and we move diagonally, going to 2, 2, 3, 3, and then up to 3, 4, which is the second point in our list of coordinates. And finally, we move diagonally all the way back down to -1, 0. And each point is 1 second in our traversal, and so we have 7 seconds. If we first take a look at my notes, this was a key point in my practice or learning because I realized that coding should not be the difficult part. In this question, I spent a lot of time trying to code up the solution and working on the wrong things. And I realized that if you understand 1 or 2 things, the rest of the problem should be easy. And this is where I set the hard limit for myself on 15 to 20 minutes to come up with a working solution. And the key idea in this question was that the distance between 2 points is the maximum difference between one of the coordinates x or y. So what this means is that if the next node or coordinate is 10 units away on the x-axis but 5 away on the y-axis, it's going to take exactly 10 steps to reach that point. The reason being is that you can only move one x or y at a time, or you can move diagonally. So if you move diagonally, the difference in the y, which is the smaller of the two differences between the current coordinate and the next coordinate, this 5 units difference is made up by moving diagonally. So you move diagonally as much as you can, and during the process, the difference in the y will be covered. After that, you reach a point like this, at 3, 3, where all that's left to do is move in one direction, either vertically or horizontally, to make up the remaining difference in the x or the y axis. So if we head over to the whiteboard, this should make more sense. We start off by creating a result variable which will keep track of the length of time our solution will take. Given the points that we have to hit, we pop off the first 2 units, which is 1 and 1, and this will be our starting point. And we create a while loop which only breaks once we've visited all of the points and our points array is empty. We'll see this at the end. Next up, we pop off the next 2 coordinates in our points array. So x1 and y1 are 1, 1, and x2 and y2 will be 3 and 4. And here is the key to this solution, which I explained earlier, in that the minimum amount of moves we can make is the maximum difference between either the x's and the y's between the 2 points. So we take the absolute difference of the y values and the absolute difference of the x values, and we see which of these 2 values is bigger. For the y's, we have 4 minus 1, which gives us 3. And for the x's, we have 3 minus 1, which gives us 2. So we add the value 3 to our result. And we can see this is true by looking at how we move from 1, 1 to 3, 4. We move across diagonally as much as possible, and that takes us 2 seconds. And then we can only move horizontally to make up the final difference in the y units, which gives us 3 seconds. Then we update our coordinates, so 3, 4 is now our x1 and y1, and we repeat the same process with all of the points in the list. At the end, we'll have our result, which is the total seconds it takes to hit all of the points in optimal speed. And this is our solution. Now, a question like this might not be asked in the interview because it will be quite difficult to convey a graph type setting, but I added this in here because it's a key learning point that once you understand one or two key concepts in most questions, coding it up then becomes super easy. And as you can see, we only have one while loop with a bunch of constant operations inside. So this gives us a time complexity of O of n. We're also only storing a set number of variables. The result, x1, y1, and x2 and y2. And regardless of the growing input size, we're only storing these set variables. So that gives us a constant space complexity. And that is our solution for the minimum time to visit all points in a graph. Next up, we have our first medium question. And this is one of my favorite questions. Given an m times n matrix, return all elements of the matrix in spiral order. So if this was our matrix, we would go along the first row, down the last column, in reverse, along the last row, and then back up and to the middle. And the same for a larger matrix. So it sounds fairly simple, and this is one question that I would highly recommend giving a go. So if you feel up to it, pause the video and give it a go. This might take a long while to figure out or get the code working, but I'd suggest not giving up. As you can see here, there's a lot to cover in my solution. On the left, I've included the working out that I did to get to my solution, and this took me quite a while. And you can see the value when I suggest to you guys to draw stuff out and work it out, because it really does work and it really does help you quite a lot. I started off with the first matrix that they give us in the question, and I put it alongside the input or the matrix array. And then I began drawing out the solution. Our first move is to go across the first row, and I saw that directly corresponds to the first array. And then I saw that going down correlates to the last 2 points in the last 2 arrays. Then the purple line going back left is the reverse order of what's remaining in our last array. And the orange line going up and the green line going across will be these 2 values here. So I had a basis for some sort of pattern, and I repeated it with a larger matrix to try to generalize the solution. Again, I saw the first row was the first array of our matrix, the same last 2 elements by going down. Going back left on the last row was again the reverse order of the last array minus that last value, and the orange and the green line were these 2 values here, except now we had an extra in our green line. So I repeated this once more with a larger matrix, except this time I increased n as well as m. After that, I was happy to pull some sort of algorithm from my whiteboarding, and I wrote it out at a high level, and I came up with this one here. From this, I coded up my solution, which you can see on the right. It took me a while. For example, my algorithm on the left forgets to check if the matrix traversal is complete, so I had to add this function after. And you can see how each step correlates to a section of the code on the right. So after trying to submit my solution, getting it wrong, trying to tweak it and improve it without looking at any solutions, completely doing it by myself, I finally got to a working solution that passed all of the tests. And this really increased my confidence tenfold. I completed a medium question by myself just by putting pen to paper, coming up with the algorithm and writing it out from scratch. After that, even though I was correct, I looked at the best solution I could find, and it was a much more simplified and cleaner version of my solution. But again, I was happy to see that I was on the right track. So this is our solution here. Let's head over to the whiteboard and see how it works. So here we have the simplest matrix from example 1, the input that we're given, and our solution on the right. If you want to give it a go on one of the larger matrices, feel free to play around with it after this solution. The first thing we do is create our return variable, and then we check while matrix. And this was one of the first key differences I saw in my solution. In my solution, I was checking while true, and then I added a function to check if our matrix was empty, and if it was, then we could break out of our while loop and return our result variable. If I hadn't have come up with the solution first, it definitely wouldn't have registered as much, this key difference in how to write while loops in a cleaner fashion. And this is why I'd always recommend to come up with your own solution, no matter how messy or slow your solution might be. Anyway, the first thing we do is add the first row / list of our matrix to our return variable. And we do this by popping off the first list from the matrix, which is 1, 2, 3. And using the plus equals means we just add the items instead of the array itself. Next up, we move to step 2. If our matrix exists and the first list within our matrix is truthy, then for each row in our matrix, we append to our return variable the last item in that row. And we do this by popping it off. So that would be the 6 and the 9. So let's remove those and add them to our return variable using the built-in append. Next up, we move to step 3. Add the reverse of the last list. So if the matrix exists, we pop off the last item. So when you don't add an index, we're popping off the end. We're adding this to our return variable in reverse order. So we would add 8 and 7. And this is this move down here along the bottom row in reverse. Next, we move to step 4. the matrix does exist and the 0th element is truthy. So for each row in our matrix in reverse order, so this will come into play for a bigger matrix, but for now, reversing the order of our matrix gives us the same matrix. So for each row, which is the list 4 and 5, pop off the first item from that array and add it to our return variable. So let's add the 4 and not forget to remove it. So we go back to the top of our while loop, the matrix still exists, and we're back at step 1. In step 1, we're popping off the first item from the matrix and adding it to our return variable. So let's add the 5 and remove the first item. At this point in the second step, the matrix does not exist, so we can break free from our while loop and return our return variable. 1, 2, 3, 6, 9, 8, 7, 4, 5. 1, 2, 3, 6, 9, 8, 7, 4, 5. This solution is O of n because each operation is linear. So as our matrix grows, our operations grow linearly. There are no nested loops or any operations that could expand in a non-linear fashion as our input grows. And so that is the spiral matrix question, our first medium question in our arrays section. Next up, we have number of islands, and this is a very nice question because the solution introduces a new concept which we'll be looking at later. So given an m times n 2D binary grid which represents a map of ones and zeros, which is land and water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are all surrounded by water. So if we take the first example, we can see that the output is 1 because we have an island here. And all of them are connected horizontally or vertically. So if we had a 1 in this position, it would be a separate island. And we can see that in the next example. So we have one island here, the second island, and the third. And essentially we need to iterate over this grid in some way that we can find all of the islands. And initially I can think of one very slow solution, which is to brute force it in some way by iterating over each position in the grid, and then maybe a second iteration around to check whether there's ones and zeros. And to be honest, if you're not familiar with the concept that the solution implements, then I would be very surprised if you were to get it on the first try without using some slow brute force solution. However, if you watched the data structures video, then you might remember the search algorithms that we went through, giving you a good chance. So let's take a look at our solution. We will be using breadth first search. Again, if you have completed your data structures, this will be very familiar to you. If not, I'll quickly go over it. Breadth first search is a traversal algorithm that explores nodes or elements in some iterable object like a tree. Breadth first search is commonly spoken about alongside depth first search. You can think of them like two sides of the same coin. Breadth first search explores all the neighbor nodes on the same level before moving on to the next level. And we'll cover these two algorithms a lot more in binary trees. So it's a good reminder to ourselves in this section. Typically, there are two implementations of both the algorithms, iterative and recursive. I typically don't like recursive algorithms. They're harder to read and debug, and they can take up a lot of space in memory, which can cause stack overflow. We have gone so far deep in a call stack that there is no more available memory. So I recommend using the iterative approach. And remember from our data structures practice, a key difference is the use of a queue in breadth first search versus a stack in depth first search. So let's take our solution over to the whiteboard. This is the grid in question, and let's start off our solution. We first of all check if we have a grid, and if we don't, we return 0 because there are no islands. Let's ignore this breadth first search function for now and continue following the execution the same way the code would. And let's go down here and create these variables. We start off with a count of 0, which will count our islands, the rows and the columns of our grid, and we'll be using these to make sure we're in the right range, so we're not checking any positions that are outside, which will give us an index error. And then we have a visited variable, which is just an empty set for now, and it will keep track of all of the elements in the matrix which we have visited or not. Then we start off with a nested loop. So for every item in each row and every item in each column, so we'll be going along the rows and then the columns. So our rows will be the length of the grid, which is 1, 2, 3, 4, and the length of the first item in the grid, or the first row, which is 5. So in range 4 and in columns 5, if grid RC, which will be 0, 0 because we're on the first iteration of each range, if this equals 1 and RC is not in visited, then carry out the breadth first search function that we skipped earlier. So position 0, 0 equals 1 is true and RC is not in visited, 0, 0. So let's go ahead and jump to our function here. Let's create a queue, and I think it will be better to call it search queue because this will hold all of the positions in our matrix which are next up to be searched by our algorithm. And I've initialized it as a deck here, but a queue would work just as fine. Now let's add 0, 0 to our visited set. And remember, sets do not allow for duplicates, which is why we use one. You know, we could have used a list and then check if 0, 0 is already in the list, but this is much more efficient. And then we're going to add 0, 0 to our search queue. So while our search queue exists, let's pop off the first item. So we're going to grab this 0, 0, and to this first coordinate, we're going to add a bunch of different directions. And remember, this is the up, down, left, right. We're going to check to see if the island exists and not the diagonal as the question told us. So we have our first coordinate, and then we're going to be adding some directions. The first one is 1, 0. So we've added to our row and our column here, which are 0, 0, the direction in the rows and the direction in the columns that we're going to search, which is just up, down, right, left. So inside our for loop here, the R and the C are going to be 1 and 0. 1, 0. And I think it might be good to cross off 0, 0. Even though we've not finished searching around it, it's in our visited set, and I think this will help us keep track. But it's the current item we're searching, so I'm going to draw a blue circle around that. So we're on this line now. R is inside our range, 1 and 0 is inside our range for the columns. So that's nice and easy. We just have a quick sanity check. Now, is grid RC equal to 1? So 1, 0 would be the second column because we're 0 index based in Python, and it would be the first column inside that second row. Is the value equal to 1? Yes, it is. And is it not invisited? 1, 0 is not invisited, so let's go to the next line. We're going to add 1, 0 to our queue. And then we're going to add 1, 0 to visited. And at this point, you should be able to see the breadth first search algorithm starting to come to life. We're still inside our for loop for the position 0, 0, so we don't need to update our blue circle yet. Back again, we're going to check the next set of directions. So RC becomes -1, 0. Immediately, I can tell this is outside of our grid. So we go to the next one because this if will be false. The next one is 0, 1. 0, 1 is the first row and the second column. This is equal to 1 and it's not already in visited. So we're going to add the position 0, 1 to our queue and our visited set. And I'm going to cross it off, adding it in here. Back in our directions, 0, -1 will be out of range, so our if statement will not execute. We go back to the top of our while loop in that case, and we start off again by popping the next item in our search queue that we are going to search. So we're going to pop off this 1, 0, update it down here, and we can move our blue circle to 1, 0. And at this point, you can tell in our traversal algorithm that we're going to search what's right and what's down of the current item. So let's give it a go. So we're currently searching 1, 0, and we're going to add these directions to it. And we're starting off with 1, 0. Our new RC will be 2, 0. 2, 0 is in the range of our grid. 2, 0 is equal to 1, third row and the 0th column. So we're going to add it to our visited set and append it to our queue so that we can search it later. So let's cross it off, add 2, 0 to our visited set and append it to our queue. And then we go back to the top of our for loop, check out -1, 0. -1, 0 will give us 0, 0, except 0, 0 is already in our visited set. So this if statement will be false, and we go to the next direction that we need to search. So we've already searched the one above. Next up, let's add 0, 1, which gives us 1, 1, and that will be the item that's right of our current search element. So I've crossed it off because it's in the range, it's equal to 1, and it's not in visited. In that case, let's add it to visited and add it to our search queue. And then finally, we're going to check 0, -1. That would give us 1, -1, which is outside of our grid, and that finishes our search for this element. We go back to the beginning of our while loop, and in our search queue, we will pop off 0, 1 and repeat the whole process again. At this point, you should understand kind of what's happening. If you don't, I'd recommend continuing to carry out this algorithm by pen and paper. But essentially, at this point, we would check this one here, cross it off our search, update the visited, and repeat the process for 2, 0. At this point, we would search around, cross this one off, update our visited set, update the queue, and eventually we would cross off these two here, and we would finish because our queue would be empty. So we would break out of our while loop and come back down here, update the count by 1. At this point, we are still only on 0, 0 in these two for loops. So R is still equal to 0 and C is still equal to 0. But we've visited a bunch of items and added them to our set, plus the others that we went through quickly. So back at the beginning of our nested for loop, the next item to search would be 0, 1. 0, 1 is in our visited, so this if statement would be false and we would move on to the next one, which would be 0, 2. We would continue repeating this process, and for this example, we would find that we have visited all of the ones that are possible, and if the item in the grid was not in our visited, then it is not a 1, and so the if statement would also be false. At that point, we've found the only island that we can. We break out of our two for loops once we reach the end of our grid, and we return the count of 1. So it's a super cool solution, and if you just spend a minute or two drawing out the algorithm, the traversal immediately becomes clear, and you can quickly pick up on the concept of breadth first search and how we are approaching this solution. And if you're still struggling with it, I'd recommend to give the second example a go. And finally, the time complexity for this solution is O of m times n. So something new that we've not looked at. This is somewhat similar to the n squared time complexities, except in this case, our rows and columns could be very different. So we're doing m times n. It depends on the input here. And in actuality, our solution is 4 times n, because in the worst case scenario, we could search each position up, right, left, down, and we find another one, and we search again up, right, left, down, and we continue doing this. Except when we look at time complexities, we're looking at the worst case scenario. So when our input is extremely large, this 4 becomes so insignificant that we can boil our solution back down to m times n. And that is the number of islands solution. So next up in our array section, we have 2 pointers, and this is a common technique when working with things like arrays and linked lists. And if I zoom in here, you can see 2 pointers is a common pattern that you might come across, and don't be too concerned with what's actually happening in the image. Just be aware of the fact that it's a reminder we have 1 pointer and a 2nd pointer in our array or linked list or some kind of iterable, and we're using those to solve the problem. So our first question is the best time to buy and sell stock. Go ahead and give this a go if you want to, otherwise let's read out the question and go through the solution. You're given an array prices where prices I is the price of a given stock on the ith day. So for example, 7 would be the price on day 1. You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. Return the maximum profit you can achieve from this transaction. If you cannot achieve any profit based on the prices array, then return 0. So in a sense, we want to find the greatest difference going forward. So we have to go from left to right, and the second number is when we sell. So we're minusing the first number that we choose from a number that must come after it. So 7 and 1 might give us a bigger difference, but we'd have to do 1 minus 7 because we're buying at price 7 and selling at 1, which would give us minus 6. So the best difference, in fact, is to buy at price 1 and sell at price 6. 6 minus 1 gives us 5. And in this case, the numbers are always decreasing. So whatever price we buy at, we're going to have to sell at a loss. So in this case, no transactions are done and the maximum profit is 0. Let's give a look to the solution. So our solution says, reminder to myself, greedy algorithm. I know that this is an algorithm where we make the best choice at each step in our problem. Or in other words, making the locally optimum choice at each stage. And this is in our 2 pointers section. So you already know we're going to use 2 pointers. So we have a left and right pointer. So for each left pointer, iterate right across and calculate the profit. When right is greater than L or left, we know we have evaluated all potential maximum profits. So move left to where right is and repeat. So this might sound a bit convoluted, but let's look at the solution on our whiteboard. So let's take the first example and have our set of prices here. So we initialize a left and right pointer at 0 and 1, and we initialize a variable of max profit and start it off at 0 because if we can't find any profit, we return 0. We have our left pointer at 7 and our right pointer at 1. While right is not equal to the length of prices, so while we're not at the end of our list, if prices left is less than prices right, let's carry out some functionality. So first of all, is prices left less than prices right? Well, 7 is definitely not less than 1, so we can skip this if statement and head to making left equal to right, and then we plus 1 to our right pointer. So back again, we repeat our while loop. 1 is less than 5 for sure, so we can calculate our profit at this point. And you can see we're going to be calculating our profit at each point using the 2 pointers, and this is why it's a greedy algorithm. We're calculating the best possible choice at each stage of our problem. So we check, is our new profit greater than our current maximum profit? Well, 5 minus 1 is greater than 0, so we can update our max profit to be 4. And now we can update R to be +1. So the reason we're not moving left is because we want to calculate if there's a greater opportunity for the same buy price, our left pointer. And without going through each line of code, we know that 3 is going to be less than our current max profit because 3 minus 1 gives us 2. So we move right again in this line. Right is still less than our length of prices because it is 0, 1, 2, 3, 4, which is our pointer. So it's the value of the index that we're currently looking at, and our length is 6. So is prices left less than prices right? Yes, it is. The profit at this stage would be 5. 6 minus 1 is 5. And we're checking our new profit against the max profit. 5 is greater than 4, so we update and move along in our while loop. Update R, so the value of R is 5 and it points to the element in our list, which is the number 4. 1 is less than 4, but the profit by buying at value 1 and selling at value 4 is not greater than our current max profit. So at this point, we would update the right index pointer by 1. Back at the top of the while loop, the right pointer is now equal to the length of the list. So we break and return the max profit. And you can see why this simple statement works now, because if we found a new value in our prices which was less than current price, and we had already evaluated all of the options up until that price, the next best step would be to begin re-evaluating from that price. So if we had the value 0 after the 6, we know that when our left pointer is at 1, we've already evaluated the 5, the 3, and the 6. And then our right pointer hits 0. We know that from this point forward, any profit we try to calculate is certainly going to increase by making our new left pointer, which is our buy price, the 0. And that's why this simple if statement works so well. And that's the reason for updating our left pointer to be our right if this is not true. But back to the question we originally had at hand, we update R by 1. At this point, R is equal to the length of our prices because Python is 0 indexed. So at this point, R is equal to 6. So we break out of our while loop and we return our max profit. So using 2 pointers instead of a nested for loop, which would have given us an n squared time complexity, we can get an O of n complexity, which is a lot better. And we have constant space because we're only keeping track of 3 variables. No matter how big our input prices array is, we're still only keeping track of these 3 variables. So that completes best time to buy and sell stock, a nice introduction to 2 pointers. Next up, we have this array squaring and sorting question. And this is a really good one because I know there's at least 3 approaches we can take to solve it. And it would be really interesting for you to pause and give it a go and see which solution you come up with. And going through each solution will really help us understand time complexities. So this is a good question for that. Given an integer array nums sorted in non-decreasing order, so from smallest to largest, return an array of the squares of each number sorted in non-decreasing order. And if it's not obvious, one easy trick to getting a fast time complexity solution in this question is to understand that squaring a negative number or a positive number gives us the same value. So we need to square all of the numbers and sort them. And it says down here, squaring each element and sorting the new array is very trivial. And that is why this question has a high pass rate. It's finding the O of n solution, which is a bit difficult. So first of all, let's take a look at the easiest solution. And you can see down here, I just made a note to myself that there can often be multiple solutions, and it helps to evaluate the time complexity of each sub-process to help us try to find the optimal solution. Not only that, but it does also help with identifying the time complexity of the current solution you have. So the simplest one is to square all of the numbers in our list and then sort them. Iterating through the list and performing the squares is O of n, and without getting into the technical details of Python's built-in sort function, we know that it is n log n. And so the sorting is the bottleneck of this solution, and it gives us an O of n log n solution. Next up, we have the split and merge solution, and this one is really cool. So I've broken this up into 3 parts, including a little edge case section. So we just check first of all if our nums exist, it has numbers inside, and what we're doing here is we're making sure that there are no negative numbers. This increases the efficiency of our solution because if there are no negatives, then we can just square everything and there's no need to sort them because the question tells us it's already in ascending order. But from the examples, we know there might be some negatives, and in that case, we need to carry out the next three parts. So let's take our split and merge solution over to the whiteboard and break down exactly what's happening. So quickly, we've checked our edge cases. There is a list and the first number is negative. So what we're going to do in the first part is find the index of the first positive number. That's all we're doing. So all we're going to do is iterate through our list and find the first positive. So at this point, we're here in our code. We set m to equal 0. We know that's not the first positive index and we're going to update it. When we enumerate through our list, we get the index and the value at that position. We loop over our entire list and eventually we find a value which is greater than or equal to 0. At that point, we set m to be the index and we break from our for loop. So at this point in our code, we have m which is equal to 2. 2 is this 0 here, 0, 1, 2. So this line might look a bit convoluted, but all that we're doing here is reversing all of the negatives up to 0. And I'm pretty sure you can see why. That is because once we square them, the reverse order of the negative section of our list will then be in ascending order. So this might be an example of poorly written code, and I'd suggest finding your own way to write this. Instead of doing list comprehensions and we're creating two variables in one line and we're doing a for loop in one line, we're reversing in one line, there's a lot going on here and it's not the best example of clean code. So maybe I could have changed that, but it's good to see where you've gone wrong when you go back and look at these questions. But nonetheless, a will be equal to nums from m to the end of our list. We set m equal to 2, so 0, 1, 2. And we're slicing our list from this point on. So we have a new variable called a, which is equal to 0, 3, and 10. And we're looping over our list, cutting it off at 2, not including 2, and we're reversing it, and we're timesing it by -1 to make it positive. This will give us 1 and 4. And similar to part 1, this is O of n because we have one loop in it, and we're performing operations that as the list grows, the operations will grow linearly. And finally, we're on to part 3, squaring and merging. So we're passing in a and b into this merge function here. We set new variables called a and b both equal to 0 and a list ret, which is short for return because that is going to be our list of squared and sorted numbers which you're going to return. And before we get into it, essentially what we're going to do is for each position in the two lists, capital A and capital B, we're going to compare each index in the list to make sure we're increasing in the correct ascending order. So while a is less than length of A and b is less than the length of list B, let's perform some operations. So this is our A pointer and this is our B pointer. And so this is this one here and that's this pointer. And pretty simply, we check is the 8th item, so pointer A, that's one pointer, and the second pointer B. Let's compare them. If A is less than B, so 0 is less than 1, add the item to our list, which we will be returning, and update A to point to the next position. We go back to the beginning of our while loop and repeat this process. 1 is less than 3, so we can add 1 to our list, and let's not forget that we updated A to +1 to it, and then we do the same now that we've added an item from B to our list. So let's update the pointer to be 4, the second position in B's list, which is the first because we're 0 indexing, and then we go back to the top of our while loop, compare the two again. 3 is less than 4, let's add 3 to our list, update the position of A, compare once again, add 4, +1 to B, so B now has a value of 2, which takes us outside of our list. The pointer B is in fact equal to the length of our list B, which was the negative section of our original nums list. So we break out of our while loop and hit this if statement. And essentially what this if else statement does is we add the rest of whichever list we have not finished adding to our return list. In this case, all that's left is the number 10. So all of the items from the current pointer for our list A, let's extend that onto our return list. And if it was A that had gone out of scope for our list, then we would have done the same for B. So by splitting our list, reversing and merging, we have managed to sort our list in O of n time. All that's left to do at this point is the squaring, which is the easy part, and then we can return our list. And there's our answer in O of n time. Super cool way to approach the problem by splitting the list from positive, reversing it, and then merging the two. Finally, let's take a look at the third solution. Our third solution focuses on using these two pointers, except we do it on the list that is passed in, making the solution more efficient. And we call this one absolute and merge. So this third solution takes advantage of the fact that the absolute squared value of a negative or positive number will be the same. And in this solution, we use a deck. So we're going to take a look at Qs later, but if you've watched the data structures video or done some practice, you should be quite familiar with what decks are and how they work. And this solution relies a lot more on the 2 pointers. So we have 2 parts here. We're going to iterate through our list, and then we're going to append. Appending is constant time, and iterating through the list is O of n. So let's create our answer, which we will return. And this is our deck, which I will represent as an empty list for now. We have our left pointer, so I'll call it left to be precise, which we start off at 0, and our right pointer, which is the length of the list minus 1. So here's the same input that we had from the last question. So our length is 5 minus 1 gives us a right pointer of 4. Because again, as always, Python is 0 indexed. So we are here, while left is less than or equal to right. Let's check the absolute values of the 2. And that should immediately let you know what's happening here. We're going to create 2 new variables on the absolute values of those 2 items in our list based off the left and right pointers. So the naming in this solution that I pulled is not great. So I'm going to call this left pointer and right pointer. And let's call it left value and right value. So our left starts off at 0 and our right starts off at 10. And in this answer, A is being passed in as the list, which is a bit different from the last example. So let's not confuse ourselves. Cool. So everything's set in place now. So the absolute value, or the nth item in our list A, the absolute value of minus 4 is 4. Same for the right pointer, that gives us 10. So we've done that, and let's move this now to this conditional statement. Left is greater than right. That's not true. So let's go to the else, and we're going to append to the left side of our double-ended Q the squared value of our right value here. So that gives us 100. And then we're going to reduce our right pointer by 1. Back at the top of our while loop, we check, is left less than or equal to our right pointer? That's true, and the reason we're checking that is because when that's not true, we would have finished iterating over our list, and we will see that in a second. So let's update our left and right values. Our right pointer is now 3, our left value is still 4, and our right value is now 3. If left is greater than right, left value is 4, it is indeed greater than 3. So let's append to the start of our double-ended Q the square of our left value. And now you should definitely be able to see why this solution works so well. By using 2 pointers, we can, in one pass, one single loop, iterate over our array and determine at each step which absolute value is bigger before adding to our answer. This 2-pointer method allows us in one go to avoid sorting our array like we did in the second solution by splitting and merging, reducing the code complexity and number of operations, giving us a more efficient solution. So let's continue with our solution and add one to our left pointer. So we finish in our if statement. Back to the top, this is still true. Now let's compare the next 2 values. Left value is minus 1, but we take the absolute, so it's 1. Is the left value greater than the right? No, it's not. So let's append the squared right value and minus 1 to our right pointer. So now we're comparing our last 2 values. This is still true. We're comparing 0 and minus 1. 1 is greater than 0. So we add the square of that to the start of our double-ended Q, and then we can add 1 to our left pointer. So our left and right pointers are equal now, and that is the importance of the less than or equal in our while loop. And so again, this shows the value of whiteboarding your solutions and thinking about your solution end to end, because something as small as an equal sign in a comparative operator can completely render your solution incorrect, and not just while solving Leetcode questions. This often happens in your job or production code, where something as small as an equal sign or some tiny missing value can completely break your system. But there's usually a lot of testing to make sure nothing goes wrong. Either way, make sure to pay attention to the details. Finally, we check if left is greater than right, which at this point they are both equal to 0. So we hit the else statement, and we can see this else not only covers when the right is greater than the left, but also when they are equal. And then we can append 0 to the start of our double-ended Q, and we can return our answer without forgetting to convert the data type into a list. So there's our solution, which solely relies on 2 pointers. And a quick note on the space complexity, it is bottlenecked on the answer variable where we are storing our sorted squares array and returning that at the end. So if we had a really long input, the answer array we are storing could also be really long, and this is a linear proportion. And you can see for each solution how we slowly improved our code until finally we used the two-pointer approach and came up with a super efficient algorithm. Next up is 3-sum, the successor to 2-sum, and it's a medium question. Easy questions typically have one core concept, whereas medium questions merge two concepts or two easy questions together. So 3-sum builds on 2-sum, and there is a 2-sum part 2 question in between that might help in figuring out the concepts involved for 3-sum. So it might help to solve 2-sum part 2 before giving 3-sum a go. The question tells us, given an integer array nums, return all the triplets nums I, j, and k such that I does not equal j, I does not equal k, and j does not equal k. And the sum of these three numbers should be equal to 0. Notice that the solution set must not include duplicate triplets. Remember, immediately we can always think of our brute force solution as a sort of safety net towards solving the question. So we could have a triple nested loop and search for each answer. Something like this. We start off with the first nested loop, send out a second loop to check each number, and then the third moves along, then the second nested loop moves along, and then we repeat the process moving along in our first nested loop. At each point checking if the sum equals 0. However, this solution would give us n cubed time complexity, which is very slow, and it also has the potential to give us duplicates. Sorting our array will help us overcome the duplicate problem. So I've quickly sorted our array. So our solution looks something like this. I plus j plus k equals 0. And the green arrow indicates our loop that will evaluate all the numbers for the I position before sending out the red arrow in a loop for the j number and the blue arrow in a loop for the k number. And now that we've sorted our array, we know that when we move on to the next number, if this is identical to the previous number, we can skip evaluating this number and move on to the next in our sorted array. So a triplet with the I position of -1, for example, has already been evaluated. Additionally, we know that when the first number is positive, we can stop our solution because we will never have a triplet summing to 0. For example, if we had an extra value in here and our first nested loop began at 0, there's no point continuing. So sorting helps us overcome the duplication part of the problem and optimizes the solution a bit more. We now have a system for safely filling in the first position in our solution. After that, we only need 2 more values to reach a new target, which will be the positive value of whatever I is. So for example, if I was -4, we know the sum of j and k need to be +4 to give us a solution of 0. And now the problem has been reduced to the original 2-sum problem, 2 numbers and 1 target. So we could use the original solution with a hash map. However, now the array is already sorted, we can use 2 pointers to make this solution more efficient. So here's our sorted array, and if we begin by evaluating the first number in our array, -4, we set the left pointer to be the next value in our array and the right pointer at the end of the array. At each point in the algorithm, we check if the sum equals 0. So for this example, -4 minus 1 gives us -5, plus the 3 gives us -2. So we need to increase the value of our triplet because the sum is less than 0. And the only way to do this is by moving the left pointer up. Because of course moving our right pointer down will have decreased the sum even further. We could also have a check to optimize our solution that if it's the same number, we can just move the pointer further up again. So I've added a 1 in here to show you how to get to our solution. So if this question had a solution that included the -4 and 0 and 3 still gives us -1. So we would move the left pointer up again, and there's our solution for I and j plus k. And this method will guarantee we find our solution. There is no way for us to do this 2-pointer adjustment and need to go back on it. For example, we will never need to move the left pointer back down or the right pointer back up, because any previously unexplored combination that could be considered by reversing the pointers would have already been invalid based on our prior calculations of whether the sum was greater than or less than 0. So you can give the code a go yourself. Otherwise, let's walk through the first example now. So here's the code for our solution. The first thing we do is initialize a triplets list, which will be returned at the end and give us our solution. After that, we sort the numbers, and here is the first example from the question. Then we begin a loop over our enumerated sorted array of numbers, and that is this green arrow here. Next up, we have a check. We make sure that the index we're currently evaluating is inside of the range of our array to avoid any errors. And then we make sure that the next number we're evaluating is not the same as the previous number to optimize our solution and avoid any unnecessary operations. After that, we initialize a left and right pointer. The left pointer will be the next index along, and the right pointer will be at the end of our array. And then we begin a while loop. And this is just a conditional check to make sure our left pointer does not cross over our right pointer, because we will have evaluated every option at that point. Then we take the current sum of the three values our pointers are pointing to. So for the first loop, it will give us -4 plus -1 plus 2, which equals -3. Our current sum is less than 0, so we push the left pointer up by 1. We could also include another check at this point to push the left pointer up by 1 if it's the same as the previous value. But nevertheless, our solution will check the current sum, we'll find that it's less than 0 again, and we'll push the left pointer up again. At this point, we have a current sum of -4 plus 0 plus 2, which gives us -2. Left is still less than right in our pointers, so we evaluate the current sum. -2 is still less than 0, and we push left up by 1 again. Our current sum is now -4 plus 1 plus 2, which gives us -1. -1 is less than 0. Push the left pointer up by 1. Left is no longer less than right, so we break out of our while loop and go back to the beginning of our for loop. So we've evaluated all of the options for -4, and we found that no solution exists. I is now 1, and the value of that is -1. We check if -1 is equal to the previous value we just evaluated. It's not, so we can set our left pointer and right pointers back to their starting positions. At this point, our current sum is -1 plus -1 plus 2. That gives us a value of 0. So we finally have a valid triplet, and we hit this else block here. We add to our triplets array that we initialized earlier our valid triplet, which is -1, -1, and 2. And it's important now to keep evaluating for more solutions. And this is exactly what's going to happen. So we push our left pointer up by 1 index on this line, and then in the next line, we do another check to make sure that the left pointer is not equal to the previous left pointer value. Otherwise, we'll be evaluating the same solution. The I was already fixed. This was our green pointer analyzing all solutions for I, which was -1. We then found a solution with a number for j and some number for k. If we push the left pointer up by 1 and we have the same j number, well, this will just give us the same k number and a duplicate triplet. So 0 is not equal to -1. This while loop is false, so we go back to the previous while loop. Left is less than right, and the current sum is now equal to -1 plus 0 plus 2, which gives us a value of 1. At this point, our current sum is greater than 0, so let's -1 from the right pointer to move it down 1 value. Back at the top of our while loop, the current sum is now equal to 0 again, and we found a second solution for a triplet with the same I position of -1. So down in our else block, we're going to add the new triplet to our solutions. We add 1 to the left pointer, but that would give us a left which is equal to right, so this while loop would be false, and the same for the parent while loop. And we go back to our for loop and move along to the next evaluation, which would be -1. So I would be 2, except at this point the value is the same as the previous value we just evaluated, and that's here in line 13. So we continue, which makes us move along one more iteration in our for loop to the 0. And of course, you can see at this point, there are no more solutions. We could also throw in the checks we talked about earlier for being in the positive side of our sorted array. For example, we could check if the left pointer when first initialized is a positive number. In that case, we know there will be no solutions. 0 plus 2 positive numbers will never give us 0. And finally, our time complexity is O of n squared, because we have one main for loop which iterates through the elements in the array once, and we have our 2 pointers which also iterate through the array once. Despite the fact we have 3 nested while loops, as you've seen in the previous 2 pointer questions, our 2 pointers only iterate across the array once. The second while loop simply moves our left pointer up, skipping numbers that would otherwise have been evaluated in the parent while loop. So this makes our solution n squared, because there is effectively only one nested loop. And space is O of n for 2 reasons: the built-in sort function in Python, as well as our storing of the triplets list. And so altogether, there's our solution for 3SUM. Finally, the last question we have in the 2 pointer arrays is the longest mountain. The question says, you may recall that an array is a mountain array if and only if the length of the array is greater than or equal to 3, there exists some index I, 0 indexed, where the I is greater than 0 but less than the length of the array minus 1, such that every number to the left of I in our array is less than that number, and everything to the right of the ith number in our array is also less than that number. Given an integer array R, return the length of the longest subarray, which is a mountain. Return 0 if there is no mountain subarray. So simply put, a mountain can be defined as a sequence of 3 or more elements where there is at least one element or number that acts as the peak. This means the elements before the peak strictly increase and the elements after the peak strictly decrease. And definitely give this a go because it's a lot simpler than the previous question. And since we've gone in this order, it should be easier for you to get the solution. So looking at our solution, the question tells us the array will definitely have at least 3 items. So we don't need to do an edge case check for that. We just need to initialize our return variable. And this return variable will be the maximum mountain range that we found while iterating over our array. So we start with the main loop from index 1, the second item in our array. The reason being is that the item in the loop, the I that we're looking for, is the peak. And for the same reason, we can skip iterating over the last item, because the first and the last items cannot be peaks. Then we have this simple conditional check, which checks if we are at the peak by seeing if the numbers in the array on either side of our current index are smaller than the current number. Then we can send out 2 pointers like a search party. We do this for the left side, making sure we don't go out of bounds beyond the 0th index. And afterwards, we do the same for the right side, making sure we don't go beyond the end of our array. So for example, if we were at this number 7, which is the peak, that gives us our solution of 5, the length of a mountain range of 5, as we can see in the original question. So while left is greater than or equal to 0, and current number that left is pointing to is greater than the next number, move L down once more. So 4 is greater than 0, so we can move the left pointer down one more position in our array. The same is not true when comparing the 0th and the first index, so we stop there. We repeat this for the right side of our mountain, and we find that the right pointer ends at 2, or the 0, 1, 2, 3, 4, 5th index. At that point, we check if the max of the current return variable, which remember keeps hold of our maximum mountain range that we found while iterating over our array. So in our solution, we would have moved the green pointer, which is indicating our main for loop. We would have continuously moved this along and found no peaks until the 7. So at this point, our return variable is still 0. And we compare that against this calculation here. We do right minus left, which gives us the numbers of steps it takes to go from the current item the left pointer is pointing to in our array to the right pointer. And of course, we plus 1 to that to get the actual number of items in this range. So the right pointer is at index 5, the left pointer is at index 1. 5 minus 1 plus 1 gives us 5. That's greater than the current return variable of 0, so our return variable is now 5. We would then continue our original for loop, evaluating the next number to see if it is a peak until we have evaluated all numbers in the array, break from our loop and return the answer. And for this question, there will be no more peaks. Now let's break down the time complexity. Overall, on average, it is O of n, but the absolute worst case is O of n squared. Our topmost for loop is O of n, a single linear pass through all the elements in the array. And if there are multiple peaks evenly distributed throughout the array, each inner loop operation, both left and right, could theoretically cover a significant portion of the array. For example, an array pattern like this, where nearly every second element is a peak, requires the inner loops to be executed continuously to scan the mountain range each time. And of course, it is O of 1 space because we are only keeping track of our return variable and the 2 pointers. A quick note is that there is a slightly more optimized solution, although it does share the same time complexity, where instead of a for loop, we can use a while loop, which allows us to update our current iteration value, this I, or the green arrow that we use to indicate it. What we can do is move the value of this to the end of the mountain range we just evaluated. This will save us a few extra operations of unnecessarily checking the next values after a peak we just found. So I leave this up to you to give it a go, otherwise I'll include the solution in the material. So nice and simple, that's our longest mountain question. Okay, so we've made it to the third and final section of our arrays, where we will be looking at the sliding window pattern. And the concept of a sliding window is super straightforward. We use a typically fixed section or window to traverse over our iterable object like an array or a linked list. For example, a window of 3 items, and we perform some calculation at each step. The window can be dynamic in size, but this will typically be for medium to harder questions. So the first question is contains nearby duplicate. And this is the second part that builds on the first version of this question we answered earlier. And what's cool is I decided to check out my previous submissions, and I see I completed this question on Christmas Day. Really goes to show how much I put into this, and the evidence is all there that if you really do practice and put the time in, then this stuff will become easy and smashing the interview will be a piece of cake, believe me. Anyway, this is a fairly straightforward question, especially given we are looking at sliding windows. If you're unfamiliar with the concept of a sliding window, then feel free to stick with me for the solution and maybe give the others in this section a go. On the left, you'll see I included the raw working out when I first attempted this question. And the question asks us, given an integer array nums and an integer k, return true if there are two distinct indices I and j in the array, such that nums I equals nums j and the absolute difference between the two is less than or equal to k. So we know the difference between these two values must be less than or equal to k, and k gives us the max size of our sliding window. And in my notes, this gave me a solution using a set, but we can also use a dictionary. So I've included the dictionary implementation below, and as always, have a look at both to extend the scope of your problem solving methods. Let's stick with the set solution for now and have a look at it in the whiteboard. The first thing we do is create our scene set to keep track of the items currently in our sliding window of size k. So this is the first example question, and let's create our scene set. Next, we iterate over our enumerated list using a for loop. And at each iteration, we check if the current number num is already in our scene set. If the number is in our scene set, it indicates that there is a duplicate within the range k indices because the set scene only contains elements within the last k indices. And we make sure of this in a second down here. So for the index 0 and the number I, let's add that to our code. I equals 0 and the number will be 1. We check our set, number 1 is not in there, so we can just add it to our set. Then we have a check to maintain our sliding window. The length of set is not greater than k, so we're not going to execute this now. So in the next loop, I equals 1 and the number equals 2. 2 is not in scene, so we can add it to our set. The length of our set is 2, which is not greater than k. One more iteration and we're at index 2 with the number 3. 3 is again not in our set, so we can add it in there. Our scene set length is now 3, which is still not greater than k. One more iteration, we have an I of 3 and a number 1. At this point, the number 1 is in scene, so we found a duplicate within the range k. We can return true and there's our solution. However, if we had another number in here, let's say 4, so the third index would have given us number 4. No duplicate is found, and we need to maintain our sliding window length at 3. So we would have added 4 in this line, scene.add num, which is 4. The length of scene is now 4, which is greater than k. So to maintain our sliding window, we just remove the last item or the oldest item from our scene set, which is nums I minus k. I is 3 minus a k of 3 gives us 0. So the number in the nums array at index 0 is number 1. So scene.remove 0 will check our set for the number 0 and remove it. And that's how we maintain a sliding window of fixed length 3 using a set without relying on the order. So nice and simple solution. As for the complexities, the lookups for a set is constant, O of 1, and there will be a reference chart in the material somewhere for common operation time complexities which you can have a look at. Adding and removing to a set are also constant, except we have one linear iteration, going through all the numbers in the array once, and of course this gives us a linear time complexity. As for the space complexity is O of k. And the reason is that we store a single set which is at most size k, and this is our sliding window. And so that's it for the contains duplicate question part 2. Nice and easy. Minimum absolute difference, and let's get straight into the question here. Given an array of distinct integers r, find all pairs of elements with the minimum absolute difference of any two elements. Return a list of pairs in ascending order with respect to pairs. Each pair a, b follows. A and b are from the array. A is less than B and B minus A is equal to the minimum absolute difference of any two elements in our array. So essentially, we need to return all the unique pairs of numbers with the smallest possible difference in the list in ascending order. Now, you could absolutely brute force this with nested loops and get a solution, but no surprise, we're going to use a faster solution with a sliding window. So pause now if you want to give it a go. So our solution is super clean. We have 3 parts. We sort the array, and this will allow us to evaluate the array in a sliding window, which is 2 elements large, in order to find the pairs. In part 2, we find the minimum absolute difference in one linear iteration. And then in part 3, we have our sliding window, iterate across the array, and if the difference equals our minimum difference, we add it to the answer list. And naturally, this will give us the answer in ascending order as the question asks, because we sorted the array earlier. My original solution had one loop. It still had similar operations, but at each point we would check if the new minimum pair difference in the sliding window for the current pair was less than a pair we previously evaluated by checking the minimum difference and updating it if the new difference was smaller. And while it had the the same time complexity, it was very messy. So it's good to see how you can go back and make your code more readable, and this applies of course to real world code. If you can extract some of the responsibilities of a section of code and modularize it, this will help with debugging, readability, and maintainability. So I've left my original solution for you to have a comparison on how we can extract responsibilities and make our code cleaner, and looking at the two will be a good exercise. So here's the example from the first question, and what we're going to do is sort our array in place using the same array. So here's our new sorted array, and we're going to set the minimum difference initially to be positive infinity. And this is of course because if we set any real number, which is below 10 to the power 6, we have the potential to break our solution. So for I in range 1 to the length of our array, so we begin at the second position in our array, and to find the minimum difference, at each point we compare the current minimum difference to the difference between the current pointer, so the current ith position in our array, and the previous number in the array. So at this point the difference is 1, at this point the difference is 1, and at this point the difference is also 1. And in step 3 we collect all the pairs with the minimum difference and we put them into this result array, which we will return at the end. So we have a new for loop, and in a similar fashion we check if the current minimum difference starting from the second element is equal to our minimum difference. For this question, each pair will give us a minimum difference equal to 1, so we would append 1 and 2 to our list, and then we would move along, append 2 and 3, and move along and append 3 and 4 in that order. The time complexity is of course n log n, the sort function being the bottleneck, and space is O of n worst case, based on Python's built-in sort algorithm, which you can feel free to check out why, and there should be a reference to it in the material. But we are also storing the pairs of the answers in a list, and if every pair is an answer, like in this example, then our result array will be n length, and so there's our minimum pair difference solution. Finally, our last sliding window and our last arrays question, a medium question where we are given an array of positive integers nums and a positive integer target. We are asked to return the minimal length of a subarray whose sum is greater than or equal to the target. And if there is no such subarray, then we return 0. And if you want to give it a go, pause now, or I can give you a hint and tell you that our solution will implement a sliding window using 2 pointers. Another example of how medium questions merge 2 concepts or 2 easy questions together. So let's take a look at the solution. And you can see we don't have that many lines of code, so it really does come to just understanding a few core concepts like we saw in the graphs question. We start off by initializing some variables. We set our minimum length to positive infinity. The reason being is that later we will compare if there is a new minimum value against this current min length value. Setting the minimum value to anything above the constraint of 10 to the power 9 would have worked just fine, but we can initialize our value to positive infinity to be safe. We also initialize a left pointer at 0 and the total or the current sum, which is the sum total of the values in the current sliding window. So there's our left pointer, there's our total, and let's add our minimum value. So we've initialized this left pointer at index 0. We then begin a for loop where the loop index represents our right pointer. So let's add that in. Our right pointer begins at 0, and we continue to increase our right pointer to expand the window until we meet our target condition, and that is this while loop. So on the first iteration of our while loop, the total value will be 2. The total is not greater than or equal to our target yet, so we move right up again. We add 3, the total will be 5. We do this again, the total will be 6, and we do this once more, and our total becomes 8. At this point, we enter into our while loop, because the total, 8, is greater than the target, 7. And we update the variable which we will return, indicating our minimum size subarray. Right, so comparing the minimum of infinity against r minus l plus 1, which gives us the number of items in our minimum subarray. Our right pointer is at the third index, our left pointer is at index 0, so 3 minus 0 plus 1 gives us 4 items in our minimum subarray. So let's update our return variable to be the number 4. At this point, we begin moving the left pointer up, so we begin decreasing our sliding window. And the reason being is that we might be able to find a smaller subarray which hits the target value by moving our left pointer along. So we move it to the second item in our list, and we find that the total is now 6. So our total has now dropped below our target, and we can continue moving our right pointer along. At this point, we have a total of 10, except the minimum subarray is the same as the current minimum subarray, so we don't need to update it, and we can move our left pointer up. And you can see now that a big jump, for example from 2 to 4, gives us more room on the left pointer side to decrease the minimum size subarray, which is exactly what's just happened, because we have a total value now of 7 with 3 items in our subarray. And we would continue to repeat this process until we came towards the end of our array and we found a minimum subarray of size 2. And so we break out of our for loop and we check at this point if there was any minimum size subarray that sums to the target or greater than the target. So we check if it's positive infinity. In this case, we would not have updated our return variable. We return 0 as the question tells us. Otherwise, we return the minimum size subarray. And one thing to point out here is that it may look like a typical two-pointer solution, but the sliding window concept comes from how the 2 pointers slide across the array and maintain the window of elements that meet certain conditions. As long as the sum of elements within the window is less than the target, we continue moving that window along, making it shorter or smaller. And so this process continues, effectively sliding the window over the array to maintain the minimum size subarray that satisfies the condition. And there are no hard boundaries on what makes something sliding window or 2 pointers. These are just abstract problem-solving patterns that are meant to help you think about a solution. And that's why a lot of the solutions in this problem will call it a sliding window. And as for the time complexity of this solution, it's O of n. You might think it's quadratic due to the nested loops, but this is not the case. As you've seen in the previous 2-pointer questions, the left and right pointers are traversing the array in one pass, and they are independent of each other. Increasing the input size will not disproportionately affect our operations. The left and right pointer will proportionally increase their operations. This while loop will not quadratically increase our operations. Instead, as we've seen before, moving the left pointer up is not a compounding effect. So our solution would be O of 2n, 2 times n, because the left and right pointers are each iterating over our array in one pass independently. And our 2 times n solution boils down to O of n. As for the space, it's of course constant because we're only keeping track of a few variables unaffected by the input size. This question also offers a follow-up asking us to get the solution in n log n, which is a worse time complexity, but it's definitely a useful exercise, and the technique is based on prefix sums and binary search. In my opinion, this is overkill right now and definitely wouldn't be judged in an interview if you don't know the techniques I just mentioned, but it's definitely interesting to see how it works, and if you can understand it, you know you're doing well. So that's it for our minimum size subarray sum question and the array section in our Leetcode. Next up, we have a section on bit manipulation, and while this may seem like a low-level computing concept, may be irrelevant to you if you're going for a software role or web development, this was actually one of the questions I faced in my software interview. So let's understand bit manipulation before looking at the question. If you have the material, you will have looked at the essential core computer science and programming concepts provided, which includes detailed walkthroughs on bits and lower-level mechanisms. Otherwise, a quick reminder without getting into the entire concept space. Bit, short for binary digit, the most basic unit of information in computing, a 1 or a 0. And an operator is some symbol or keyword that instructs some mathematical computation or actions. For example, x plus y equals z, where x and y are the operands, the plus and the equals are operators, and of course we have our result z. We can also have different types of operators. The plus is an arithmetic operator, and if we were programming and we wanted to assign the value of x plus y to z, then the equal sign would be an assignment operator. A bitwise operator is simply another type of operator, where the defining characteristic is that it performs actions on the bit level. And here is a list of bitwise operators. The first few somewhat similar to logical operators, another type of operator. So that should set us up perfectly for the following question. Where given a non-empty array of integers nums, every element appears twice except for one. Find that single one. You must implement a solution with a linear time complexity and use only constant extra space. So I have 2 slides for this question here, and the first one we will be looking at other solutions. You should be an expert by now in knowing that we can always brute force our solution, except for this type of question it will give us n squared complexity, and the question wants us to try achieve this in a linear runtime. We could also sort our array and check the neighbor index at each position to check if it is a duplicate. Of course, the sorting will give us n log n, so still not good enough. We could also use a hash map, very similar to what we did in the 2-sum question. We would iterate through our array, store the elements, and check if we found them again while the iteration continues. This gives us a linear time complexity, but we're storing our hash map, so that gives us O of n space complexity, which is still not good enough. And that leaves us with bit manipulation. And you'll find bit manipulation is very popular in competitive programming because it's so efficient. And specifically, we're using the exclusive or bitwise operation, giving us linear runtime and constant space. This exclusive OR operation is the key to solving this problem, and let's see why. Here is an array of numbers from the question's first example, and here is their values represented as bits. What exclusive OR does is it returns a 0 if both bits are the same, otherwise it returns a 1. as we saw explained in our table on the right and shown for the bits on the left. So we can use this up arrow to represent our exclusive OR. So 1 exclusive OR 1, both bits are the same, and that gives us 0. Pretty simple so far. In that case, doing the exclusive OR on the number 1 in our array against this number 1 will also give us 0. Of course, the bits are also identical, and that's why we would get 0. In that case, the same goes for the 2's. They are also identical, and they would also give us an exclusive OR value of 0. And altogether, we'll be left with our 4, the only item in our array which does not have a duplicate. Furthermore, this solution also works because we can do it in any order. Let's see why by taking a look at the specific columns and the single bits per number in our array. So if we were to perform exclusive OR on the first 2 values in the array, and continue doing this, iterating across our array. Well, the first 2 values, 0 and 1, that gives us 1, because they are different. Doing an exclusive OR of the 1 against this 0, that would also give us 1. 1 against 1 would give us 0, and 0 against 0 would give us 0. So this final value is the same as the first that we had. Let's check again for the second column. 0 against 0, that would give us 0 because they are the same. Doing an exclusive OR of this 0 against the 1, that would give us 1 because they are different. The 1 against the 0 in the second column would give us 1 again, and 1 against the final 1 would give us 0. That's also the same as the second column bit for our single number which does not have a duplicate in our array. And finally, I'm sure you can guess it, but the final column will be the same also. 1 against 0 would give us 1, 1 against 0 would give us 1, 1 against 0, 1, 1 exclusive OR against 0, we have 1, which is the same as our first bit that we started with. So overall, we'll be left with the bit value of the only number in our array which does not have a duplicate. On a macro scale, n exclusive OR against 0 gives us n. All the duplicates in the array will result in 0 because they are the same, leaving us with the only number without a duplicate, which is our n. And I don't think we need to go through the code because it's exactly the same as the intuition. We simply iterate over the array and we perform the exclusive OR operation using the up arrow in place on a single variable, changing its value based on current value in our nums array that we are evaluating. And you can see on the right here what the values printed out will give us as the bits of the return variable we initialized continue to change along the array, finally leaving us with the 4, our single number which does not have a duplicate. So there's one question on bit manipulation. Very good to get some awareness of what bit manipulation is and how it works. A much lower level concept than we've dealt with so far. And like I said, this was one of the questions I faced in my software engineering interview. And in fact, I was not afraid to tell the interviewer that I had seen it before. I think it's good to be honest, and I would suggest you do the same. I would be skeptical if someone can come up with this solution never having seen it before. And it also shows that you've put in a lot of practice. Anyway, that's it for bit manipulation. Next up, we have a section on dynamic programming, a technique used to solve complex problems by breaking them down into simpler subproblems. It works by solving each subproblem only once, storing the solution to that subproblem so that when the solution is needed again, it can be looked up instead of computing the answer to that subproblem all over again. This approach helps save time and computational effort. And a quick note that the term memoization refers to the storing of our results from these function calls and subproblems in some data structure so that later we can reuse them. So we have a few dynamic programming questions in this section, and we're going to start with a medium, so hopefully you'll be able to complete the easier questions before going straight to our solution. In the coin change problem, we are given an array of coins representing coins of different denominations and an integer amount representing a total amount of money. So here are our coins, and the amount we want to reach is 11. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So before diving straight into our dynamic programming solution, I'm going to try work our way up to it. We could try a greedy algorithm, like we've seen before in the best time to buy and sell stock question. Our greedy algorithm could be to continuously use the biggest coins we can find at each stage while remaining below our target. 5 is the first biggest coin we can take and remain below our target. So that gives us a current value of 5. We can't use 5 or 4 or 3 because we'll be above our target for the next coin. So the next biggest we can take is 1, giving us a value of 6. And if we repeat that process, we can only use the 1 coin again, and that gives us a value of 7, which is our target, and we used 5 once and the coin 1 twice, and overall we used 3 coins. Except we know this is not the right answer. Using the 3 and the 4 coin is only 2 coins, and that gives us a target of 7. So trying to go for the best choice at each stage by going for the biggest coin will not work. We need to evaluate all the solutions, and we can do this with depth first search, which will lead us nicely into the dynamic programming solution. So here's the first example from the question. We have a target of 11. So we could use the 1 or the 2 or the 5 coin, and seeing as we're going for depth first search, we're going to use every coin. Bear in mind, we could also use breadth first search. That's not the point of this solution. At this stage, we're simply trying to convey that we're using every coin to find every possible solution. So if I was doing depth first search, I would use the coin 5, and that would give me a value of 6. Then maybe I would use 5 again. That would give me a value of 1. And at this stage, I can't use the 2 or the 5 because that would take me below the target, so I use the 1, and that gets us to 0, and there's one solution. Let's now look at this in a breadth first search and try all the other coins before moving on to the lower levels. So if I was to use 2 and 1, I would end up with targets 9 and 10. And at the point of this 6, I could have also used a 2, and I could have also used a 1. So this is about to get very messy, but bear with me. So at this point, we have a value left of 5. At this point, we have a value left of 4. When I first used the 2 coin, I could now use a 5. I could use a 2, and I could have used a 1. At this point, I'll be left with 4. At this point, I'll be left with 7. And at this point, I'll be left with 8. A 2, a 5, or another 1 coin, giving us 9, 5, and 8. And let's go one more level down before taking a step back. 1, a 2, or a 5. So we started at 11, and at each stage we're testing every coin we can possibly use before ending up at 0 or going negative and realizing we can't use this combination of coins. Eventually we will evaluate every combination and find our minimum amount of coins to reach our target. Except this is of course very inefficient. We end up with the same subproblem repeated over and over, which is leading us to unnecessary repetitions. At this point we have the target 8 that we need to evaluate all combination of coins. We also had to evaluate the 8 target here after using the 1 and the 2 coin. The same subproblem reappears when the target 4 comes up, and the same for the 9s and the value 7. And we see this again and again with the 5 and the 6s. And remember what I first defined dynamic programming as. Dynamic programming is a computer programming technique where an algorithmic problem is first broken down into subproblems. The results are saved and then reused to find a solution efficiently. In this search solution, we approach the algorithm top down, but let's now turn the problem on its head and start from the bottom. So what does this mean? What we're going to do is start with the smallest target possible, 0, 1, 2, 3, all the way up to 11, and check the minimum number of coins for each target along the way. This will help us avoid repeating the calculations for each subproblem that we see reappearing. And that will come to life in the form of this array. And what I'm going to do is put the code alongside the intuition because they are identical. So this blue arrow is going to represent where we are in the code. And the first thing we do is create this array up to the length of the target value, plus 1 because we are 0 indexing. The value of each position is the minimum number of coins we need to get to the target, which is our index of the array. At this point our target is 0, at this point our target is 1, all the way up to our target of 11, which is the answer we are looking for. And eventually each box is going to contain the minimum number of coins we need to reach the current target, which is the index. And for all of the subproblems, we pre-fill the value with some arbitrarily large value like we have done before with the positive infinity, but in this case we can simply add 1 to the target, and you'll see why this works in a second. And then in the next line we can set the index of 0 to have a value of 0 because of course we need 0 coins to reach the target of 0. And the question tells us this in example 3. Then we begin the bulk of our work with the for loop across the array, starting from the second position up to our target. Inside, we iterate across our coins. So let's track this with our green arrow. And inside our for loop, we're going to have a nested for loop to iterate over our coins. The reason being is that we have to check every solution to find the minimum number of coins. There is no getting around this. Then we have a simple check to skip evaluating the current coin if using that coin takes us below the current subproblem target. That's just common sense. And finally, here is the important part. We set the minimum number of coins, that's what the value inside the array represents, to be the minimum of the current number of coins versus 1 plus dpi minus c. Let's break down the minimum comparison's second value. 1 plus dpi minus c. 1 is the current coin we are evaluating, and we are adding to that the value of the dpi minus c index. I is the current subproblem target, and c is the current coin's value. So what we are doing is checking. If we are using the current coin to reduce our target I, we will then get some new value, some new subproblem target. For example, in the top-down problem, we use the value 5, and then we have a new subproblem target of 6. 6. And at that point, we check what is the best possible solution, which we would have already evaluated previously in our array because we are going bottom up. So this will definitely make more sense as we work through the solution. So for C in coins, we are looking at coin number 1 for the index I of 1. So let's keep track of that also. Index of 1 and the current coin is 1, which is this red arrow. 1 minus 1 is greater than or equal to 0. So we can use it to get to our target. At that point, we compare what is the current minimum value. Well, we pre-filled it to 12. And this is why I said earlier that adding 1 to the target will work just fine, because we're comparing 12 against 1 plus dp I minus c, 1 minus 1, dp of 0. Well, that's 0 because we need 0 coins to get to 0, which will indicate that we've reached our target. So 1 plus 0, the minimum between 12 and 1 gives us 1. Next, we iterate to the next coin, which is 2. 1 minus 2 is less than 0, so we can't make this comparison, and the same goes for 5. So we go back to the top of our first for loop and go to the next subproblem. At this point, I equals 2, and we go back to evaluating the first coin. 2 minus 1 is greater than 0, and we have a new comparison to make. So we're using our first coin, which is 1, so we're adding 1 to the combination of coins to get to our subproblem target of 2. And I minus c, well, 2 minus 1 gives us 1. So using our coin 1 to get to the target of 2, leaves us with a subtarget of 1. I2 minus 1 C leaves us with a target of 1. So we've already solved the minimum number of coins we need to reach our target of 1. So we're looking back and we're using that value. We know that it's 1 coin. So using 1 plus the value which we previously calculated, 1 plus 1 gives us 2. 2 is less than 12, so we have a new minimum value. Great. At this point, we go back to the top of our second for loop and check out the next coin. 2 minus 2 is indeed equal to 0, so we can go to our minimum check. We are now comparing 2, which is the current minimum value, against our dp of I minus c. 2 minus 2 gives us 0, and so we have a value of 1 and a new minimum value of coins to reach our sub-target of 2. And we can't evaluate 5 because that will give us a value below 0. So I've filled in some of the values, and now let's look at a bigger sub-problem to make this more interesting. We start off with coin 1. That gives us a value of I minus c, which is 6, 7 minus 1. That's okay, so let's do a comparison of the current minimum number, which is 12, against our dp of I minus c, which is 7 minus 1, or 6. 1 plus the dp of 6, which we calculated earlier to be 2. 1 plus 2 gives us 3. And we have a new minimum value. And we knew at 6 the minimum coins were 2 because we calculated that earlier in the same way, and we figured out that the 5 and the 1 coin were the minimum number of coins we could use. We then iterate over to the 2 coin. 7 minus 2 is 5, and we have a new comparison of 1 plus our dp of 7 minus 2, which is 5. And at 5, we figured out we only need 1 coin, which is the 5 coin. 1 plus 1 is 2. And we're in fact comparing this against the value we just calculated, which is 3. So we have a new minimum value. Let's iterate across again. So we're now looking at the 5 coin. 7 minus 5 gives us 2, and we have a new comparison. 1 plus dp of 7 minus 5, which gives us 2. So we're using the 5 coin once, and the number of coins we needed to get to the subproblem target of 2. Earlier, we figured out that was 1, and we went through this. We only need the 2 coin. And we're doing this comparison against the current minimum value, which is 2. So we don't need to update this. We've gone through all the coins, and we repeat this process for the subproblem of 8. Through the same method, we'll get the minimum number of coins we need to get 8, 9, and 10, and eventually we reach 11, which is our target. For the first coin, 11 minus 1 is greater than 0, so let's make our new comparison. 1 plus a dp of 10. At 10, we figured out we need 2 coins, which is the 5 and the 5. So at 10, we used the 5 coin, we looked at the 5 subproblem, and at this point we only needed 1 coin, which was also the 5, to take us to 0. So at 10, we only need 2 coins, plus the 1 coin we are looking at now, and that gives us a minimum number of 3 coins, and a new minimum number of coins for our target 11, which is 3. We then iterate across to the next coin, which is 2. 11 minus 2 gives us 9, and we have a new comparison. 1 plus a dp of 9, which is 3. 1 plus 3 would give us 4, which is not greater than the current value. So then we can iterate across to the 5, our last value that we need to calculate. 11 minus 5, that gives us 6, and we have a new comparison. 1 plus the dp of 6. Well, at 6, we calculated we only need 2 coins. 1 plus 2 gives us 3. And we don't need to update our value of 3, and we've come to our solution, which is the minimum number of coins we need to get to 11, 3. Finally, if the number of coins at our target is not equal to the target plus 1, which is what we initialized all the values to be at 12, then we can return the minimum number of coins, otherwise there is no solution, and we can return -1 like the question asks us to. Our time complexity is O of n times c. We have one iteration going across all the values in our array, and at each point we're iterating across all of the coins. These are our two nested loops, giving us a time complexity of O of n times c. Similar to n squared, but not quite the same. Still quadratic time though. And of course we have a space O of n, which is our array of all of the values up to our target 11. And that's coin change, the first question in our dynamic programming section. Next, we have the climbing stairs problem. Pause and give it a go now that you've seen the concept and coded implementation of the dynamic programming approach. You are climbing a staircase, it takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? So if we had a length of 2 steps, we can either get there by taking 2 steps or 1 step twice. And for 3 steps, we can either take 3 single steps, we can take 1 step and then 2 steps in one go, or we can take 2 steps in one go and then 1 step. And here is our visualization of the problem for 4 steps in our staircase. And I'm going to show you the code above. Similar to the previous question, we create an array and we're naming it dynamic programming DP. We set the index of 0 to be 0 because it takes 0 steps to reach a position of 0. And to reach our first step, we can only take 1 step. So the value for our target of 1 is going to be 1 step. Now for our target of 2, we're evaluating all the ways we can reach that second staircase. Now remember, we can either take 2 steps in one go, and that's one way to reach our second step, or we can take 1 step twice. So that's another way. 1 plus 1 gives us 2 different ways to reach our position of 2. And these 3 targets are always going to be the same. No matter what our staircase length is, positions 0, 1 and 2 are always going to have 0, 1 and 2 unique solutions. Now the important part is we create our for loop, starting at the 3rd index. And the way we calculate the number of unique steps at index 3, which is our current I, is by taking the solution to the previous subproblem plus the one 2 positions before it. Why is that? Well, for any number inside the for loop, we can either reach it with 1 or 2 steps. So we can either jump from 1 straight to 3, or we can reach 3 by taking 1 step from 2. That's the only way to reach any staircase. Now you might be wondering, well, we could go from 1 to 2 to 3, except this step here has already been factored in when we calculated the subproblem of the staircase 2. We can just get the second step from taking 1 step from 2. So to calculate our solution for 3, we simply take the sum of the last 2 values. That gives us the total number of unique solutions, which is 3. On the next iteration, we simply do the same thing. 2 plus 3 is the number of unique solutions we can get to reach 4. That's either 1 step from 3 or 2 steps from 2. All the other steps have already been factored in, and that's the whole concept of dynamic programming. We're calculating all of the subproblems and reusing the solution. So 2 plus 3 gives us a solution of 5, and we would simply keep doing this for all of the values up until our target, no matter what the value is. And finally, at the end, we return the value 5. So a super simple solution to a nice problem. As for the time complexity, we have O of n, since we have this for loop. And the space complexity is O of n because we're storing this DP list here. Alternatively, we could have a constant space solution. Because if you've noticed, we only need to keep track of the 2 variables inside our orange box to be able to calculate the value of the next step in our staircase. So for example, we could start off with these 2 variables. To calculate our value for 3, make the first variable the value of the second variable, and make the second value the sum of the 2 variables before changing the first variable. To get to our value of 4, just repeat the same process and get our new value of 5. And we would simply repeat this until we reach our target. And so that's it for climbing stairs. Our second medium question inside dynamic programming is max subarray. We are told, given an integer array nums, find the subarray with the largest sum and return its sum. And they give us a definition of what the subarray means. Essentially just a continuous set of numbers inside our array, which is non-empty. And this is a medium question, but given what we've gone through so far, it's not that difficult. So definitely give this one a go if you can. Otherwise, let's look at the solution. So this one here, we can definitely solve with brute force. And initially I was drawn to some kind of sliding window solution. And given what I've said before, these are just problem solving techniques, so they can blend together. But given the way this works out, I put it in the dynamic programming section. And the reason is, at each stage, we're solving a subproblem. Specifically, at each point of the array, we're solving what is the largest sum. And this this simply comes down to looking at the max of the current value versus the max of the previous value inside our DP list. And the previous value will of course be the solution to the same problem. So ignore this second solution for now, and let's look at our classic solution where we create our DP list. For the 0th index, we only have the value -2. So that is the largest sum subarray we can find. When we move across to the next index, the largest sum is going to be the current value or the current value plus the sum of the previous subarray. At this point, 1 is greater than 1 plus -2. And then we move along, and in blue you can see we've made some changes. When we're evaluating -3, the largest value is either -3 or -3 plus the previous index. -3 plus 1 gives us -2. So we've taken into account a previous subarray, and at this point our largest subarray is this one value here. Moving on to 4, of course 4 is going to be larger than -2, and there's no need to include the previous subarray value. So we have a new max subarray which gives us a value of 4. On the left here you can see adding -1 will decrease the value, except at that position in our array, -1 is better off including the previous 4. 4 is still our max subarray, except we update this value in case at the next point in our index, we would be better off by including the 4. And that can only be done by updating the next index, which is the -1 and including that 4 to make it 3. And this is exactly what happens. When we're evaluating this 2, the max value we can get is either 2 or we can include the 3, the previous index. So 2 plus 3 gives us 5 and a new max subarray sum. And we get that by including the 4, unfortunately the -1, but this helps us because we can now include the 2 and get a value of 5 which is greater than 4. And we continue this way until we find our max value which is 6, and we return that 6. Of course, this is O of n time because we are doing a for loop and iterating over each item in our array. And if you looked at the previous climbing stairs question, you'll see that in these dynamic programming questions, it's not always necessary for us to keep this list and have O of n space. On the right is the solution where we only keep track of 2 variables, our max sum and the current sum. So instead of keeping track of the max sum at each point in our list, we're just doing a similar maximum comparison and then storing that max sum in a single variable, giving us constant space. So feel free to go through this constant space solution line by line, but it's pretty intuitive, so I'll leave it there for the max subarray question. So back to the lower level hardcore computer science foundations, counting bits. And let's get straight to it. If you haven't yet familiarized yourself with bits, let's take a closer look than the previous bit manipulation question. In front of you is a table comparing the numbers in our base 10 system versus the bit system on the left. Each column represents a value which is derived from 2 to the power of some number, which is a single digit linear increase. So 2 to the power 0, which is 1, 2 to the power 1 equals 2, 2 to the power 2 is 4, 2 to the power 3 is 8, and so on. For the number 0, we have 0 bits. Simple. For the number 1, we have a single bit in the first column, the 2 to the power 0 column, giving us a total value of 1. For the number 2, we need a single bit in the 2 to the power 1 column, giving us a value of 2. So we have shifted columns now. And for the number 3, we need a bit in the 2 to the power 1 column and in the 2 to the power 0 column, giving us 2 plus 1, which is equal to 3. And last one, let's look at 4, where we shift columns again because we need a bit in the 2 to the power 2 column, giving us a value of 4. Now, if we take a step back, the value of 2 in bits looks like 10 to us, and the value of 4 looks like the number 100 to us. Well, this is because bits use a base 2 number system, and we use a base 10 system. So for us, each column would be 10 to the power of some value. So this would be 10 to the power 0, this would be 10 to the power 1, this would be 10 to the power 2, and so on. This would give us 1 in the first column, 10 in the second column, and 100 in the third column. So if we wanted the number 2, well, we can't move to the next column because this has a value of 10. So we would need a 2 in the first column. And we are allowed to use the number 2 or 3, 4, 5, 6, 7, 8 or 9 because these 10 digits are part of the system. It is a base 10 system. So the number 615, for example, would have a 6 in the hundreds column, a 1 in the tens column, and a 5 in the ones column. So that should give us a solid understanding of bits and the base 2 system. Let's now look at the question. Here we have the numbers 0 to 8 with their bit representations, or in other words, the base 10 value on the left and the base 2 value on the right. On the left, let's highlight the significant bit values. These were the values of each of the columns in our base 2 system. So for each one of these numbers, they are the value of 2 to the power of some x. So for the first one, x is to the power 0, x is to the power 1, x to the power 2 gives us 4, and x to the power 3 gives us 8. This will come in handy later. For the first 4 numbers, let's quickly jot down the number of ones inside the bit value. This is what the question wants us to find. So here we have 0 ones, here we have 1, and here we have 1. And you'll notice the columns begin to shift at each significant bit. For example, at 1, we had a 1 in the first column. At 2, the column shifted again, and we had a 1 in the second column. At 4, the column shifted again, and at 8, the column shifted to add a 1 in this fourth column here, similar to what we saw in the table above. If we look a little bit closer, every time the column shifts, the previous bit values repeat. So when the column shifted for the 4, the first 2 bits look like a repeat of the 0. For the 5, we still had the extra 1 in the third column, but this 0 and 1 looks like a repeat of the number 1. For the 6, we still have 1 extra bit in the third column, except the first 2 bits look like a repeat of the number 2, and the same goes for 7. And it looks like when we reach 8, this is similar to the 4, which was similar to the 0. And this is the same in the base 10 system. When we go from 10 to 11 to 12 to 13, this is just the same as 0, 1, 2, 3, except now we have an extra 1 in the tens column. So the value of whiteboarding wins again. We are beginning to notice a repeating pattern. So the pattern we're beginning to notice here is that every time we reach a number which is equal to 2 to the power of some digit, we have an extra bit value in a new column. For example, the 1 in the third column for 4 to 7, or the 1 in the fourth column for 8. And we plus to that the number of ones in a previous value. So for example, for 8, we had 1 in the extra column plus the value of ones in 0. For the number 7, it's this extra 1 in the third column plus the value of ones in the 3. For 6, it was 1 in the extra column plus the value of ones in the 2. So we're beginning to notice a pattern. Let's check number 4, for example. We said this was 1 in the extra column plus the value of ones in the number 0. So pretty similar to our 8 example. And we can connect these because they are power of 2s. So things are beginning to add up here. The numbers 2 and 3, we have a 1 in the extra column, and the bits in the first column repeat. So we have this extra 1, and we have 0 and 1, 0 and 1. And we can also do the same for the number 1. It's simply 1 extra value in the very first column. And we can check this by looking at our table again. Here we go for the number 1. We have 1 in the very first column and the same number of 1s as the number 0. For the number 2, we have a 1 in the second column and the same number of 1s as the number 0. So we've noticed some connection on the shifting columns, which is connected to the most significant bit, which is our 2 to the power of some number. And we know exactly why. If we wanted to reach the number 6 from the number 2, for example, we would simply add a 1 in the third column to increase the value by 4, or the 2 to the power 2 column. So when we look back, we are offsetting only by the current most significant bit, which for the number 6 is 4. And in the base 10 system, for example, if we wanted to go from 5 to 15, we would just add a 1 in the tens column. It's the same concept. Great, that's step 1. The next step is to generalize our solution. And if I change the wording of our solution to be more programmatic, let's say we had this value of 1s in some previous number by checking a list we create, and if I call this list dp, then this value of 1s in 3 can become the dp of 3. And this value of 1s in 2 can become the dp of 2. And let's quickly change the rest to follow this pattern. Okay, so we're getting closer, but we're not quite there yet. We need to generalize even further to get to our programming solution. And one thing I've noticed by looking at the 4 is that this previous lookup value is increasing digit by digit linearly. 0, 1, 2, 3, until we go back to 8, which is 0. At the power of 2 value, we have 0. We're looking up the bits in the 0 number. So we can change these values to be I, representing the current index that we are on, minus the most significant bit. And you'll see right now how this works. So we can take I to be the current index that we're on, which is the value 4, and we minus from it the most significant bit. So in this case, we're minusing 4 to get to our 0. Again, 5 minus 4 gives us the number of bits in the number 1, which is exactly what we're looking for. And then we're adding to that 1, which is the extra column that we have for the number 5. So let's quickly change all of these to match this new pattern. Great, so we are a lot closer to our final solution. Everything is looking a lot more generalized now, and we've gone through the intuition to understand why. Except there's one more thing. If we are writing our code, we don't know what the offset is. We're not looking at this table. So we have this offset, which is necessary to tell us which subproblem to check for our solution to the current number. We just said this offset is always 2 to the power of some number x. Well, this x is also going to increase in a single digit linear fashion from 0 to 1 to 2 to 3. And so there's our generalization. And if we look at the code, this will make a lot more sense. Here's the code, and we're creating this DP array like we've done so far in our previous dynamic programming questions. We give it a length of n plus 1 to account for the 0 number. And then we begin with our offset of 1. which is the first of our 2 to the power x. And then we begin our for loop, skipping the 0 because we know that has 0 ones inside. And let's ignore this if check for a second. dp of I, which is the current number we're on in our for loop, dp of 1 equals 1 plus the dp of 1 minus 1. Exactly what we had on our whiteboard. That gives us a value of 1. Now on the next loop, we have to check if the offset times 2 is equal to our current I. And this works perfectly, because whenever this is true, we will have hit a new 2 to the power of some x. So on our next loop, we check if the offset, which is 1, times 2 is equal to our current I. Our index is 2, and this will be our most significant bit and the offset we are looking for. And the same will be true for the index value of 4 and so on. So we iterate across our array, updating the offset and looking backwards for the previous values we solved at each stage before finally returning our array list as asked, completing our bottom-up dynamic approach to the counting bits question. And of course, I'm sure you're becoming experts at this now. The runtime is O of n. We have one single iteration across our array and some operations which will grow linearly as the input grows, and a space of n due to our DP list. So that's it for counting bits. Our last dynamic programming question, range sum query immutable, and this is a different type of question than we've seen so far in terms of input, because we have a class with 2 functions to write. We are given an array of numbers and we want to handle some queries, which is just asking for a sum between 2 indices in our array. For example, the sum from index 0 to 3. So my first solution here on the right is of course a very simple way to approach the question. Simply initialize the list as asked with no modifications in the first init function and use every left and right pointer on the go to calculate the sum as asked. This would be O of n every time it's run. However, we can improve this. As you can see in my notes, 2 algorithms can have the same complexity but different runtimes. So if we were to improve this, we could instead calculate the prefix sums. And by prefix, we just mean any subarray starting from index 0. So we could create an array in O of n time by calculating the prefix sums. So when given a query, our left and right indices, we would simply take the right index value away from the left index value, except we would go one left index value along. Let's create our prefix sums array and look at an example. So here is our array, and you can see at every position we have taken the sum up until that position. -2 plus 0 gives us -2, plus 3 gives us 1, plus -5 gives us -4, and so on. And when the question passes in this array of 2 numbers, our left and right pointers, for example, let's take 2 and 5. So the sum from 2 to 5 is -1. And if you were to do that by looking at our sums, we would simply take the value at the 5th index, which represents the sum from index 0 all the way up until the 5th index, and we would remove the prefix sum that we are not interested in. Since we are only looking at index 2 to index 5, we can remove these 2 numbers here. And we do this by taking the value at the 5th index, -3, and minusing from it the sum from the previous position up until the index we want. So if we're looking at 5 to 2, we minus the 5th index value from the 1st index value. -3 minus -2 gives us -1. But we do have an edge case. For example, if we wanted to calculate the sum from index 0 to index 2, well, we can't look at the next index along from 0. So we can fix this in the code. We could add an if check for this edge case, or we could take a different approach. We could just initialize the array with one extra value in the 0 index, and so we no longer need to check the next index along from the left pointer, but the next index from the right pointer. So instead, our prefix sums array would look like this. And for the same example, we would take the next index along from the right pointer and minus from it the left pointer that we are given. -3 minus -2 gives us -1. And carrying out this modification in the initialization of our class is O of n. Of course, because we are iterating over each number in the array and creating our sum. However, this is an improvement on the last solution because we only carry out this O of n operation one time. After that, every query is constant. We are just looking up 2 values and performing a quick operation. And you can definitely see a big time improvement between these 2 solutions. And this might look quite different from the previous dynamic programming questions we've seen so far. However, a lot of the solutions will tag this as dynamic programming because in a sense, we are looking back and reusing values from a previous subproblem or calculation that we had. And so that's it for our range sum query question and dynamic programming section. Next up, we have backtracking questions. Backtracking is an algorithmic technique where we try to solve a problem by building a solution incrementally, finding different paths, and if one does not work, we backtrack and try another path until we find the right one that satisfies our problem constraints. Think of problems like Sudoku. We can keep trying different numbers in the positions, and if we reach a dead end, we backtrack, change the first number and try again. and backtracking is one of the more difficult Leetcode question sections. All the problems here are medium, a lot less likely you'll get one of these in an interview, but still possible. If you are working fast or have an interview soon, of all the sections I'd recommend covering this last or skipping this entirely. However, if you are just starting out, this will definitely improve your programming skills. And there are two core concepts in this section: permutations and combinations. Both refer to selecting items from some set of data. Permutation is referring to the ordering or arranging the data in a different type of way, and combinations is referring to the different selections of data from that dataset. And as you can see from the table, the order of the items in permutations is important, but not for combinations. So the first question is letter case permutation, where we are given a string S and we can transform the casing of every letter individually to create another string. And we are told to return a list of all possible strings we could create and return the output in any order. Of course, the order within each string matters. So in the first example, we are keeping the order exactly the same throughout, and every time we have an alphabetical letter, we are creating two new permutations of the lower and uppercase versions of these letters. We have two possible ways of attacking this question. We can take the iterative approach and build out a solution incrementally, or we can do the similar thing in a recursive fashion. Let's first walk through the iterative approach, and we can go straight to our code because there is no deep intuition behind this. It's pretty brute force, and that's why it's 2 to the power n, a very slow time complexity. Essentially, what we're doing is iterating through the string that we're given, checking if it's a letter. If it is, creating two new permutations, just like in the example, and if it's a number, then we add it to the existing permutations. Hence why we have one less append, and we add these permutations to a temporary variable before adding them to our output. And here's the exact same code, but I've added some print lines so that we can walk through it. If I run the code on the string from the example, you'll see the very first C, or character, that we iterate across is the A. It is an alphabetical letter, so we hit this for loop, contained within these two dashed lines. We add to our temporary variable the upper and the lowercase versions of this character, and at the end we update our output to equal this temporary variable. Pretty simple so far. So next, we iterate over to the 1. This 1 character is not alphabetical, so we hit the else block, contained within these two dashed lines here. At this point, we have two permutations in our output, which is what this O is representing. We add to each output, the smaller and the uppercase A, our number 1. Then we update our output to equal this temporary variable, ending up with A1 lowercase and A1 uppercase. Next, we hit our character B. It is alphabetical, so we go to this for loop, and for each current permutation, or O, in our output, we append the upper and lowercase versions of this B character. Except at this point we have two permutations in our output, the uppercase and lowercase versions of A with the number 1. So first of all, we loop over the lowercase a and the 1, and we add to that the lowercase b and the uppercase b. Then we go to the second iteration of this loop, we find the second permutation which is currently in our output, the uppercase a1, and add to it the lowercase b and the uppercase b. So now we have 4 permutations in our temp variable, and we update our output to equal this. And finally, we hit the 2. There is no uppercase and lowercase for the numbers, so we simply add it onto every permutation before we get all existing permutations after finishing our iteration of all the characters in this string, and we can return our output. So logically, very simple, but in terms of the efficiency of this algorithm, pretty complex, 2 to the power n. The reason it's 2 to the power n is because we have a string of length n. And each character can be represented in 2 different ways, upper or lowercase. So mathematically, the total number of different permutations is the product choices of each character. 2 times 2 times 2 times 2. Maybe we'll get some number times 1, but that will have no effect. And ultimately, this simplifies down to 2 to the power n. And our space complexity is also 2 to the power n due to the need to store all the permutations in the list output, which could be 2 to the power n permutations. And as for the recursive solution, I won't go into this one too much because it has a worse space complexity. However, here's the code, and I've added in this print statement. And you can see that, for example, when we take the first letter A, we're calling this backtrack immediately. That's the first thing that happens in our letter case permutations function. And initially, our subarray is empty, as you can see in the first print statement. And if our subarray permutation is equal to the length of our string, then we know we can append this to our results and return for the current backtrack. However, for the most part, we'll check if it's an alphabetical string similar to the previous solution and call backtrack if it is on the reverse upper or lowercase than the character currently is, and increase our iteration by 1. Otherwise, we would just call backtrack on the number itself. Otherwise, if it was an alphabetical letter, we would just call backtrack on the original upper or lowercase character. And you can see for the very first character A, we first call the uppercase backtrack, and we keep going down and down the call stack until we finished our permutations. Only then is this second backtrack called on the lowercase original A, and you can see by the first iteration I, and at that point we would go down the call stack and fill in our permutations. This has a similar time complexity due to the different possible permutations based on the upper and lowercase characters, but a space complexity of n plus 2 to the power n in total. Our recursive call stack has a O of n space complexity, and the space needed to store all the permutations is 2 to the power n again. And of the two, the first solution is a lot neater and definitely more achievable without looking at the answers. And so that's it for our letter case permutations question. Okay, so next up we have this subsets question. Pretty similar to the previous question, except this time we're returning all subsets of an array of numbers. We can return our output in any order, and note that each subset is unique, so 2 and 1 is the same as 1 and 2. And the question is slightly easier for us because all numbers are unique. So there's a lot going on in this solution. So again, I'm going to head over to the code instead of the whiteboard. So here's our code, and similar to the previous question, we initialize a result variable, which is our list, that we will return at the end. And then we begin our recursive backtracking solution on the very first iteration on an empty list. So I've added these print statements in here underneath our very first operation to help us understand what's happening. On the very first call of our function backtrack, we pass in the empty list and the start number 0. And the very first thing we do is append our current path to the result. And this syntax here appends a snapshot of the current path, creating a shallow copy. We use shallow copies in backtracking because they efficiently capture the current state of the path when dealing with simple immutable elements like integers. We could have used a deep copy, except that would make our solution less efficient. Deep copies are only needed when dealing with nested or mutable objects. Creating a shallow copy creates a new list object that contains references to the same elements as the original list. And since path typically contains simple immutable elements like integers, any changes to path, such as adding or popping elements, do not affect the elements that have already been appended to the results list. If the original path list changed an element, the previous reference would remain for the shallow copy, and a new reference in memory would be made for the changed element in the original list. This is because integers are immutable, and that is why we would use deep copies for mutable objects, like nested lists. So in a sense, appending a shallow copy of path to the results list effectively freezes the state of path, appending a snapshot of our path. If we were to use the original path object, then appending this to our results will lead to the elements inside our results changing when we change the path variable later on. And so deep and shallow copies are definitely something I'd recommend taking some time to look into. So we've added in the very first subset. Next, we begin our loop, which will have some recursive calls inside, beginning at the start index of 0 and ending at the length of our numbers. We then append to the path the very first item in our nums array, which would be the number 1 at the 0th index. This will give us a path containing just the number 1. And it might help if I print the path here. So we can see the path before our recursive backtrack is 1. So next, we're recursively calling backtrack on the next iteration along, passing in our current path. So we go back to the start of our function, and our new result is going to include this 1, plus the empty list we added earlier. And then we go back to the start of our for loop, from now the index 1 to again the length of our numbers. We now append the next number in our array, using the start index, which is now 1. This gives us the number 2, and our new path is now 1 and 2. So we call backtrack again on the next iteration along, passing in the new path of 1 and 2. So calling backtrack again will add the new path to our result, giving us the empty list, the 1 and the 1 and the 2. And of course, if we do this again, we'll end up with 1, 2, 3. Recursion is quite difficult to follow, so I've screenshotted our code and headed over to the whiteboard. At the very start, we called backtrack on the 0 and the empty list, which is exactly what we had here. And then we had our result, which was an empty list. Then we began a for loop, which is what this purple line is indicating, starting off at the index of 0. Then we added to our path the number 1 and began a backtrack on the next index along, which was also 1. And we ended up with the result of the empty list plus the number 1. So after beginning a new backtrack with the index of 1 and the path of 1, we ended up with the result of the empty list and the number 1. Then we began a new for loop starting at the index of 1. We added to the path the number 2, added this new path to our result, and began a new for loop at the index of 2. Using the index of 2, we found the number 3 in our nums list, added this to our path to get 1, 2, 3, and adding it to our result to get the following. Then we began a new for loop using the new index of 3. A for loop from 3 to 3 will not execute, so our code stops here for this recursion. We go back up the call stack to the for loop that was executing previously. At this point, the next backtrack along has just finished, so we pop off the 3 from the end of our path. And right now we have a path of 1 and 2. So this is where we've reached so far. After that, we'll go back to the beginning of our for loop, and 2 will become 3. That will also stop our code, because we've reached the end of our range. So we go back up to the for loop that was previously being executed. At this point, we had just called the backtrack on the next index, which was 2 on the path 1 and 2. So the next line along, based on the current path that we have, we pop off the last item. So right now we just have a path of 1. Then we go back to the top of our for loop and the next index along, which is 2. Following the code, we append to our path nums of the index 2. This will give us 3. So our new path is 1 and 3. And then we begin a new backtrack on the index of I, which is currently 2, plus 1 gives us 3 on the path of 1 and 3. And this is exactly what we have executing in our code, which will append 1 and 3 to our result. And we can continue this way, following the code, and we'll realize that this solution gives us every possible subset. We begin our main for loop on 0, adding 1 into the first backtrack. This will allow us to get 1, 1, 2, 1, 2, 3, 1, 3. And then at that point, we go all the way back up to the very first for loop and then iterate from 0 to 1. This then allows us to do the same process but with 2. So we'll add 2 in as the result, 2 and 3, and then go all the way back and iterate to the 3 and do the same process again, exhausting all of our options. And this style is very common in our backtracking solutions, as you will see in the next question. For example, after writing it out now, I can see exactly what's going to happen next. The backtrack that we just called on the 3 with the path of 1 and 3 will not execute its for loop because the index is 3. So we'll come back to our code and we'll pop off this 3 and our path is now 1. We'll go back to the top of our for loop and iterate to the next index along, which is 3. This will also stop the execution of our code and we'll go back to the very first for loop. At this point, we'll pop off the 1, our path is now empty, and we'll jump back again to the beginning of our for loop and we'll iterate to the next index along, which is 1. To the empty path, we'll append nums of the index 1, which is 2. Call backtrack on the index of 2 and the path, which now contains 2, and we'll end up appending to our result the number 2, which is exactly what we have in our code after the 1 and the 3. And so that's our solution. So with these backtracking questions, if we are implementing with the recursion, there will typically be some constraint in the question that we are looking for that limits the depth of our recursion stack, stopping the code execution and allowing us to go back up the call stack and find all the permutations or combinations that we are looking for. And the time complexity for this is n times 2 to the power n. N is the number of elements in the input list, and each element doubles the number of possible subsets, giving us 2 to the power n. And the cost of copying the current path to the results list is proportional to the size of the subset. So in the worst case, we have a full subset size of n. The cost operation would take n time. So the total time complexity involves all 2 to the n subsets, and for each potentially copying up to n elements, giving a worst case of n times 2 to the power n. And the space complexity is also n times 2 to the power n. We need to store all 2 to the power n subsets. In the absolute worst case, each subset can have up to n elements, leading to the total storage of 2 to the power n times n. And so that's it for our subsets question. Now we reach combinations, the next type of core concept in our backtracking section. And the question tells us, given two integers n and k, return all possible combinations of k numbers chosen from the range 1 to n. So if they gave us the number 4, we have a range of 1, 2, 3, 4, and we want all possible combinations with a size of 2. So 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So the question sounds pretty simple. If you'd like to give it a go, pause now. Otherwise, let's look at our solution. Here is our code, and you can see again we're following a similar style to the previous questions, where we kind of have a function inside of our main function that we're calling after creating our result variable, which we will return at the end. So let's take the example from the question and start with our n of 4 and our k of 2. And let's also create our result array. This blue arrow is going to indicate where we are in our code. And the first thing we do is call backtrack on the number 1 and an empty list. This is our backtracking base case. And we do this because our range is from 1 onwards, as the question tells us. So similar to the previous question, we have our start and our path. If the length of our path is equal to k, then we return, only after appending a shallow copy of our path to our results variable. And that's because we know we've reached our limit of 2 items in our path. Otherwise, we begin a for loop from the current start variable to n plus 1. This way, our loop will iterate up to and including n, because the second element in a range is exclusive. So I've written this out identically to the previous question, so hopefully it will make a lot of sense. So here's our current backtrack call, the very first one that we make, and here is our path, which at the moment is empty. And we will keep updating this to be the current value of the path. Our length is not equal to k yet, so we hit the for loop and begin. And I'm going to indicate a for loop with this purple line here, and I'm going to add the I, which at this moment is equal to 1. Then we append to our path the I, which is 1, and we call backtrack yet again, iterating one value along, passing in the start value of 2 and the path which contains 1. So we've called backtrack again and we're at the top. The length of our path is not yet equal to k, so we hit this new for loop. Except at this point we begin with an I of 2. Then we append 2 to our path, and we call backtrack once more, iterating up one number and passing in the new path. So now things begin to get interesting because the length of our path is indeed equal to k. So we can append a shallow copy of our path to the result variable, 1 and 2. And after that we return so the code can stop executing here. This takes us back to our backtrack call and we go to the next line, popping off the 2 from our path. After that we head back to the top of our for loop and iterate to the next value along, which is 3. Appending this 3 to the path gives us 1 and 3. And we call backtrack again on the next iteration along. So we pass in a value of 4 and the path 1 and 3. At the start of our new backtrack call, the length of the path will be equal to k, so we also append this to our results list. And you can already see that this backtracking gives us the same solution as the answer in the question, indicating that we're likely on the right path. So after appending, we return and the code execution for this backtrack stops here, leading us back up the call stack where we can now pop the last item in our path. We go back up our for loop and iterate to the next value along, which is 4. And now we can append the value of 4 to our path, which contains 1. Then we call backtrack once more, and you can also see why it was important to add the +1 to our n at the end of our range. Otherwise we wouldn't have looped over to this 4 and we wouldn't have included the 4 in the path, passing it down to our backtrack down here and eventually appending it to our results. At this point the backtrack will return, the code execution stops here, back up our call stack, we go to the next line and pop off the 4 from our path. At this point the for loop has finished because we've reached an I of 5, and at that point our backtrack function has finished, so the code execution stops here. Back up the call stack we were at this point and we can go to the next line along and pop off the 1 in our path. And so we finished all of the combinations beginning with 1. At that point we iterate along to the 2 and the whole process starts again with 2 at the beginning of our path. And we will avoid duplicates this way, for example including 1 again, due to the fact that every time we call backtrack we're adding 1 to our I value, dictated by the main for loop at the beginning of our recursion stack. So after we finish adding 2 to our path, the next iteration along will add 3, and we should have 2 and 3 being the next combination, which is also what the output has in that order. And so writing out our code for this backtracking solution in this way, almost identical to the previous question, helps us develop some problem solving memory, giving us a familiar solution for permutations and combinations. The time complexity for this solution looks a bit messy. O of k times n factorial divided by n minus k factorial times k factorial. So pretty messy indeed. In plain English we can say this section here is the number of combinations, and each combination takes O of k time to generate because we copy the path list of length k to the result, and so that's where the k comes from. And you may also see this written as O of k times nk. And we pronounce this as n choose k, where this part here, n choose k, denotes this entire section here, also known as the binomial coefficient. This basically just represents the number of ways to choose k elements from a set of n elements. And the space complexity is the exact same. There are n choose k combinations, and each combination is of length k. So the space required to store all these combinations is k times n choose k, our binomial coefficient. And the depth of our recursion stack is at most k, because we add elements to the path until the length is k. And you see that because at each time we have 2 elements in our path, we immediately return. So if we were just looking at our recursion stack, the space would be O of k. And the storing of our path is also O of k, except the recursion depth and this path list are not the dominant terms here. It's the storing of our combinations in the results, and that's where our space complexity comes from. And so that's it for our combinations question. Next up is our final question in the backtracking section, which is called permutations. So we've just done combinations and now we're doing permutations, where we are given an array nums of distinct integers. So all the integers are unique. We want to return all possible permutations in any order. Of course, the order for each list inside of our return list matters. And you can clearly see we have every possible permutation. And again, our backtracking solution is going to be pretty similar to all the questions we've seen in this section so far. So I'll definitely give it a shot now. Otherwise, let's go through the solution. So here's our code and the first example from the question. And you can see, of course, it's pretty similar to the previous questions. We begin by initializing our results array, which we will return at the end. Before that, however, we call backtrack, passing in 0. 0 will be our starting index, and of course we want to include the 1 here, so we're going to pass in 0. The second argument will be the length of our nums, and this will be the constraint for when we want to append to our results list. Each question is different. Although the style of our backtrack solution is similar, the details are different. Here the question is asking us to return all the permutations of the same size of the original list. So we know when we've iterated through our for loop and our starting index for the backtrack becomes equal to the length of our nums, we've reached the end. We have 3 elements inside our nums list, so we can append to the result and return. The previous example was the same. Only when we had 2 integers in our path could we return. The question before that, however, we were not returning, and that's because we wanted all possible subsets. So even if we only had 1 integer, we would append to our results and continue to find a larger array, and then append that also. So just a note on the details and the importance of reading the question twice and understanding exactly what it wants. So I'm sure you're all experts on this now, but let's quickly run through a few steps of our code to help us understand what's happening. So we begin with our backtrack on an index of 0 and the length of our nums, which is 3. At the beginning, our start is of course not equal to our end, so we jump to this for loop, which again I'll show with a purple line and the current index that we are on. We begin by looking up our numbers array and switching the start index with the current I index. So at this point, our start is equal to 0, as is the I in our for loop. So switching these two numbers across keeps the current order in our nums the same, allowing us to append the original order in a second. So we're going to call backtrack again, as always, iterating up to the next index, and we're keeping our ending condition the same throughout. At this point, our start is still not equal to our end, so we'll reach our for loop, switch numbers over, and call backtrack again. So we have a new for loop starting at an I of 1. Our start and our I are still equal. 1 and 1. So our nums list order stays as the original and we call backtrack yet again. 2 is still not equal to 3, so we reach our for loop, switching over the second index with the second index, keeps the original nums list order the same, and we call backtrack once more. At this point, our start is equal to the end, so we can append to our results list a shallow copy of our nums. So there's the very first permutation in our results, and here's where things begin to get interesting. Our code execution stops here, and we go back up to the call stack to where we just called backtrack on the next index along. At this point, our start and our I are still equal. We will see later that this line is meant to undo the swap that we done before the backtrack, allowing us later to make changes unaffected by our current changes in order to get the full list of permutations. So switching the 2 and the 2 gives us the original nums list in the same order. We go back up to the beginning of our for loop, except now we've reached the end because our I will be 3. So our code execution can stop here and we can go back up the call stack yet again. At this point, we had just called backtrack with the 2. So on the next line, we will switch the I with the start, giving us the same order of our nums list. Then we go back to the beginning of our for loop and the 1 becomes 2. Now we can finally begin switching some numbers around. Our start was equal to 1 and our I is now 2. Switching these two numbers across will give us 1, 3, 2. We're switching the first and the second index, 1 being our start variable and 2 being the current index. So after that, we call backtrack on our start, which is 1, plus 1 gives us 2, and our end is staying the same at 3. At the top of our new backtrack, our start is not equal to our end, so we begin a new for loop. At this point, our I is equal to 2, as is our start variable, so we call backtrack yet again, adding 1 to our start. As you can see, our start is equal to our end, so we will append to our results and return straight after. So we add our current nums list, which is 1, 3, and 2. Code execution stops here. Back up the call stack, we had just called back backtrack, and switching the current start, which is 2, with the current I, which is 2, does nothing. So we have reached the end of our for loop, because at the next iteration our I will be equal to 3. And we go back up our call stack once more to when we had just called this backtrack with the 2 and the 3, and we reach the next line, switching over our start and our I. Our start is 1 and our I is 2. This reorders the nums list back to its original state. At this point, the for loop for our backtrack with the start variable of 1 would have reached its end. So we go back up the call stack once more to when we called the backtrack with the start of 1 and the end of 3. Our I is equal to 0, as is our start, so switching these numbers over does nothing. And now we can finally loop over to the next iteration in our very first for loop. And taking a look at our answer, right now we have 1, 2, and 3, and 1, 3, 2, which is the exact same as what the output has. So you know we're on the right track. And you can see that iterating now to the next index in our main for loop, the 1 pointing to the 2, gives us a whole new set of permutations beginning with the number 2. And finally, on the last loop, our very first index will have the number 3. So it's this main for loop dictating our permutations and the order of our output in our results variable. So I'm going to leave it here because I'm pretty sure you can get the hang of it by now. If not, feel free to continue following the code execution by yourself. As for the time and space complexities, it is O of n times n factorial. There are n factorial permutations for an array of n distinct elements, and we've seen this before. For example, 3 factorial is 3 times 2 times 1. And for each single permutation, it takes n time to generate this to our results list. We are carrying out the same number of operations on our n factorial permutations. For example, swapping the elements and creating a copy of our list. So these n operations times by our n factorial permutations gives us a time complexity of n times n factorial. And similar to the previous questions, our space complexity is the exact same as our time complexity. We have our n factorial permutations, each of length n, requiring the same space to store inside our results variable. And on top of that, we also have a recursion depth of n space. So our call stack is O of n. And finally, we're also creating a copy of our nums list, which at each time we are appending to our results will be of length n. So that also needs n space. Overall, however, the bottleneck is our n times n factorial space, the most dominant term. And so that's it for our permutations question, covering all the different types of backtracking solutions we have, giving us one more solution in the same style we've seen before that we can reuse whenever we are asked this style of question, making changes based on the details that we are asked. And so that's it for our backtracking section. Our next section is linked lists. We have gone through a lot of these questions in the data structures part of the material, so this should be a walk in the park for a lot of you. And let's head straight into the first question, which is called middle of the linked list, where we have to, given the head of a singly linked list, return the middle node of the linked list. If there are 2 middle nodes, return the second middle node. And the question also defines for us our linked list by giving us a class list node. So for example, if we were given the linked list from 1 to 5, we would return the middle node, which is 3. And our output shows 3, 4, 5 because 3 is pointing to 4, which points to 5. So it is a bit misleading because in fact we will just be returning the node itself. And we've already gone through this in detail in our data structures video. We simply have a while loop which will push along our slow and fast pointers as long as the node the current fast pointer is pointing to exists and has a next node. So in the first step of our while loop, the slow pointer will move along one node and the fast pointer will go to the next node. The condition for our while loop is still true, so we move along 1 more in our slow pointer and 2 more in our fast pointer. At this stage, the node that the fast pointer is pointing to does not have a next node, and so we break out of our while loop and return the node that the slow pointer is pointing to. And let's quickly see how this will work for an even length list. Our slow pointer will move along 1 node and our fast pointer will move along 2 nodes. The condition for our while loop is still true, so our slow pointer will move along 1 and our fast pointer will move along 2 nodes. At this point, fast is pointing to none, so while fast is not true, and our slow pointer is pointing to the second of the middle 2 nodes, so we break out of our while loop and return the second middle node, just as the question asks in the second example. So a pretty nice intro into linked lists, and we can do this in O of n time because it's just one while loop with operations that increase linearly as the input grows. And of course we have constant space because we're just keeping track of our slow and fast pointers as we iterate across our linked list, no matter how big it is. And so that's it for our introduction into linked lists with the question where we have to find the middle of the linked list. Next up we have linked list cycle. and we are given the head of a linked list, we should determine if the linked list has a cycle in it. And this is just defined as some node in the list which can be reached again by continuously following the next pointer. The question also says that internally, pos is used to denote the index of the node that the tail's next pointer is connected to. Pos is not passed in as a parameter. So in this example, the tail, which is -4, is connected to the node of index 1, our pos of 1. And we need to return true if there is a cycle in the linked list, otherwise return false. And in our constraints, we see that pos is -1 if it is not a cycle, otherwise it's a valid index. And as a follow-up, we want to try answer this question in constant memory. So let's have a look at our solution. So here's our linked list, and again we're going to use a slow and fast pointer. And the trick is that if there is a cycle, eventually the two pointers will meet. So as the question shows us, let's imagine that -4 points back to -2. Both our slow and fast pointers are initialized on the head of our linked list. So while the fast node and the fast.next nodes exist, let's move them along like we did in the last question. So at step 1, we're going to move the slow pointer up 1, and my fast pointer in red is going to move up 2 nodes to 0. Let's repeat this again. The slow pointer moves to 0 and the fast pointer follows the loop in the linked list back to the value 2. So let's clean this up a bit. Back at the top of the while loop, our condition is true, so let's move the slow pointer up to the next node in our linked list and move the fast pointer to its next node. So our if condition, slow is equal to fast, is true. So we can return true, and that's our solution. Nice and clean. If we had a situation where we didn't have a cycle, eventually the fast pointer would be none, or it wouldn't have a next, and we would break out of this while loop and return false. And of course it's O of n time due to the fact that we have one iteration. In the worst case scenario where the tail points back to the first node, both pointers will meet after n iterations of the slow pointer. This is of course because the fast pointer moves twice as fast, so it will meet the slow pointer within n steps. So the slow pointer would take n steps and the fast pointer would take n divided by 2 steps. And if you're interested in looking a bit more at this algorithm, search up Floyd's tortoise and hare algorithm. And of course we have constant space, we're only keeping track of our slow and fast pointers. And so that's it for finding a cycle in our linked list. Nice and simple. Next up, we have another question which we have gone over in our data structures practice for linked lists, where we are asked to reverse a linked list when we are given the head of a singly linked list. So pretty simple. If we have 1, 2, 3, 4, 5, we want to reverse the list. So the head is now 5 and the tail is 1. So 1 points to none. If our list is empty, then we just return an empty output. And if we didn't have this example, it might be a good clarifying question to ask if you're in an interview, shows that you're paying attention to the details. And the follow-up question asks if we can implement it iteratively and recursively. So today we'll be going through the iterative solution because, as I've said before, it's much more readable, easier to debug, and less prone to consuming too much memory. But definitely give the recursive solution a go if you can. Otherwise, let's get into our solution. So here's our linked list and here's our code on the right. You see we have in total 3 variables. Our previous pointer, which we have in blue, our current pointer, which we have in red, which we initialize at the head of our linked list, and we can add this label to let us know what we've labeled as the head node. And we have this next pointer inside of our while loop. So current is definitely not equal to none, so we set the next pointer to be current's next. And then we set the current next to be equal to our previous. Our previous is initialized to point at none. So we can set the head node to now point to none. And then after that, we set the previous to equal our current node. So here they are both pointing at our head. And then we update our current to be equal to the next pointer. So you can see the responsibility of this next pointer is to enable our current to update after we remove the link between the current and the next node. And just before that, we update previous to equal our current pointer. And let's repeat this all over again at the top of our while loop. Our next pointer moves to point to current next. Current.next is set to previous. So we're essentially removing this arrow and changing it to point in reverse. And then we set things up for the next loop by moving our previous to equal our current and our current to equal our next pointer. Repeating this again, we'll move our next pointer to the 4 node, update the next of our current pointer to be equal to the previous node, update our previous to point to the current node and our current node to point to the next pointer, setting us up to continue reversing our linked list. If we repeat the while loop one more time, we reach a position like this. We've set our next pointer to be current's next, which is none, because we're at the tail of our linked list. We set current.next to equal previous, so we move this arrow and point it to the for node, update previous to be our current, and our current to be our next pointer. At this stage, our while loop will no longer execute because current is indeed equal to none. We've reached the end of our linked list. We have one more small adjustment to make, which is to update the head of our linked list to point to where previous currently is, and that is the new head, which was the old tail of our linked list. And that is how you reverse a linked list. Nice and simple. Of course, the time complexity of this solution is O of n because we have one while loop with a bunch of operations that increase linearly as our input size grows, which is just the length of our linked list. And the space is of course constant because, as we said at the start, we only have 3 variables: our previous pointer, our current pointer, and our next pointer. And so that's it for reversing a linked list. Next up in our linked list section, we have another easy, but the pass rate has dropped significantly, so we're doing a bit more here. The question asks us, given the head of a linked list and the integer value, remove all the nodes of the linked list that have that value and return the new head. So essentially what we're going to do is loop through this linked list, checking the next value of each node. If we find a node with the current value that we're looking for, we kind of want to bypass the current node, and we can delete it or not. It doesn't matter as long as we remove it from our linked list, and take the arrow that the 2 is pointing to and send it straight to the 3, and then continue traversing our linked list. So a fairly easy concept, and let's get into our solution. On the left, I've copied the linked list from the question, and before we look at the code, let's look at my note, which is try to find workarounds and a complete solution to allow all edge cases to be solved by the same function. So when I first solved this question, I had a lot of if statements. For example, what if it's an empty list? What if it's a head node? What if it's the last node that needs deleting? So all of these edge cases, and looking at the solutions, I found one that is a complete solution in that every single type of edge case could be solved by the same function. And so let's take a look at that code now. The very first thing we do is create a dummy node which points to the head, and we do this in case it is the head that needs updating, and we can set the value to -1 because the problem constraints tell us that the value will never be below 1. So let's label this our dummy head, and that's how we begin our solution. And the next step is we initialize a current node pointer at the dummy head, and then we begin a while loop where the condition is as long as the current node.next exists, continue to traverse our list and check if the node needs deleting. And this is because we know that when the current node doesn't have a next, we're at the end of our list, we finished our traversal. And now you might ask me, but wait, if our current node is pointing to the last node, for example, well, our while loop would stop while current node.next is not equal to none. But it's okay because we are checking if the current node's next is equal to the value that we need to delete. So at this point, we would have already checked and deleted the 6 because our current node checks at the node before whether our node's next value needs deleting. And this can save us some complexity, for example, keeping multiple pointers to check what our previous and our next or our next pointer is, similar to the previous question. So let's walk through this example from the question, and afterwards we'll take a look at the case where the head needs deleting and the dummy head proves its use. So the first thing we do is hit the while loop. The first line, we check if the current node next value is equal to the value that we're looking for. The question told us we want to delete the value of 6. So this is not true, and we hit our else block, updating our current node to traverse our list and point at the next node. So now we've entered our original linked list. So let's follow our code. Another iteration of our while loop, and we find out that the current node's next node is one that needs to be deleted. So what we do is we take the current node's next and we point it to the current node's next. And what this would look like is taking this arrow and pointing it to the 3. Now at this point, we don't need to remove this 6. Once we return the head like the question asks us to, the 6 will be removed from our linked list. For example, traversing the linked list would go 1, 2, 3, 4, 5, 6. But again, it might be a good point to bring up in your interview that you've noticed this potential issue in failing to clean up the deleted node. And it's important here not to update our current node because we need one more while loop and one more if check to make sure that after updating our 2 to bypass the 6, the 3 does also not need deleting, because if the 3 was a 6 value, we would have to repeat the same process. Except in this case, it's okay. So we update our current node to point to the 3, and a few more while loops over, and we end up at the 5. The if statement tells us that the current node's next value is equal to the value we're looking for, so we can set the current node's next to point to the current node's next, which is none. At this point, the current node's next is equal to none, so our while loop has finished, and we return the dummy head's next, which is in fact the head. And let's quickly go over a case where the head needs deleting. deleting. So we can see the value of this dummy head. So let's imagine we have a linked list which looks like this. The very first thing we do is set the current node to point to the dummy head. In our while loop, our current node's next value will need deleting. And let's remind ourselves that in fact, this is the head. So we do the same thing we've done before and point our dummy head to the current node's next, which is the head's next. After that, we'll do another loop. The 2 does not need deleting, so we update our current node, point it to the 2 node. At this point, the current node's next is equal to none. So we break from our while loop and we can return the dummy head.next, which is our new head. And we can see based on the question that they're passing in a head which is just a node. Depending on how you write the linked list, as we saw in our data structures videos, we can in fact create a linked list and label the head. But in this case, this head label is not a concrete value. We're just passing around list nodes as an argument for the head. So when we return our dummy head's next node as the head, which the question asks for, we're simply returning another list node. And so that's our solution. And of course, it's of n time due to the single while loop and constant space due to the fact we are only keeping 2 variables, our dummy head and our current node. So that's it for removing nodes from a linked list. So next up we have reverse linked list 2, which builds on the reverse linked list question by making us reverse a single part of the linked list. So not the entire list, but a section of the linked list. And the question will give us left and right integers, which represent the index of the 2 nodes in our list from which we should reverse the links. And before we look at the code, let's try to consider our high-level approach and some of the edge cases that we might come across. So here is the first example from the question, and we are told we want to reverse from 2 to 4. So we're given a left pointer of 2 and a right pointer of 4. So we know our left pointer is here and our right is here. Essentially, what we want to do is break each of these links, have the 4 node instead point backwards to the 3 point backwards to the 2, and with some steps in between, eventually the 2 point to the node that's immediately right of the right pointer. So that's how we can identify that. And all that's left now is to make the node left of the left pointer point to the node that is defined by the right pointer. And so at a high level, there's our solution. We have 1, 4, 3, 2, 5. 1, 4, 3, 2, 5. So as you've seen in our quick walkthrough, that we are using the node left of the left pointer. And in the case that we need to delete the head, so our left was 1, this could cause some difficulties. And similar to the previous question, we could check for this with an if statement, except it will be a lot easier to introduce a dummy head. So previously, when we were reversing from the second node, we had the head or the number 1 node point to our right. In this case, if we are reversing from the very first node, we would break this and have the dummy head point to the right instead, making the node 4 our new head. And we know this because whatever our dummy head points to is the head of the original linked list. So let's begin our solution, and we're going to do this in 3 parts. The first part is reaching the node at the left position. So in this stage, we just want to set things up before we begin breaking links and reversing things. So we've created our dummy head and set it to -1. Based on the code, this could be any value, but seeing as the question tells us the value of the node is between -500 and +500, then maybe it's a good idea to change this to be positive or negative infinity or outside of this range. But based on the solution, it's not going to be a problem. Then we begin by creating 2 pointers, our left previous and our current node. Current node is going to drive our traversal, so it's always going to point to the current node that we're on and we're making changes to. And the left previous is the node that's directly left of the left that's given by the question. So the question tells us the left that we want to begin reversing from is the 2, and the right side that we want to finish our reversal is the 4 node. And so by the end of this first stage, we want the left previous to point at the head and our current node to point at the left. And how we're going to do this is we begin with our left pointer at the dummy head and our current node pointing at the head. And we begin a for loop in the range of left -1. Left -1 will give us exactly the number of loops or iterations of our current node to reach the left pointer. So for example, 2 - 1 in this case, the current node will reach the left pointer and the left previous will reach our head. If left was 3, for example, then we would do 3 - 1. Current node needs to move twice and our left previous would move 1, 2 to the second node, setting us up perfectly. And we do this simply by updating the 2 variables at once. Our left previous becomes what our current node was and the current node simply becomes its next. So for this example, we will do 1 iteration. Our current node is now pointing at the left and our left previous is pointing at the node left of the left pointer. And so that's it for the first part. In the second stage of our solution, we begin by creating a new variable called previous and setting it to none. So there's our previous pointer. Then we begin a for loop in the range right - left +1. And we can do this because right - left gives us the number of links or the number of steps between those 2 nodes, 1, 2. And then we +1 because actually we want the number of nodes that we should be taking action on. So each iteration of our for loop corresponds to a node that we are taking action on. So in our example, we're going to have a range of 3. And then finally, we create one more variable, our next pointer. And we need this next pointer to be able to update links after breaking them, which we're going to see right now in a second. We set our current node.next to equal previous. So in the very first case, our previous will be equal to none. And we'll do some changes at the end to fix this. So what that means is breaking this link and setting 2 to point to none, which is what we set previous to equal originally. And then in the third line of our for loop, we set things up for the next iteration of our loop. We do this by setting previous to equal our current node and our current node to equal our next pointer. And we've seen this next pointer in action in the previous questions. As we've just seen, it lets us update our current node. So on the next iteration of our for loop, our next pointer points to the 4. Our current node.next is set to now equal our previous, which is the 2 node. And then we update everything again. Our current node points to the next pointer and our previous is now the 3 node. And we have our final iteration of our for loop, update our next pointer, update the current node's next to be the previous, and update our previous to be the current node, and our current node to point to what the next pointer is currently pointing to. And so that's it for stage 2. We've reversed all the links between the left pointer and the right pointer, and you'll notice this part of the problem was pretty much identical to the entirety of the very first reverse linked list problem. Now all that's left to do is some cleanup. We need to set our left previous to point to the node directly after where we finished making our changes, and we need to update the left, which we set to none, to point to the last node we changed, which is the right. So let's have a look at that. So here's where we left things. So there's 2 things to clean up, and we can do this in 2 lines. Finally, using our left previous pointer, we take the next of that and set it equal to our current node. So the next of our 1 node is the 2 node, and the next of that is pointing to none. And this will always be the case no matter where left is. So we're going to take this arrow and point it to the current node, which is the 5. And then we take the left previous's next, which is referring to this arrow, and point it to the previous, which is the 4, this arrow here. So let's clean this up. You see now, if I remove all the pointers and the arrows, and I've not changed any of the links, I've simply moved them around, we have our 1 pointing to the 4, our 4 pointing to the 3 pointing to the 2, and the 2 node pointing to the 5th node, which points to none. 1, 4, 3, 2, 5. 1, 4, 3, 2, 5. And so that's our solution. And finally, here's our notes, our reminder for how to answer this question, broken down into 3 parts. And the time complexity is of course O of n. We're doing one single iteration over our linked list, which as the length of our linked list grows, so will the number of operations proportionally. And it's constant space because we're only keeping track of these 4 variables here, which is a nice reminder that when I come back to this slide, I can check. Immediately I can see these 4 pointers, and I know how to answer reversing a linked list 2, where we reverse part of the linked list. So that's it for this question. So next up we have this palindrome linked list question, where we are given the head of a singly linked list like always. We need to return true if it is a palindrome or false otherwise. And it gives you the definition of a palindrome, which is just a sequence of characters or numbers that read the same forwards and backwards. So 1, 2, 2, 1, 1, 2, 2, 1. And they mark this as an easy question, except we'll be using a few concepts from other questions. For example, finding the middle of a linked list and reversing items in the linked list. So personally, I would put it at a medium, which is why it's towards the end of our linked list section. So let's get right into our solution. Here's our linked list from the question, which is indeed a palindrome, so we should return true at the end. And the first thing we're going to do is find the middle of the linked list. And we've already done this in a previous question in itself, so this should be no problem at all. We initialize 2 pointers, a fast and a slow pointer. So here's our fast pointer initialized at the head, and here's our slow pointer also initialized at the head. And while fast and fast.next are truthy, we're going to move fast along twice and slow along once. So one iteration of our loop will put the fast pointer at the 3rd node along and the slow pointer at the 2nd node along. Our while condition is still true, so we move fast along twice and slow along once. And that's all there is to the first part of this question. Nice and simple. Now for the second part of the question, we're going to reverse our linked list, except we're only going to reverse the second half. So we begin by creating a previous pointer and setting it to none, like we've just seen in the previous question. So here's our previous pointing at none. And then we begin by creating a next pointer and setting it to slow's next node. So here's our next pointer pointing at the last node in our linked list. And then again, as we've seen before, we update slow.next to equal our previous. So we're breaking this link here and pointing the 2 to none. And then we set previous to equal our slow and our slow to equal the next pointer. Slow is still not equal to none, so we repeat the process one more time, updating our next pointer to equal now none, which is the last node's next. We set our slow.next, which is this arrow, to point to our previous, which is the node to the left. So there's our new link. And then we set previous to equal slow and slow to equal our next pointer. At this point, slow is equal to none, so we finished reversing the second half of our linked list. And finally, the third stage of our solution. We create 2 pointers, our left and right. And we have no need for these 4 pointers anymore, so we can get rid of those. We now have our left initialized at the head and our right initialized at our previous. Our previous had finished at the very last node of our linked list. So there's our right pointer. And essentially what we're going to do is use the right pointer to iterate across the linked list and use the left pointer to do the same and check if they are equal. So we begin a while loop, which continues as long as our right pointer is not equal to none. And this is the only way we can know that we finished our traversal, because we did not update the first half of the linked list. So the end of our linked list on the left side still points to the second half of the linked list. And that's fine based on what we're trying to achieve in this question. So if our left.data, or value as it is in the question, is not equal to the right, then we know it's not a palindrome. In this case, 1 is equal to 1, so that's fine. And we now update our left pointer to be the next node along, and our right pointer to also be the next node along. Repeat the process again, and 2 is indeed equal to 2, so we can update both of our pointers again. Left.next, and we're at the third node, and right.next, and we've reached none. At this point, our while loop no longer executes because right is now equal to none. So we know we've traversed both sides of our linked list, and we know during both traversals, each node was identical to the other half. So we can break from our while loop when right is equal to none and return true at the end. And so that's our solution. So similar to the middle of the linked list question, we use our slow and fast pointers to find the middle. And then we reverse a section of the linked list, similar to the previous question, using these 4 pointers. Except based on the details of the question, we don't need to do all of the updates. So it's fine for us to still have this link from the first to the second half, as long as we check if the right pointer is equal to none. And then in the third and final section, we use 2 pointers to traverse both halves of our linked list, checking at each stage if the values of the nodes are equal. And of course it's O of n because all of the operations are linear in time complexity. Each of the 3 while loops are independent, so there's no exponential growth of our operations as the linked list grows in size. And it's O of 1 space because we're only keeping track of a set of variables. For example, our fast and slow pointers, our next pointer, and our left and right pointers. And so that's it for our palindrome linked list question. Nice to see how we can bring in previous concepts and adjust them based on the current question. Now we have our final question in the linked list section, which is merging 2 sorted linked lists. So this is quite a nice question, especially if you've completed the sorted array squares question in our 2 pointers section. So we are given the head of 2 linked lists, list 1 and 2, and we want to merge them into one sorted linked list. The list should be made by splicing together the nodes of the first 2 lists. Return the head of the merged linked list. So in this example, we have 1, 1, 2, 3, 4, 4. And based on the order of the 1s and the 4s, we can see it doesn't really matter which node comes first if the values are the same. And based on the definition of our list node, programmatically there will be no difference. So let's go ahead and give this a go. Here's our solution. So the very first thing we do is create a current pointer, our dummy head, and make them both equal to a brand new list node. This is going to be the beginning of our new sorted linked list, which we will return at the end. So here's our dummy head, and we don't need to give it a value because we're not going to include it in our final linked list. Then we begin a while loop, while list 1 and list 2. Remember from the question, list 1 and list 2 are the heads of the 2 sorted linked lists. So let's create some pointers for those. And the main function of this while loop is to compare their values. And after the comparison, we can begin linking to our new dummy head, whichever value is smaller in the correct order. And we don't need a separate if statement for if the values are equal, saving us some code complexity. And you'll see why this is the case in a second. So for the very first comparison, the 2 are equal. So we hit our else block and set current.next to equal list 2. At the start, we set current to equal our dummy head. So the next node in the linked list is going to equal this list 2. Except right now, this list 2 is still pointing to the 3. So let's make sure we don't forget that. So this is what it looks like right now. And then we update list 2, and updating the 2 variables in one line means current will equal list 2 before we made the change. So we can set our current to equal this list 2, which it was previously. And then we begin a new iteration of our while loop. At this point, list 1's value is definitely less than list 2's value. So we can repeat the process except on list 1 this time. Setting current.next to equal list 1. Current.next is referring to this arrow, so we can point it to list 1. And then we repeat the same updates, moving list 1 to equal the next next node along, and our current to equal what list1 previously was. So let's tidy this up a bit, and there we go. Let's repeat the same process again, comparing the two values. The list1 pointer is less than the list2 pointer, so we hit the if block, update current.next to equal list1, which it currently is, so that's okay. And we can actually remove this label because we don't need it anymore. Update list1 to be the next node along, and then update our current to be what list1 previously was. Repeating the while loop again, we'll hit the else block because the list2 pointer is less than list1, so we'll change our current.next to point to the list2 node, and then update list2 to be the next node along, and then update current to be what list2 previously was. We check again, they are equal, so we hit our else block, adding current.next to equal list2, which it already is, updating list2, which now equals none because we're at the end of our second list, and then update current to be what list2 previously was. And at this point we can break from our while loop. We don't need to carry on iterating because no matter how long list1 is, we know that all the values are going to be greater than what current currently is, because the question told us the original two lists will always be sorted. So what we can do is just append whatever's left of list1 on the end of our current merged list, and then we check list1 or list2. This is to make sure that at least one list has some nodes inside that we want to append. And then we check if list1 set current.next to equal list1, or append list2 if it's list2 that still has nodes. So we set our current.next to equal this list1, and there's our new merged linked list 1 1 2 3 4 4 1 1 2 3 4 4, and we return dummy.next because the question was the head of our new merged list. So that's it for the solution. We're just creating a new merged list using two pointers like we saw in the array section to compare the values of the two lists at each point and add them onto our new merged list. So we can do this in O of n time because even though we have two iterations on list1 and list2, they are independent, both occurring in our single independent while loop. And of course it's constant space because we're keeping track of three pointers, list1, list2 and our current pointer, as well as our dummy head. So that's it for merging two sorted linked lists. And that's also our linked list section complete. Our next section is stacks, and if you've gone over the essential software foundations, then you'll know, for example, we use this data structure in call stacks, a crucial concept in JavaScript's runtime environment, representing the mechanism by which the JavaScript engine keeps track of function calls in a program. So a nice reminder that these data structures are not just for practicing interview questions, but all of them have crucial applications in real-world programming. So let's get into our first question, which is the min stack question. And if you've watched the data structures video, you'll know that this is essentially implementing a priority queue using a stack, which we've seen before. So it should be fairly familiar and definitely not a medium question in my opinion. So with that in mind, go ahead and give it a go. Otherwise, let's take a look at our solution. We are asked to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. And we are given a class minStack with the four functions that the question wants. And of course, each solution must be O of one time. So let's get right into our code. And on the right, you'll see we initialize a stack in our initialization function. Now, some solutions you'll see might initialize two stacks, one to keep track of the minimum and one to keep track of the values. Except I think it's a lot cleaner to keep track of one stack, and inside our stack, the way we keep track of the minimum value is really neat. So let's play around with the code of our solution. So when we instantiate our class, we're creating the min stack, and inside we're initializing this empty stack. And let's push the three numbers that the question pushes, -2, 0, -3. And before we print the result, let's take a look at what's actually happening. Our push function is the most difficult of the three, so once we've got that down, the rest will be a walk in the park. First of all, we check if our stack exists. For the very first case of adding -2, our stack does not exist. So our current min is set to x, which is the number that we pass in -2. After that, we append to the stack -2 and the current min, which is also -2. So at this point, our stack looks like this. And in actual fact, under the hood, our stack is just an array of tuples. The first element in each tuple is going to be the value that's passed in, -2, 0, -3. The second element is always going to keep track of the minimum number up until that point. So when we push 0 onto our stack, we're going to have -2, -2, and 0, -2, because at the point of adding this 0, -2 is still the smallest value that we have in our stack. And the way we do this in the code is we check what the current min is before appending. And we do this by using the built-in min function and checking the x, which at this point is 0, against the most recent minimum. Self.stack -1 gives us the element at the end of our stack, the rightmost element. So we've not yet added our 0 in yet, so our stack at the index -1 gives us this tuple, and the first element in that is going to be 0, 1, -2, the second element, because we're 0 indexing in Python, so that gives us -2. Of 0 and -2, our minimum value is going to be -2, so we append onto our stack 0 and -2. And in the third example, pushing the -3, we're going to create a new tuple. The first element is going to be -3, our value, and then we check again. And the second element is going to be -3 because that's our new value. And if we walk through this in the code, we'll see that our stack exists, so we hit the else block, and we check the minimum between -3, which is the x that we're passing in, and self.stack -1, which gives us this 0, -2 tuple. The first index gives us -2. So between -3 and -2, -3 is our new min, so we append onto the stack -3 and -3. So you see that every time we append onto our stack, we're appending the new minimum value in the second position and whatever value we pass in the first position. And this is how we're keeping track of our minimum value. So when the question asks us to get the minimum, which is the next operation in our list, we can just return the index of -1, 1. So stack -1 gives us the last tuple in our stack, and the index at the first position gives us -3, our most minimum value so far. If we wanted to pop, well, that's pretty simple. Pop stays the same. We're just using the built-in pop function to pop the last item. We're not returning anything, so we're popping the entire tuple off of our stack. We're just trying to get rid of it, which is different from the get min. As we see down here in our explanation, we're returning -3. And if we want top, well, let's say we've just popped off the -3, so our stack now looks like this. So now we're on top, we should return 0. And that's because top simply returns the last item in our stack. As you'll remember from our data structures video, last in, first out order. So this should return 0, and our stack will simply be left with our -2, -2. And at this point, if we get min, well, we only have one more value left, so of course we'll be returning the -2. So that's it for our code, and of course each solution is constant as the question asks for. We're not iterating over our list, we're not doing anything complicated. Each function, we're either returning something based on the index, and if we know the index, then it's a constant operation. We're just grabbing whatever information's at that memory address. When we do our min, for example, we're comparing two values which we already have, our x, which is being passed in, and the exact position of our most recent minimum value. To append is just to add on the end, and to pop is just to pop off the top. Of course, however, our space will be O of n because we're keeping track of our stack. So if we pushed onto our stack n times, our stack would be of n space. And so that's it for this min stack question. Next up, we have the valid parentheses question, and this is a nice one because it's a little look into how language parsers work, a fundamental concept in programming. You'll be familiar with this if you have gone through the software engineering material or have done your own learning. Compilers and interpreters need to ensure code has the correct syntax before beginning to process it. Otherwise, it will break. So they use language parsers. And without getting into the low-level specifics, this generally means making sure the syntax rules of the programming language are upheld. Things like checking for balanced symbols, such as the opening and closing of brackets, which is exactly what this question, valid parentheses, is asking of us. Given a string s containing the characters, and we see three types of brackets, curved, curly, and square brackets, determine if the input string is valid. And it's valid if the opening brackets are closed by the same type of brackets in the correct order, and every closed bracket has a corresponding open bracket of the same type. And we see from the three examples below exactly what the question is asking of us. So let's get into our solution. So here's our input from the first example of the question, and here's our code. The very first thing we're going to do is initialize a stack and a hash map, or as we call it in Python, a dictionary. And our dictionary is going to have the keys of the closing of the brackets and the values of the opening corresponding brackets. And then we begin a loop across our s string which is passed in. So let's make this bigger and add an arrow to show where we are. In our if statement, we check if the stack exists. At this moment in time, it does not, so we'll come back to this later. So instead, let's append into our stack the element that we're currently pointing to, which is this open bracket. So here's what our stack looks like at this moment in time. And then we go back to the top of our for loop and move on to the next symbol. At this point, the stack does exist, so we check the second half of our conditional in our if statement. If the element is in the hash map, so we're checking the keys of our map, and it is definitely in our hash map, it's this one here, and stack -1, so the element at the end of our stack is equal to this hash map element, then we pop from our stack. Well, this stack -1 is pointing to this open bracket here, and is it equal to the hash map using the element that we're currently iterating over to check the value in our dictionary, this one here? Well, they're definitely equal, so we can pop this open bracket from our stack. And so you can kind of get the gist now of how our solution is working. Anytime we see an open bracket, we add it to our stack, and anytime we find the corresponding closing bracket, we remove that open bracket from our stack. And at the end, if our stack is empty, we know we have a valid solution. And if we repeat this for the square and the curly brackets, the exact same thing will happen again. So let's consider instead a nested version of our question. On the first iteration of our for loop, we're going to append this open bracket to our stack. And then again, our stack exists, but the element that we're currently iterating over in our hash map, which at this point is the open square bracket, is not in our hash map. So we can append it to our stack also. And just to be clear, let's add some quote marks around these brackets because they are strings. So on the next iteration of our for loop, we hit the if statement, our stack exists, and the element we're currently looking at, which is the closed square bracket, is in our hash map, and the rightmost or the last item in our stack is indeed equal to the value of the key that we use to look up in our hash map. So we can pop this square bracket off from our stack, and then we iterate along and repeat the same process with the last open bracket in our stack. And at the end, of course, we return not stack. Because for example, if we had one more bracket in here, we would append this into our stack. There would be no corresponding close bracket, so we know our solution is not valid, and that's why we return the opposite of our stack. If it has items inside, returning not of our stack will return false, and if it's empty, then returning not on our falsy value, which is the empty stack, will return true. So that's our solution. And another quick reminder in our notes that looking up in the dictionary checks the keys, which is this element in hash map. It's O of 1 lookup constant, and it's faster than using dict.keys, which in a sense creates a view of the keys and then requires O of n time to iterate and find the key that we're looking for. The time complexity is O of n because we're iterating over the string s that is passed in with this for loop. So if our string doubles, then the amount of operations we have to do doubles, either in our if or else statement with popping or appending. And of course, the space is also O of n because we have our stack, which we're keeping track of. If we have a valid solution, the stack could be n divided by 2, which also simplifies to O of n because every time we find a corresponding close bracket, we'll pop the open bracket off from our stack. But again, because of the simplification, it goes back down to O of n. And on top of that, we also have our hash map, but that's constant space, keeping track of the 3 bracket types the question tells us. And so that's it for our valid parentheses question. Next up, we have this question called evaluate reverse Polish notation. And if you're unfamiliar with what it is, the naming will have no meaning to you at all. But this is a nice question because I've seen it in university level education as a project, so it definitely holds some value. We are given an array of strings called tokens that represents an arithmetic expression in a reverse Polish notation. And the definition for that is a mathematical notation in which operators follow their operands. And we've already gone over operators and operands in questions before, as well as our software engineering material if you have that. But simply put, this notation gives 2 numbers and the operator afterwards. So 3 and 4 added together. So we want to evaluate the expression and return an integer that represents the value of that expression. So down here in our first example, we would do 2 and 1 added together to give us 3. And then we would take that value and the next 3, times them together and give ourselves 9. And we're given some notes here on the operators included in the question. The fact that our division won't leave us with any remainders, or there'll be no division by 0, for example. So just a bunch of notes to let us know that it's a clean question. And of course, it's in our stack section, so we're going to be using a stack to solve this. And so you should be able to give it a go. Otherwise, let's look at our solution. So here's our code, and it looks pretty simple. The first thing we're going to do is create our stack, and then we have our tokens from the first example. Then we're going to begin a for loop over each element in our tokens, starting off at the 2. And we have 2 main blocks inside our function. Our if block if it is a number, and our else block if it is an operator. So we check if the element that we're currently iterating over is not in our operators, and we know this is the finite set of operators given to us by the question. Then we can append it to our stack, making sure we convert it to an integer because it's given as a string. So we can add 2 to our stack. If we loop over to the 1, we'll do the same. One more loop and we've reached our operator. At this point, we pop off the last 2 items in our stack, 2 and 1, and we check which kind of operator it is using if and else statements. So nothing too complicated there. In this case, it is a plus sign, so we can append to our stack the addition of our left and right. The reason we add it back to our stack is because this new number will be the next operand in our calculation. So in this case, we'll append the addition of left and right, which gives us 3. So we continue our for loop, hit the 3, append it to our stack, loop again to the asterisk, and in our else block, we hit this else if statement and append to our stack the multiplication of our last 2 items inside the stack, giving us 9. At that point, we finished our for loop and we can return the last item in our stack, which will always be the only remaining item, giving us 9. So let's quickly take a more complicated question to see how this would work. So in example 3 in the question, we have multiple numbers followed by an operator, and it's best to see what this means by walking through the code. We would add each number to our stack as we loop through our for loop and hit the if block in each case. Then we would loop again and hit the addition sign. This would lead us to our else block and the very first if statement. In this case, we still pop off the last 2 items in our stack. 9 add 3 would give us 12, so we can add this back to our stack in this line here. Loop again to the -11 and add that to our stack. Loop again to the asterisk, and at this point we would be multiplying the last two items in our stack. That would give us -132. And you see the very next item in our tokens is another operator. So even though we were given several numbers here, the operators and operands would still balance out. It's just based on the input tokens and the order of operations the question is looking for. So at this point we would do 6 divided by -132. Our right being the -132 and the left being our 6. So we would take the item that went first in our stack and divide it by the last item in our stack, as we can see on this line. So the float of left divided by right, and we make it an integer, gives us 0. And this is based on the notes that the question gives us that the division between two integers always truncates towards 0. So 6 divided by -132 gives us this negative decimal number. If we take the integer of that, it gives us 0. So we can append 0 onto our stack. Move along in our token string. Of course, the multiplication of 10 and 0 will give us 0. Iterate along to the 17, add that onto our stack, add the last two items, that gives us 17, and iterate again, add the 5 to our stack and add it to the 17, and that gives us 22. And again, this question differs from the first in that we have multiple numbers in a row. So let's take a look at what this means mathematically. In reverse Polish notation, whenever we see an operation, we're taking the last two operands. So in this case, the 9 and the 3 are the last two numbers before we hit the addition. And that's why these are the innermost brackets, the very first operation that we do. Then we add the 11 to our stack before hitting the next operation, which is this multiplication. At that point, again, we take the last two numbers in our stack. That would be the result of this 9 and 3 addition multiplied by the -11 we've just added to our stack, giving us 12 times -11, the next most inner bracket in our calculation. And again, we hit a division, so we would just do the same. We would take this 6, which is the first of the last two items in our stack, and divide it by the result of the last two operations, which would be 6 divided by -132. And so hopefully that gives a bit more clarity into how reverse Polish notation works and how it connects mathematically. So it's a nice solution to a question which requires a bit of understanding about exactly what the question is looking for. Understanding reverse Polish notation might not be something that's easy to pick up if you've never seen it before, but if you understand the concept, then the question is not too difficult. So I guess it's a medium in terms of understanding exactly what this new concept is. And of course, our time complexity for this is of n, due to the fact that we have one pass over our token string. So the entire time complexity relies on the length of our tokens, and the number of operations increases linearly depending on our token's length. And similarly, our space will also be O of n due to the fact that, as you've seen in our token string just now, we can have multiple numbers passed in a row. So it's not always just two numbers in our stack. So theoretically, we could have n numbers passed into our stack, giving us n space. And so that's it for our evaluate reverse Polish notation question. So our last question in the stack section is this stack sorting question, and it's not actually a Leetcode question, but it's something I found very useful to help improve my skills. And it's pretty simple. All we have to do is take a stack of integers and sort them in ascending or descending order. So I leave that up to you. That's not the focus. It's simply the switching of a greater or less than sign. And what I'm going to do is give you this pseudocode, and pseudocode is just the description of an algorithm written in plain English. So this is the pseudocode that I'm giving you to complete this solution. So it should definitely be doable. Pause and give it a go. Otherwise, let's walk through the code. So here's our code on the left, and let's walk through it. Our input stack that is given in is just an array of numbers. In the question, we're told it's a stack, and also based on the pseudocode, we're going to use a temporary stack to sort our input stack. So the first thing we do is create our temporary stack, and then we begin our while loop. Pop off a number from our input stack. And don't forget, because these two data structures are stacks, we can only stick to stack operations. So for example, we can't append to the start of our stack, only the end. So popping from our stack gives us this 23. And while our temporary stack exists, and the last number in our temporary stack, which as we've seen in our stack data structure is similar to the top or peak function. If this number is less than our current number, then we do some operations. Well, right now there's nothing in our stack, so this while loop doesn't execute, and we go straight to appending our number to our temporary stack. Back at the top of our while loop, which is iterating across our input stack, we reassign num to be the next item we pop off from our stack. which is this 92. At this point, our temp stack does exist, and the last item in our temp stack is indeed less than the current number. So what we do here is add that last number back into our input stack and pop it off from our temporary stack. So we could have done this in one line by saying stack.append tempstack.pop, but it's all the same. So we add the 23 back in here, pop it off here. At this point, the while loop no longer executes because our temporary stack is empty, so we append the 92 to our temp stack. And you should kind of get a feel for where this algorithm is going now. We're simply using the input stack as a kind of placeholder for our numbers, while we make sure our temporary stack is in the correct order. So back at the top, we would reassign our number to be 23, pop it off from our input stack. Down here in the while loop, 92 is not less than 23, so we jump to the last line and append 23 to our temporary stack. One more while loop and our new number is 98. At this point, our temporary stack exists and the last number in our temporary stack is less than 98. So we remove this number from our temporary stack, add it to our input stack, and go back to the top of our while loop. At this point, the same is true. The last number in our temporary stack is less than our current number. So what we do is take this 92, add it back to our input stack, pop it off from our temporary stack, and then finally we'll break from this while loop and append the 98 to our temporary stack. So even though it looks like we've made no progress, back at the top of our while loop, the next number we pop will be the 92. Down here, we know for sure, because we've just popped off this 92 due to the fact that it's less than our 98, this while loop is not going to execute and we can append 92 back to our temporary stack. At this point, the same is going to be true for the 23. Because before we iterated to the 98 in our main for loop, our temporary stack was in correct order, so we don't have to enter this while loop again. And now we can add the 23, popping it off from our input stack. And so hopefully you should get the gist of this stack sorting method. And it's always good when you can tell exactly what's going to happen without walking through the code line by line. And that's how you know you've understood the algorithm. So I can tell, for example, we're going to pop this 31 off. I know the 31 is greater than the 23, so we're going to pop this 23 off, add it back to the input stack, exit out of this while loop, and add the 31 to this temporary stack, so things will look like this. So I'm sure you get it by now, and if you don't, play around with the code and continue to walk through the algorithm. And so originally we said ascending or descending order. If you want to change it, the only thing you need to do is flip this sign around. Right now we're checking if the last item in our temporary stack is smaller than the current number that's being passed in. And if it is, we know we need to make some changes because we're giving our temporary stack in descending order. So that's it for our solution. On the left is the temporary stack solution we've just walked through. That's our iterative solution, and on the right we have our recursive solution. If you want to give the recursive solution on the right a go, definitely do, because it will help in the long term even though it's something that might not be asked in an interview. And the time complexity for this, I'm sure you've guessed it, is O of n squared. We have a nested while loop. The outer while loop iterates across our input stack of n elements, and for each n element, our inner while loop iterates across our temporary stack to find the correct position. So in the worst case, it will run n times. So for example, if our input stack is given in descending order and we want to return the answer also in descending order, every time we add an item into our temporary stack, the next item along is going to be bigger. In that case, every time we're going to hit the while loop, add the numbers back to our input stack, and repeat the process to make sure the biggest number is first, giving us n squared, n operations in the inner while loop for n items in the outer while loop. And our space is of course O of n. We have our number variable, which is constant, it's always going to hold one element, and our temporary stack, which in the worst case at the end of the algorithm, for example, will hold all n elements. So that's it for our stack sorting question. So we're on to our next section, which is queues, and this section is not too long because we've gone over a bunch of queues and their different operations in the data structures video. Regular queues, double-ended queues, priority queues, and in my opinion, if you've done your practice with stacks and similar data structures like arrays, then if you are asked a question on queues which you've not covered, the knowledge you already have should definitely be easily applicable. And so our first question is a nice segue into the queues section. We are asked to implement a stack using a queue. So we'll take the queue data structure and create a stack. And of course, this question focuses on the main difference between the two. A queue is first in, first out, and a stack is last in, first out. And the question tells us to implement this last in, first out stack using only or up to 2 queues. Our solution will only use one queue, a double-ended queue. And it should have all of the functions that we've seen before. Push, top, pop, and empty, which is just an empty check. And you see in the notes, it specifies that we can only use the standard operations of a queue. This means pushing to the back of a queue and popping from the front. Also, depending on your language, the queue may not be supported natively. We are using Python, so we can use the deck class. That's this one here. Inside the Leetcode editor, you won't need to import this. Outside in your local code editor, however, you may need to import the deck from the collections module. So in our initialization, we would create something like a stack and set it to be equal to our deck. which is our double-ended queue. So given that I've told you that, go ahead and give the question a go. It should be fairly easy. Otherwise, let's take a look at the solution. So here's our code on the left. Pretty basic. We have our queue, which we initialize in our initialization function. To push into our queue, which is acting as a stack, we simply use append. So let's imagine this is our queue, this is the front, and this is the back. If we want to push onto our stack, we simply append it onto the back. This is the same for a queue, so not much changes there. If we want to pop from our stack, now we need to do something different. So we're going to begin a for loop in the range of the length of our queue minus 1. Minus 1 because that's the last item that we want to pop. So let's imagine we have 4 items in our queue, and we begin a for loop in the range of the length of our queue, which is 4 minus 1, which is 3. That gives us a for loop in the range of 3. So we begin at the first element, and let's see what we do. We use pop left because in our queue we're popping from the front, first in, first out. So we're allowed to use this operation as the question tells us. So we take this one and we use the push function to add it to the back of our queue. We do this 2 more times because our for loop is in the range 3. So we will take 2, add it to the back, take 3, add it to the back, and our for loop has now finished. So we can pop from the front of our queue using the deck function pop left to remove this 4. And there's our queue updated, working as a stack. If we had a stack and our 4 was at the back, we would simply pop it off the end, last in, first out. Our peak or top function, as the question calls it, is simple. We just return the last item in our queue without popping it off. And of course, to check if our queue or stack is empty, we just check if the length is equal to 0. So nice and simple. Each function is of course constant time complexity except for our pop, which is O of n. And space is of course O of n because we're keeping our deck with n elements. And down here we just have a note on the queue module in Python, which typically if you're in an interview you'll be asked to write the data structures from scratch, but in case it's just a reference to the queue module in Python. So for example, you would import your queue and you'd use it to create a queue like this. So if you're interested in playing around with this module and the deck a bit more, I'd definitely recommend giving it a go. Anyway, that's it for our first question in the queue section. Next up, we have this time needed to buy tickets question. And I really like this question because the answer can be so simple if you figure it out. No clever coding tricks needed, just pure logic and problem solving. Definitely try this one out because even if you don't get it or you get a suboptimal brute force solution, seeing the linear solution will be a nice light bulb moment. The question is a bit of a boast, but essentially we are given this array of integers called tickets. The array represents people in a queue, and each person I, so the person at the ith index, wants to buy that position's value in number of tickets. So person at the index 0 or the first person in the queue wants 2 tickets. The second person in the queue or the person at the first index wants 3 tickets. Each person can only buy 1 ticket at a time, and this ticket buying transaction takes 1 imaginary second. Once the person buys their ticket, they go to the back of the queue and have to queue up again to buy their ticket. And you see, we can handle this queuing by minusing 1 from everyone's ticket value per pass. The question wants us to return the time it takes for a given index k to finish buying their tickets. So that's the question. The brute force should be relatively easy to get, and if you want to hint at the 1-pass linear solution, I'd suggest revisiting your notes on the minimum time to visit all points question in our array section. It's not an exact copy of the solution, but the idea behind it is similar. So pause now if you want to give it a go, otherwise let's get into the code. Here on the left is the brute force solution, quadratic in time, but let's instead focus on our linear solution. We have a single for loop iterating over the length of our queue tickets, and we split the logic into 2 parts, every person before k and every person after k. For every person before k, if they want to buy less tickets than k, then we know we can add their exact amount of tickets to the time. 1 ticket purchase is 1 second. So for example, we would add 2 and 2 to our result because it's less than our amount of tickets at index k. This is because these people before k will finish buying their tickets while k still has tickets to buy. When they finish, they will not take up any more time. So for example, after 1 iteration of our queue tickets, the values will be 1, 1, 4, 1. That's 1 second for each 4 seconds. 1 more iteration and we have 0, 0, 3, 0. 1 more second for everyone, and that's 8 seconds. After that, the first 2 values are both 0. So because they had less tickets to buy, we would add the exact amount of tickets that they had to buy, which is equal to the number of seconds. If instead they wanted to buy more tickets than k, then we know we can add the amount of tickets or time it will take k to buy their tickets. This is because they will each take up 1 second until k has finished buying their tickets and we can stop. So for example, after 1 iteration, we will have 4, 4, 1, 1. On the second iteration, we will have 3, 3, 0, and the algorithm can stop. Notice how the first 2 took the exact amount of time that k took. and the algorithm will stop there. So in that case, we can add the amount of time or tickets that it will take K to buy their tickets. Now, it's the exact same concept for the people after K. If they want to buy less tickets, we know they will finish buying before K and go to 0, so we can simply add the amount of time it takes for them to finish buying their tickets. But the only difference here is if they want to buy more tickets than K. In that case, we will still add K's time to buy, but we minus 1. We minus 1 because the question asks for the time for K to finish, and at that point the algorithm finishes, and of course we don't need to count any more time. For example, if this was our input, after one pass, the amount of tickets left would be 1 and 2. One more pass and we would have 0 at K. You see how we added K's time minus 1 for the second person. And it's of course O of n time because we are iterating our tickets queue to find out each person's time. And space is constant, one variable, which is our result. And so that's our solution to this nice little logical problem, time needed to buy tickets. Our final queues question is perfect to wrap up our understanding, as it focuses on the principal difference between queues and stacks. And remember, working with a queue is pretty similar to working with a stack, except for that key operational difference in the order of removing elements from the date structure. So the style of stack and queue questions will not differ too much, and the decision on which to use depends on what we're trying to achieve in the question, which this question is a perfect example of. It's a simple question. We want to reverse the first K elements of a given queue. So if we have a queue of 10 items and we are given an integer K, we want to reverse the first K items in that queue. And you can do this however, but the point here is to try and use a stack to solidify our understanding of the two date structures. Remember, you can only use the functionality of that structure, so removing from the front of a queue for example, and popping off the top of a stack. You can implement your queue however you like, import a queue or a deck, or write it from scratch if you want to test yourself. So give it a go now, otherwise let's take a look at the code. I've given two solutions here. One uses a queue imported from the queue module, and one uses the deck from the collections module. The code is identical except for the differences in the functions of each of these classes. Let's focus on the deck example because it's iterable, which makes our life a little bit easier. This just means we can iterate over it, for example using the len function, whereas for the queue we would have to use the given function queue size. For this reason, I think you will often be allowed to use a deck unless asked to create the queue from scratch, using an array for example. But that's fine because we've done plenty of that in our data structures work. So we're going to use a deck and treat it as a queue. And we're also going to use our stack, which we create an empty array to represent our stack. And we append onto our stack the first K items from our queue, using pop left to remove from the front of our queue. So after the first of our 3 loops, this is what we have. Then we hit the second loop, where we use the fact a stack is last in first out to pop the items from the stack and append them back onto our queue. So we have the items added back onto our queue in reverse order, except now they are no longer the first K elements. They come after n elements in our queue. So we correct that with our third and final loop, where as we saw in the first question of this section, we can pop the items off the front of our queue and push them back into that same queue. After that, all that's left to do is to return our queue. Our time complexity is O of n due to our third loop. If our queue was 1000 items long and we are reversing a K of 3 items, then the final operation of popping the 1000 items from our queue and adding them back is the bottleneck. K can never be bigger than n, so this final operation is what gives us our O of n. And space is O of k. After the first for loop, we are keeping K items in our stack. The queue is already given to us, so we're not factoring that in. And so that's it for our question reversing the first K elements of a queue, and our queue section altogether. Our next section is binary trees, and a quick reminder that a binary tree is a tree data structure in which each node has a maximum of 2 children, the left and right child, not to be confused with binary search trees, which is our next section. And a binary search tree has some rules about the values of the nodes. A lot of questions in this section will focus on the searching techniques breadth and depth first search. Go back and take a look at the data structures video to remind yourself how these work. For example, when to use the queue and stack for which traversal. And let's have another quick reminder on the types of binary trees. A leaf node is a node with no children, so these last nodes. A full binary tree is one where every node other than the leaf nodes have 2 children. A complete binary tree has all levels fully filled where the last level can be filled or not. A degenerate tree is one where each parent node has only 1 child node. A perfect binary tree is one where all nodes have 2 children except for the leaf nodes, and the leaf nodes are all at the same depth level. And finally, a balanced tree is one where the absolute difference of the heights of the left and right subtrees at any node do not differ by more than 1. So with all that in mind, let's get into our first question. Average levels of a binary tree is our first question in the binary trees section. question. We are given the root of a binary tree and we are asked to return the average value of the nodes on each level in the form of an array. Answers within 10 to the power of -5 of the actual answer will be accepted. We have this tolerance to handle minor deviations that arise from floating point arithmetic. Without getting into the details too much, as we've seen, computers use the binary system base 2 to represent all data, including numbers. In binary, only 2 digits are used, 0 and 1. So when it comes to storing decimals, there are some approximations. So that's the question, and we see we have the tree node class, which is identical to the tree nodes we were working with in our data structures. So let's take a look at how we can work this out. Here is the code, and get used to this pattern for these tree questions, because you'll be seeing it often. This code performs breadth first search. That's why I've added this orange badge here to remind us which one we're using, breadth or depth. Most of these tree questions will involve depth or breadth first search, which, as the note tells us, is better coded out using stacks and queues over recursive, because it better demonstrates our practice and understanding of data structures. And we know, of course, this question will use breadth first search because we want the average value per level, so we want to evaluate each level at a time. So we begin by initializing our queue using a deck, and inside we give it the root node. Breadth first search, we use a queue. Depth first search, we use a stack. Why? Well, because a queue means we traverse all nodes in the same level before going to the next level, by nature of the way we pop items first in, first out. We then also create our results array, which we will return at the end. And then we begin a while loop, which will iterate over the entire tree of n elements. We continue looping as long as our queue exists, because every time we reach a node, we check its children and add them to the back of the queue. So at the end of the traversal, there will be no more tree nodes in our queue, and we know we've finished. Inside our loop, we want to process our tree level by level, so we create our level array, and we begin a for loop which iterates over all nodes in the current level. And at this point, I think it will be better to walk through the code to see why this works. At the start, we receive our root node. One element in our queue gives us a for loop in the range of 1. So we pop this node from our queue and append it to our level array. Then the key here is we append onto the queue the children of this node. And so what will happen at each level, remember one for loop is one level, is that each node will have its children added to the queue ready for the next level. So on the next iteration of our while loop, when we take the length of our queue in the for loop, we will for sure have the exact number of nodes at that next level. In this case, we add the 9 and the 20 node to our queue. Our for loop finishes, and we add to the results array the average value of the nodes at that current level, which is 3 at the root. And then we would just repeat the same procedure with the next level. A for loop in the range of 2, because we have 2 items in our queue. Pop the 9 off, add it to our level array, which we reset to empty at the top of our while loop. And then we would add 9's children to the queue, 15 and 7. Pop the 20 off and add it to our level array. No children, so next our for loop finishes and we calculate the average of 9 and 20 in our level array and add it to our result. The time complexity for this is of course O of n. Our search is iterating across the entire tree to calculate the average at each level, and space is also O of n. Remember, we want the worst case. Let's think of the last level in a perfect tree. The last level will have exactly half the nodes of the tree, and we know O of n divided by 2 simplifies to O of n. So there's our solution for calculating the average value of nodes per level in a tree. A nice intro to walk through in our trees section, setting us up to answer later questions with more ease. Our next question tasks us with finding the minimum depth of a binary tree. Pretty basic question, so shouldn't take too long. Even though we are asked to find the depth, don't be misled into using depth first search. We want the minimum depth, so instead of using depth first search and potentially wasting a lot of time exploring a very long subtree before moving on to the next subtree, it might be preferable to use breadth first search, where we can terminate the algorithm as soon as we find the first leaf node. So let's see how to implement this. Here are 3 solutions. Our recursive, give this one a go if you want to practice and expand your skills. Otherwise, for now, we'll stick to the iterative. And typically, we use a while loop for these breadth first search patterns. To me, it's cleaner, and it helps us stick to one framework, making it more memorable. But the for loop version is there to help us understand that we can approach it differently and see how that's done. So, for the while loop version, we're going to accept the root node as always, return a minimum level depth of 0 if our root is null as an edge case, create our queue which will contain tuples of the node and the current level. So we begin with the root and a level of 1. So for each node in our breadth first search, we're going to check its children and add them along with their current level plus 1 to our queue. The first node we reach with no children, we know for certain we have found our minimum depth because we are searching each level at a time. So fairly simple, and I don't think we need to walk through the code here, but let's quickly see the first example. We begin with our queue of 3 as the root and the level of 1. Inside our while loop, we pop off this 3 node and the level 1, check its children, add the 9 node plus 1 to the level into our queue, so that gives us a tuple of 9 and 2, and do the same for the 20 node. On the next iteration of our while loop, we pop off the 9 node along with the level value of 2. We check and see that it has no children and return the level of 2. The time complexity for this is of course O of n. Our breadth first search processes each node, and in the worst case we process all n nodes. Space is also O of n, as again at the very last level of our search in a complete tree we would have up to n divided by 2 nodes, which simplifies to O of n. And so there's our solution to finding the minimum depth. And as we've seen this tree search pattern twice now, as well as in our data structures, we should be able to reuse it relatively easily when facing the rest of these questions. Naturally, our next question after finding the minimum depth is to try and find the maximum depth. Now the solution is going to be very similar to the previous question except for a couple of lines. So definitely pause and give this one a go. The left side solution shows us our remix of the previous question, where everything is identical except for our condition upon which we finish our algorithm. Instead of returning as soon as we find a leaf node, we want to keep going until the queue is empty, because we know at that point we've traversed our entire tree and processed every node at every level. And the last node will for certain be on the last level, because we are traversing in level order, so we can return that last node's level. Because this solution was relatively easy due to the previous question setting us up nicely, let's instead take a look at the recursive solution. We have 2 ways of doing our recursive solution. Both are valid and essentially do the exact same thing. The second solution is just written out in more depth to make it easier to follow, and it also follows the same patterns we saw in our data structures. But let's take a look at the more concise recursive solution for now. And if you're having trouble catching on, then you can walk through the more detailed version. In one sentence, what we want to do is recursively compare the left and right subtrees at each node to find the maximum, adding 1 at each depth level. You see, we begin by calling max depth on the root node. From there, we want to find the maximum value of the 2 children. We do this by taking the max of the max depth of the left child and the max depth of the right child. And at each level, we plus 1, representing the current level. So this plus 1 represents the root level 3 node. On the left side, we take the max depth of 9. Again, we take the max of the 2 children. 9 has no children, so for both function calls, we hit our recursive base case and the max depth call will return 0. We add 1 to account for the 9 nodes level, and so 1 will be returned back up to this max calculation, and that's the left side of our subtree. On the right side, we do the exact same thing on the node 20. We take the max depth of the left and right child. Max depth of 7 will return 1, because it has no children, and the 1 comes from adding 1 to account for the 7's level. On the left side, I've added the 4 so we can see exactly how it works when we have uneven levels. We take the max depth of the 4 node and the max depth of the right child, which is none. This will give us 0. On the left side, calling the max depth on the 4 node will return 1. So the max between 1, which is returned from max depth on the 4 node, and 0, returned from max depth on none, will take a max of 1, add 1 to it, and return 2 as the answer to our max depth on the 15 node. The max between 2 and 1 is 2, we add 1 to that and return 3. And finally, the max between 1 and 3, we take 3 and add 1 to it for the root level node, giving us a maximum depth level of 4. 1, 2, 3, 4. And so that's our recursive solution. And the complexity in both cases for time and space is O of n. For the time complexity, we are iterating over n elements in both cases. For the space, in the iterative case, we need n space for our queue, and in the recursive solution, we need n space for our call stack. In the worst case, equal to the maximum height of our tree. And so that's how we find the maximum depth of a binary tree. Okay, so our next question is not directly a Leetcode question, but more of a core operation you should know, and it could easily be part of another bigger scoped question. We should know how to find the max and min node in a binary tree. Remember, a binary tree is not ordered in value like a binary search tree, so the solution is not as simple as going to the end of our right and left subtrees. We need to traverse all the nodes. So give this a go because it shouldn't take too long. Here is our code. It's pretty simple. We're going to do a breadth first search over our binary tree, again using a queue and again using a while loop conditional on the existence of this queue. So the pattern is again the same. This time, however, we're going to keep track of our max value node. We can set it to 0 for the sake of this example, but of course if we had a question, we need to be careful about the constraints, because this could ruin our solution. For example, if all the values in the tree were negative. So we initialize this outside of our while loop to keep track of the max node, perform our search as standard, adding children nodes to the tree, and performing a check at the end to update our max value. Of course, if we wanted the minimum value, we would just change this to be a less than sign. It's O of n time because we are traversing all the nodes, and O of n space for our queue. A nice and easy one there for finding the min and max values. Next up, we want to perform a level order traversal and return the nodes in that order. That's our question. Level order simply means breadth first search. Here, as we see in the example, we're printing 3, 9 and 20, and 15 and 7. This is different from the traversals we have seen in the data structures practice, like in order, pre and post order. The question here wants us to return each level in a separate array. And if you want a hint, you will remember that we worked with levels before in the average node value per level question, so we can use some ideas from there. So there's a couple things going on here, and it's marked as a medium, but I definitely think it's doable. We are just performing breadth first search, as we have seen a few times now, and printing the nodes at each level in separate arrays. So definitely pause now and try to give this one a go off memory. Otherwise, let's take a look at our solution. As always, the same setup for our search, and again a pretty similar solution to our average node value per level question. We begin by taking care of the edge case, which is an empty tree. In that situation, we just return an empty array. If we do have a root, we initialize our queue using a deck and our tree list that we will return at the end. We begin a while loop, and inside we create our level array, which we will add all the nodes from the current level to. We do this inside the loop to reset it to an empty array at the beginning of each new level. Then we begin a for loop in the range of our queue. We know our queue will hold the exact number of nodes at the current depth level because inside our loop we append all the children of the current nodes. So for example, at the root node we append 9 and 20. But first, of course, we append the current node's value to our level array. After that, we append the level array to our tree, and we begin our while loop all over again, resetting our level list to be empty. So let's quickly walk through one more level in our tree. Our for loop will be in the range of 2, because we have two nodes, 9 and 20. So it will execute twice, I being 0 and 1, but we don't need to use the loop index this time. We pop off the 9, append it to our level array. It has no children, so we iterate to the next node, which is the 20, append the 20 to the level array, add both its children to our queue. At that point, the for loop has finished, so we append our level array to the tree and move on to the next level. And no doubt, I'm sure you've guessed it, O of n for both space and time. We are once more iterating over all the elements and storing them in our queue. But this time, it will be our tree array that will take up more space towards the end of the solution when it contains all n elements. And so that's how we traverse in level order and return each level in an individual array. A good question to see if you're getting the hang of breadth first searching over trees, especially given all the previous questions we have answered, wrapping up nicely before our first depth first search question. This next question, same tree, gives us the root nodes p and q of two different trees, and we are asked to return true if they are identical, meaning the same value for all the nodes in all the same places. Give it a go now, otherwise I will tell you a few hints. Same tree is our first binary tree question, which we're going to answer with depth first search, although it's definitely doable with breadth first search. Implementing depth first search iteratively follows the exact same pattern as the iterative breadth first search implementation, although we initialize a stack instead of a queue. It's a fairly straightforward question, and one final hint is not to confuse your left and rights. Take a look at example 2. It's not identical because the root nodes have a different left and right child. So let's take a look at our solution now. As we mentioned before, a very similar pattern to our breadth first search. We begin by initializing our stack, and typically we add the root node. Depending on the question, of course, we might add something different or some extra information. In this case, we're adding both root nodes. And just a quick note is that you should start to see the point of going through these questions with a very similar answer pattern. It's to understand the core problem solving pattern and be able to notice how we can manipulate our pattern to achieve a working solution. So in this case, we've seen a similar approach before, for example when we added the tuple of the node and the level to our data structure. So this time we can extrapolate that knowledge and add a tuple of both root nodes to our stack. We pop them off and then compare at each level whether they are equal. And then of course we add their children to the stack to repeat the process. Let's quickly walk through a false solution to see why these statements are required, because with identical trees we won't get to see exactly how this works. So in example 3, we append both root nodes with value 1 to our stack. We pop them off, both of them exist, so this if statement doesn't execute, neither of them are none, and 1 is equal to 1, so we don't return false. In that case, we can append their children. The reason is, if both nodes are none, both don't exist. For example, at a leaf node, we might append none for the left and right child. So in that case, if both nodes don't exist, it's okay to continue with our solution because this is identical on both trees. However, if this if statement does not execute, we know either node 1 or node 2 has some value. In that case, if either node 1 or node 2 is none, then we know one node is none and one node has a value. So we can return false because this is not identical. And finally, if both nodes exist but the values are not equal, of course we can return false. In this example though, we take the children of the root nodes and add them back to the stack. Whichever node we append second will be first to pop off. Remember the fundamental rule of a stack, last in, first out. And that will be the subtree we fully search first. So in this case, we've appended the right children, the 1 and the 2, in a tuple, and the left children, the 2 and the 1 in another tuple. We pop off last in first out, so the 2 and the 1, and the values are not equal, so we return false. So that's our solution, nothing too complex. Time is O of n, linear, because we have one loop traversing all the nodes in the tree. Worst case, for identical trees, we process all n nodes of both trees, giving us O of 2n, which simplifies to O of n. Space is O of n or O of h, where h represents the height of the tree, or in other words, the maximum height of a subtree, because we go all the way down our subtree in depth first search. For example, here on the left, we will continue appending and searching down the left subtree, so we will initialize our stack with the root nodes 1, and then in our depth first search, we will then search the 2 nodes, then the 3 nodes, then the 4 nodes, before going all the way back to the 12 node. And at the last point of the maximum height of the subtree, we would have O of h space used in our stack. We can still call it O of n, because if we had a degenerate tree, for example, one single subtree with 1,000 nodes, our space is n. H at most can be equal to n, and so that completes our solution for checking if two binary trees are identical. Our next binary trees question is path sum, and this is a cool one because on a very high level it reminds me of pathfinding in applications like Google or Apple Maps. Given the root of a binary tree and an integer target, return true if the tree has a root to leaf path such that adding up all the values along the way equals our target integer. So in our real world maps example, this could be a case where each node is a checkpoint like some junction and our leaf node is our destination. Of course, this is a very high level comparison. You wouldn't want any leaf node destination, but it's a cool comparison to make and remind ourselves that these are not just frivolous questions, but we are learning skills. So give it a go now, otherwise let's take a look at our solution. We immediately take care of our edge case and return false if there is no root node. Don't forget your edge cases, very important. Next is our standard procedure, and based on the question we decide to add our root and the value of the root in a tuple and put this in our stack as the initialization. You might think, but wait, the value is accessible via the node anyway, but there is a reason for appending it to the stack that we will see later. Inside our while loop, as always, we're popping off the values from our stack, and the first of our conditional if checks is to identify if we have reached the end of our algorithm. This is a common pattern you will see if you haven't noticed by now. We typically check if our algorithm has finished as the first thing. For example, in our edge case at the top, as well as inside our while loop, we check if the algorithm has finished before continuing to add the children to the stack. The reason is it's more efficient, and oftentimes the operations that come after could render our successful case unsuccessful. So we check if our node is a leaf node. If it is, and the value is equal to our target sum, well, that's everything we need, so we can finish and return true. But so far we've only added the value of the current root node, and we want the total path sum. So let's see where that's coming from when we continue to traverse our tree. So if our success case conditional check is not true, then we check for both children whether they exist. If they do, we add to the stack that child node and its value plus the current value. From the root, we have only one way to reach any node. This is not a graph, so it makes our solution much easier. It means we can append at each stage the current value plus the sum of the values so far. And that's why if one subtree does not evaluate successfully, we can continue our depth first search to a different node on a different level or on a different side of the subtree, and the next node we pop off will still have the correct value. For example, popping off the 2 after the 7 does not evaluate successfully, the path up until either the 7 or the 2 has been the same, giving us the same sum value so far. And we will see this in the example we walk through right now. So here's our first example, and we begin at 5 and our target is 22. We initialize our stack with the root node object and its value 5. We pop these off and we check if it's a leaf node and we've reached our target sum. It's not true, indicated by this red X, so we append onto our stack the children of the root 5 node. In the second iteration of our while loop, we repeat the same process, popping off the node 4 and its value 9. It's not a leaf node, so we continue, adding its children, which is just the 11 node. In the third iteration of our while loop, we pop off that node 11 that we just added, last in first out, and the value which we've been accumulating, which is now equal to 20. It's still not a leaf node, so we continue, adding the children of 11 to our stack. At that point, we've added the 2 node and the 7 node. We pop off the 7 node. It is a leaf node, but our current value is not equal to our target sum. And at this point, as we mentioned earlier, we can check a different traversal path and the value will still be correct. So when we pop off the 2 node and a target value of 22, we've reached the end of our algorithm. At the 7 node, you might wonder, well, if we go bust, meaning we go over our target sum, why don't we just stop the evaluation of that subtree? And we could, looking at this example here. However, the constraints of the question tell us that we can have negative value nodes. So if we want a complete solution, it's mandatory for us to continue our evaluation and let it do its thing. As with most of these questions in this section, we're using the same high-level algorithm, giving us O of n time to check every node in the worst case, and O of n space for our stack to store our nodes. And so that's our path sum solution. Diameter of a binary tree. This question wants us to find the longest possible path between any two nodes in our binary tree, given the root node. For example, in the first tree we are shown, the longest path is from node 4 to node 3, giving us a diameter of 3. You can think of it as the number of links if that helps. 1, 2, 3. And this is a rare case where the recursive solution might be easier to understand than the iterative. Let's take a look at both solutions now. And just a quick note on what both solutions have in common. Both are performing depth-first search to process each node, and at each node we are calculating the maximum diameter found by considering the sum of the left and right subtrees. In the iterative solution we have a few extra steps to find these depths. In the recursive solution, the depths are returned back up the call stack. And once we have the depths at each node, we can calculate the maximum, updating our global tracker to make sure that we always have the max. For the iterative, it's a good solution to go through because we are using multiple data structures. One of those questions that you might need to sit down with, draw it out, and spend some time figuring things out by yourself. We begin with our initialization, a stack to maintain our nodes for searching, each with a boolean indicating whether it's been visited yet or not, a dictionary to maintain the max height of each node's subtree. So from that node, how high is the subtree? How many more nodes exist further down? And our global diameter, which is set to 0. The second section is our iterative depth first search. For each node, if it's not been visited yet, we push it back onto the stack as visited, so we're visiting each node twice. We also append its unvisited children. If the node has been visited, the heights of the left and right subtrees are taken from the dictionary, or we set them to 0 if it's a leaf node. Then we update the diameter based on the maximum of the current diameter and the sum of the left and right subtrees, and we also calculate the max height and store it in the dictionary. That's the code. Intuitively, it works because for the traversal, each node is visited twice, once to explore its children and a second time to calculate the heights of the subtrees. The way we push nodes onto the stack means that a node is only revisited after its children and their subtree heights have already been processed. That way we can retrieve them from the dictionary and do our calculations. The diameter of the tree at any node is defined as the sum of the heights of its left and right subtrees, which makes sense based on the question, ensuring we capture the longest path. So for example, at the root node, the max of the left subtree is 2 and the max of the right is 1. Add that together and we get a diameter of 3. Each time a node is revisited, the potential diameter, the left and right subtree sum, is calculated and compared to the max. This makes sure we always have the max diameter. We also store the max subtree height of the current node so we can use this later when checking for a new max diameter. We calculate this as the max height of its left or right subtree plus 1 to account for the current node. If there is no children, this will equal 1, and so that will eventually accumulate as we bubble up our tree to get the subtree height. So that's the code and our description. It might be easier to follow when we look at how it works iteratively, and there's a lot going on here. I'm not going to go through this step by step, but pause and have a look. You can see that every time we pop off a node and it's not been visited, we add it back on as true and the children nodes as false. When we pop off a node that has been visited, we can calculate the heights and the diameter. In this case, for the node 3, it has no children, so we know the heights of its subtrees will be 0 and the max diameter will stay at 0. But we add to our max heights dictionary the 3 node plus the 1 to account for the node itself. And we continue iterating all the way until we've processed every node twice. At the end, we know for certain we have the max diameter, and you can see our dictionary is complete. There are no more nodes in the stack, so we can break and return the diameter. That's our iterative solution. Let's now compare this to our recursive solution. We have the code which firstly calls depth. Depth is our helper function that will calculate the depth of the tree by recursively calling itself and simultaneously updating the diameter. As for any recursive solution, we have our base case. For this solution, it's when the node being passed in does not exist and we return 0. If the node does exist, we recursively calculate the subtree height by calling depth on the left and right children. This will return to us the subtree height. Similar to our iterative solution, we take the max of the left and right subtrees. If the node exists, the subtree height starts at 1. If it is a leaf node, these will both be 0 and we plus 1. This will account for the current node. For example, like the node 4, the depth function calls on the 2 children will return 0, as we see down here. 4 itself does exist, so taking the max of the left and right depth, which are both 0, and adding 1 to it we'll return 1, and we will keep adding 1 to this value for each depth level as we search. For calculating the diameter, we take the max of the current diameter versus the sum of the left and right subtrees. Again, this works because the longest path at any node is of course the height or the depth of the left subtree plus the same for the right subtree. For example, the longest diameter or path at node 2 is the depth of the left subtree, which is 1, plus the depth of the right subtree, which is also 1, giving us a diameter of 2. So for example, at the 4 node, when we calculate the diameter, it's currently 0, the left and right depth are both 0, so the diameter is still 0, and that makes sense, there are no children. At the 2 node, when we calculate the diameter, we take the max of 0 plus the sum of the left and right depths. This updates the diameter to be 2, and that also makes sense. At the 4 node, we only have 2 children, giving us a diameter of 2, each child returning a depth value of 1. So calculating the max diameter at each node will let us keep track of the max diameter variable for our longest path, which when the recursive calls finish will be returned. And so that's our recursive solution. Both solutions are O of n time and space. For the iterative solution, time is O of 2n as we process each node twice, first unvisited and then the second time visited. But this simplifies to O of n, and space is O of n for the stack and the dictionary. For the recursive, time complexity is O of n. We need to visit each node once, and space is O of n, where n is the max height of the tree, when our recursive call stack is at its maximum. For example, when calculating the children of node 4. This time, in my opinion, I think the recursive is a better solution. It's cleaner, easier to follow, and more efficient. But of course, choose the solution that you like the most. And so that concludes our diameter question. Our penultimate binary trees question asks us to invert a binary tree. And this is one you might often hear people talk about or make jokes on for it being a difficult question and very different to the actual work you do as an engineer or developer. For example, if you were an engineer and you'd not done any data structures or algorithm practice, you might feel anxious because the question sounds a bit difficult. But now we've done all the previous work up until this point, you'll find this surprisingly easy. We're given the root and we want to invert the tree. After that, we return the same root. Pretty straightforward, especially compared to the last question. I'll give one more hint in a second, otherwise you can pause now. Inverting the tree in this case is vertical because we are swapping each node's left and right child. At every single node in the tree, the right subtree becomes the left subtree and vice versa. So that should tell you a bit about the operations that you're going to have to carry out. So let's now take a look at how we do this. 7 lines, that's all it takes. We initialize our stack with the root for a depth first search traversal, nothing new there. For this question, the breadth first search solution is pretty much identical apart from the use of a queue of course. For this solution however, we iterate over the stack, popping the nodes off and at each point swapping around the left and right child. We then extend onto our stack the pair of the children. And there's 2 things here. We could have explicitly checked if the children exist before pushing them onto our stack. So in this case, if we reach a leaf node, we're pushing none onto the stack. But it's okay because straight after we pop, we check if that current node exists anyway, so there's not much issue there. And secondly, we're adding both children at once, so we use extend. The extend operation means we're not adding the array into the original list. For example, when we extend the list with the 4 and 5 using extend, the elements inside the array are added onto the original array. But when we call append, we'll be adding on the entire object itself. And so that's pretty much it for our solution. We'll continue to process the entire tree, swapping children at each stage. Nice and simple. The recursive solution is also there if you want to give it a go, and an example of horizontal versus vertical inversion. Time complexity is O of n, iterating across every node, and O of n space for our stack. And so that's how you invert a binary tree. Our last binary trees question is another medium called lowest common ancestor. This will be a nice challenge for our final question. Given a binary tree, find the lowest common ancestor of 2 given nodes in the tree, where the lowest common ancestor is defined as the lowest node in the tree that has the given nodes P and Q as the descendants. Simply put, this is the lowest common parent. So in this example 1, the lowest common ancestor of 6 and 4 will be the node 5. The lowest common ancestor of 2 and 8 will be the root node 3. And we also have a special case where we allow a node to be a descendant of itself. So the lowest common ancestor of 8 and 1 will be 1. So let's take a look at our solution. There's a lot going on here, but don't worry, we're going to go through everything. Again, we have our 2 solutions, iterative and recursive. To switch things up a bit and make sure we fully understand depth and breadth first search, our iterative solution on the right will use breadth first search, and our recursive will use depth first search. As an opportunity to truly master binary tree searching, try implementing the opposite search pattern for each solution here. Let's first walk through the iterative. Here's our code, and on a high level level, let's explain what's happening before we get into the action. We have our queue to maintain our nodes for a search traversal, our parent dictionary. This will contain a map of each node's parent, the key being the node, the value being the parent. For example, on the end here, we have the 8 node and the parent 1. This will come in handy towards the end. Our first while loop is our traversal over all the nodes in the tree. During this, we populate our parent dictionary until it contains both the nodes that we are looking for, P and Q. At this point, we know we have all the information we need to find the lowest common ancestor. We've traversed and found both the nodes P and Q, and we have our dictionary of all the nodes and their parents that we passed on our path for P and Q. So we stop our traversal by breaking from our first while loop. No need to search any more nodes. And before getting into the second section, I think we should walk through the code up until this part. As you see here, we have our queue initialized with the root node and the parent dictionary with the root node and a parent of none. On the first iteration of our while loop, we add 3's children 5 and 1 and update the dictionary. On the second iteration, we're doing a breadth first search, so we pop from the front of the queue, taking the 5 node, adding 5's children 6 and 2, updating the dictionary, and we do the same with the 1 node, the same with the 6 node, and the same with the 2 node. At this point, the final if check in our first while loop executes. We have the node 6 and the node 4 in our dictionary. P is 6, Q is 4. And that takes us to this second block of code. Here, we initialize an empty set and call it ancestors. This will store all the ancestor nodes of P so that we can check if Q has the same ancestors. We do this with 2 while loops, one for P and one for Q. In the first while loop, we add all the ancestors of P until we hit none. So all the ancestors of P up until the very first root node. That way, we know for certain the lowest common ancestor of P and Q will be in this set. The second while loop is how we locate which of all these parents is the correct one, the lowest common ancestor. We first check if Q is already in ancestors. If it is, we know Q itself is the answer. Otherwise, we check our parent dictionary for Q's parent, updating Q. If Q's first parent is in the ancestors set, this is the lowest common ancestor. If not, we check the dictionary for the parent of Q's parent, and we continue this way in the while loop until we find the lowest common ancestor and return it as our answer. There is another less intuitive way to do this, which takes up less space, which we'll walk through after our explanation here. So this column is our first while loop. You see, the very first thing we do is add P to the set, update P to its parent, add the 5 to the set, update P to the 5's parent, and finally add that which is the root node to the set, and at that point the parent becomes none, so we break from the first while loop. On the right side we have our second while loop. Q, which is 4, is not already in our set, so we update Q to be the parent of Q, which is 2. 2 is also not in the set, so we update Q to be the parent of Q, which in this case the parent of 2 is 5. Finally, this if check executes because 5 is in our set, and we know we found our lowest common parent of 6 and 4, which is 5. Let's now take a look at the less intuitive way to do this second part, which takes up less space. We use 2 pointers and initialize them to P and Q, and what we're doing is iterating up their respective parents until the pointers are equal. At that point, we return the node as the lowest common ancestor. So in the simplest case, for the 5 node and the node 1, one iteration and they are both equal to their lowest common ancestor. But there is a second case where one of the pointers reaches the root node and the other pointer is still somewhere in the tree. When this happens, the pointer iterates one more and becomes none. When that happens, we set the pointer to be the opposite of the target node P or Q that we first set it to be. This solution will work in 2 iterations max, meaning the pointer won't switch from the root node to the opposite P or Q more than once, and the solution of course won't loop forever. This is because when we switch the node to be the opposite of the target, the pointers will eventually traverse the exact same total distance as each other. This total distance will be their respective paths to the lowest common ancestor and any nodes between the lowest common ancestor and the root. Switching at the end ensures this synchronicity, so I've included this solution in the notes also. So if we set the first pointer to be at the 6 and the second pointer to be at the 4, and we have our dictionary so we can do our traversal. In the first loop, the 4 goes to the 2 and the 6 goes to the 5. On the second loop, the 5 to the 3 and the 4 to the 5. One more loop and the blue pointer becomes the parent of 3, which is none, and 5 goes to the 3 node. At this point, we switch the blue pointer to be the opposite of the target node it was first initialized to, so we set it to the 4 node. And at this point, the purple pointer goes up to none. One more iteration, the blue pointer goes to the 2 node and the purple pointer switches to the 6. The blue pointer goes to the 5, and at this point, the purple pointer also goes to the 5, giving us our lowest common ancestor. So that should demonstrate how both pointers will traverse the exact same total distance, their respective paths to the lowest common ancestor and any nodes between the lowest common ancestor and the root. And here it is written out in full. So just focusing on the last 2 sections of this iterative solution, both are O of 2h time complexity, where h is the height of the tree. In the worst case for the pointers, each one will traverse the entire tree, giving us O of 2h. For the ancestors set solution, the first loop in the worst case scenario will traverse the entire height of the tree to collect all the parents, and the second loop doing the same. So both will be O of 2h for time. Again, just focusing on the last section for now. But the difference here is the pointer solution is constant in space. We just have these 2 pointer variables. However, for this first solution, our space will be O of h for storing our ancestors set, all the nodes in the max height of our tree. For the entire solution, however, both iterative approaches are O of n space complexity for our queue storing. The queue in the worst case will be the size of the deepest level in the tree, which we've explained before as up to half the total nodes in a perfect tree. This is because we are doing breadth first search, and our parent dictionary could also contain all the nodes in the tree. As for time, the overall solution is O of n as we traverse every node in the tree, and as we said, O of h time for these last two parts to find the lowest common ancestor, which overall simplifies to O of n since h is at most n. So that's our iterative solution. Let's quickly check out our recursive solution. The logic here is that we perform a depth first search, and when we reach a leaf node, we return none, or if we reach p or q, we return p or q. And that's our base case, which this first line does, defining the action behind these arrows at the end of the tree, the leaf nodes, or when we pass the target nodes 4 and 6 back up to their parents. The next two lines are of course our recursive function calls, which enable us to traverse down the tree until we find this base case. And the final few statements are where we determine the lowest common ancestor. Firstly, if we receive values from the left and right subtrees, we know this will be our lowest common ancestor. So we return that node, which is the root of the current function call, just as we see here with the 5 node. The next two statements are us returning towards our lowest common ancestor, or defining the return of the lowest common ancestor back up the call stack. For example, at the root node, when we return the 5 because the right side is none. On the other hand, these can also define the actions for us reaching our lowest common ancestor. For example, at the 2 node, when we return the 4, because left is none, so we return the right at the end. Time complexity for our recursive solution is O of n to process all the nodes, and space is O of h, where at the worst point of the algorithm, the recursive call stack will be the length of the deepest subtree. The maximum height giving us O of h, which is at most n, for example, a degenerate binary tree where every node has one child, giving us O of n space. And so that's our recursive solution, giving us a full evaluation of how we can find the lowest common ancestor in a binary tree, wrapping up our binary tree section nicely. Our next section is binary search trees, and a reminder that a binary search tree is a data structure which is a form of a binary tree. It's an ordered binary tree where the ordering is such that every node in the left subtree is less than its parent, and every node in the right subtree is greater than its parent. In other words, any node's left child is less in value to itself, and right child greater in value. So let's get straight into our first question, where we want to search our tree to find a single node. This is one of those core operations that could easily be part of another bigger scoped question, like the mediums. You shouldn't have too much trouble with this one, so definitely try giving it a go. Otherwise, let's take a look at the code. We're going to take the root node of the tree and the value that we're looking for. While our node exists, we're going to traverse down the tree and update the current node. If the node is too small compared to the target, we go right, and if the current node is too large, we go left. Eventually, we'll find the equal node and return, or we reach the end of the tree, updating the current node to be the child of a leaf node which is none, break from our loop and return none as the question asks. And remember what we said previously about checking the end of the algorithm towards the start of a code block. This is another example. And one more programming concept that we can also learn here is that we can directly use the root without creating this current node variable. That's why we have these two solutions side by side. In Python, when we pass the root into the function here, we're creating a reference to the same object, but a new local variable root inside our function. This can then be reassigned without modifying or overwriting the original reference outside the function. For example, when we reassign this current node or root to be the left or right child. So that's our solution. Time will be O of n because in the worst case, we could search the entire height of the tree to find our node, or break from the while loop and return none. And space will be constant because we're only keeping track of the root variable or the current node that's passed in. So a nice introduction into binary search trees using the fundamental property of left being less and right being greater than to find a node based on the given value. In our next question, we have another core operation which is inserting into a binary search tree. It's marked as a medium, but I definitely think it's easier than most mediums. We've looked at inserting recursively in the data structures practice, although the iterative is never too far off, just a while loop or an extra data structure to store some information. So now to contrast that, we can look at the iterative approach. And although it's easier than most mediums, it's likely marked as such because there are two smaller scoped problems. First, we have to find the node's position in the tree, a similar concept to the previous question, and then we have to insert the node, making sure to maintain the binary search tree properties. Let's take a look at our solution. The first thing we do is create our new tree node with the given value. We will insert this later. If there is no root, the tree does not exist, so we can return the new tree node. That's our new entire tree. Otherwise, we can assign the root to a new variable called current, although as we've just seen before, this is not necessary. And then next, in our while loop, we traverse down the tree, updating our current node to be the left or right child, going left if the value we're adding is smaller than the current node, and right if the value we're adding is greater. Again, we saw this while searching for a node in the previous question. We keep doing this until eventually we want to go left or right, but we've reached a leaf node. At that point, we can just add the node as the right or left child. So in the case of this first example here, we are adding node 5 to this tree. Inside our while loop, we go right because 5 is greater than 4, and on the next iteration, we reach the 7. 5 is less than 7, so we go left. But we can't go left by updating the current node to 7's left, so instead we add 5 as the left child of 7, and that's our new tree. Pretty easy to understand solution, and no need to update the root node like in this example. Our time complexity is O of n, where n is the height of the tree, because in the worst case, we traverse over n nodes equal to the max height of the tree. For example, if we want to add the 0 value, we would go all the way down this left subtree. And space is constant, nothing is being stored except our current variable and the node we are adding. And that completes inserting into a binary search tree. Nothing too complex. Our next question, we want to convert a sorted array into a binary search tree. So working with another data structure which we have seen before and should be experts on by now. The question says, given an integer array nums where the elements are sorted in ascending order, convert it into a height balanced search tree, meaning the depth of the two subtrees at any node never differs more than 1. So you see in example 1, based on our input nums, we have -10 as the smallest value, so that will be the furthest down the left subtree, and then -3 and so on, building our height balanced tree. So despite being marked medium, this is a bit of a difficult one, but give it a go. Otherwise, let's take a look at our code. We have two different styles of a recursive solution, but let's ignore that now and focus on our iterative. We use breadth first search, so the overall style should be very familiar. And we're going to use some concepts from our array section to complete our solution. And here's a walkthrough of that example. There's a lot going on here, but don't worry, we're going to cover every single step. We begin with an edge case check. If there is no input nums, then there is no tree to build and we can return none. Otherwise, we begin by initializing our tree. We can use n, the length of the array, to perform a floor division, finding the middle index and taking that number to create our root node. This is necessary for ending up with a tree that is balanced in height. And then we set up our queue for our traversal. The item structure inside our queue here will be a tuple of 3 elements. The first element will be a node, specifically the parent node. The second element is our left pointer, and our third element is our right pointer. This sets up our mechanism for building our tree initialization and our breadth first search initialization. So using the array from the example, we see we have 5 elements inside. That gives us a midpoint using floor division of 2, and at the 2 index we have the value 0, so we can create that as our root node. And the core mechanism inside our while loop is that at each stage we're going to select the middle element of our array or our subarray and add it to the tree to maintain the balanced nature. For example, at the start when we just took the 0. After that, to set up the first iteration of our traversal, to the queue we add the node 0, which will be the parent node reference, and then we add a left pointer at 0, the very first index in the array, and the right as mid -1. This will be the entire left half of the array. The next tuple will add 0 as the parent, and the left and right boundaries as 3 and 4. This will create a subarray of the right half of the input array, 0 to 1 being the left half and 3 to 4 being the right half. This is what we're setting up in our queue. And of each subarray, we take the middle value again to ensure we keep the tree balanced, creating a node object with that value and adding it on in the correct position of the tree. After that, we split the subarray again by appending the left and right sides of that subarray from the middle. So it might not be clear with this example, but if we take a longer array, you might get the idea. So there's 10 elements in our array. Using the exact same mechanisms in our initialization, 10 divided by 2 gives us 5. At the 5th index, we have the 6 value. So we'll take that and make it our root node. After that, we take the entire left half of our nums and the right half. So from 7 to 10 and from 1 to 5. These will be the first 2 tuples in our queue. And from there, we do the exact same thing again. We would take 3, which is the middle node, and we would take 8. Making them the left and right child of 6. And then from that, we add the left and right subarrays to our queue for each node. So at that point, we'll have 4 more tuples in our queue. And we continue this way again, taking the middle node and creating our tree. Eventually, the left pointer will be greater than the right, because each time the bounds are adjusted to exclude the middle every time. And as we progress and shrink the size of our subarray, eventually the subarray will be empty or invalid when left is greater than right. So we check this to prevent any errors or further evaluation. And that's pretty much our code. So let's go step by step through the first example. And just a quick note that 2 different results are accepted. The difference arises from the choice of the middle element when the array is split, especially when there is an even number of elements to choose from. So as we said, we initialize our tree with the node 0, which is the middle element of the array. Then we add the two tuples, which are the left and right subarrays, into our queue, ready for our traversal. On the first iteration, we pop off this entire tuple. The parent is the node 0, the left is 0, and the right is 1. And we assign them all in this line here. From there, we figure out the midpoint, taking the start and the end index of our subarray. So in this case, it's just 0 add 1, and we perform a floor division on 2, the same way we did in our tree initialization. That will give us a value of 0, and the element at that index in our input array is -10. So this value is less than our parent node's value, which is 0, so we assign the node -10 to be the left child of our node 0, and then we queue up the next two subarrays into our queue. First in, first out, so the next element we pop will be this tuple with the 3 and the 4. These two boundaries will give us a midpoint of 3, pointing to the element 5 in our array. This node's value is greater than its parent, so we make it the right child of our node 0. The next tuple we pop off will not evaluate because left is greater than right, so there is no more subarray to be evaluated here. On the fourth iteration of our while loop, we will add the -3 node as a right child of -10. The next tuple will not evaluate. On the sixth iteration of our while loop, we'll add node 9 as a right child of node 5. After that, every tuple in our queue will not evaluate because left is greater than right. So our while loop will continue, pop these all off, none of them will evaluate, so we break from our while loop and return the root of our brand new tree. The time complexity for this iterative solution is O of n. Each element in the input array is processed exactly once. This occurs in our while loop. And space is O of n, the queue can contain up to n nodes in the worst case, and we are also using n space to create our tree. And so that's how we can create a binary search tree from a sorted array. A nice question that uses two date structures in the problem. Next up, we have an old favorite, TwoSum. It's made a return, and this time in the form of a binary search tree. Given the root of a binary search tree and the integer k, return true if there are two elements that exist in the tree such that they are equal to k, and false otherwise. For example, node 2 and 7 are equal to our target 9, so we return true. So this is another question that builds on some previous concepts we've encountered, piecing together different parts of our knowledge tree. And actually, this will be a bit simpler than the arrays version because the question is not asking for us to return the index, but just whether it is true or false. So let's take a look at the code. We begin by initializing our queue for our breadth first traversal level by level. We also create a set. The set will hold all the values of the nodes we've seen so far in our traversal, similar to the hash map in the original question, but no need for an index key value pairing. Then we traverse over our entire tree, at each point calculating the difference between the target and the current node value. If this difference is in our set, we know we have two nodes that can sum up to the target, so we can break and return true. The other case is where our queue is empty, so we finished our traversal. Then we know for certain there are no two nodes that can sum up to the target, and we can return false. So pretty straightforward, and I don't think we need to go through it line by line. However, I've gone ahead and drawn out the first example from the question, so pause and look over the details if you want a line by line walkthrough to help your understanding. Time is O of n, since in the worst case we traverse all the nodes in the tree and the last one gives us our solution. And space is O of n. If we do have to traverse every node to find our solution, then every node will be stored in our set. On top of that, we also have our queue, which can store n nodes. And so that's our TwoSum solution for binary search trees. Lowest common ancestor of a binary search tree is our next question. And we have just gone through this for a binary tree, which is more difficult than a binary search tree since we did not have the ordering. So you will have no trouble giving this one a shot. Pause now and give it a go, otherwise let's take a look at the code. So this picture here defines the mechanism of what's happening inside our while loop. But before that, we check p and q and quickly assign the smaller of the two to a variable named small and the larger to a variable named large. And a quick reminder that p and q are two nodes in the tree that are given to us, and we have to find the lowest common parent in the tree. So we begin iterating over the tree, and we let the current node's value dictate the path of our search. At each point, starting with the root node, we check its value. If the current node's value is greater than our large variable, whichever that is, p or q, then we know we need to go down the left subtree to find the lowest common ancestor. For example, here in case 1, p is 2 and q is 4. The current node is 6, so for sure the common parent node we're looking for is on the left side. In that case, we update the root to be the left child and repeat the process. On the other hand, if the current node's value is not greater than the larger of p and q, but less than our small variable, then we need to update the root to be the right child. As we see in case 2, if p is 8 and q is 9, then 6 is smaller than the small variable. 6 is less than 8, then we know we should check the right subtree. Finally, the other option is if the current node is not smaller than our small or larger than our large. In that case, it must be the common ancestor, as we see in the third example. If we don't find a node with a value in between the small and the large, then at some point the code will update the node to be a child which is none, breaking from our while loop and returning none at the end. The time complexity is O of h. since in the worst case we go down a subtree, which is the max height of the tree. Then we either find nothing or find our solution and we finish. This can of course also be O of n, since h is at most n. Space is constant, we have our small and large variables, and that's it. And so that completes our solution for finding the lowest common ancestor in a binary search tree. A lot friendlier than the binary tree version. Minimum absolute difference is our next question. We are given the root of a binary search tree and we want to return the minimum absolute difference between any two nodes in the tree. So it's a familiar problem we've seen before, except now we're dealing with it in a different data structure. And I'll give you two hints before we get into the question. One is that the minimum difference will always be between consecutive nodes. That should help scope down the problem space. And hint 2 is that processing in ascending order is the traversal that will give us the best solution. Left subtree, root, right subtree. If you remember our data structures practice, this is in order traversal. So pause now if you want to give it a shot, otherwise let's see our solution. So as we just said, we want to do an in-order traversal, smallest to largest. And at each node, we compare its value to the previous node. So in our example here, 0 is the smallest node, which will be the first we traverse. And eventually, we compare the one node, which is the next smallest value, to the previous smallest, the 0, and find the difference. To set this all up, we create a min difference variable. This will track the minimum absolute difference at each node comparison in our traversal. We also create a previous value variable. This is for the comparison after we update the current node, something we saw often in our linked list questions. The two values are set to positive and minus infinity, since this will be outside the constraint of the question. The first is positive since later we are updating the variable and we will look for the minimum or the smallest value, so positive infinity will definitely be replaced. And negative infinity for the previous value. This is just a neat trick to avoid extra code in the first node comparison for when there is no previous value yet. We'll see this in a second. And lastly, we create an empty stack. This will contain the nodes for our ascending in order traversal. Then we begin a while loop which will execute as long as there is a root or stack to process. We have two blocks of code inside our while loop. The if block is for traversing down the left subtree, pushing nodes onto the stack from the largest to the smallest until we reach a leaf node all the way down the left subtree. When we reach a node which is none, we know we've gone as far left as possible, so we hit the second block of code. In this block, we pop a node from the stack, which will be the next smallest node. We do the evaluations, calculating the min difference and updating the previous value before updating the root node to be the right child. So seeing this in practice will make a lot more sense. In the first iteration of our while loop, we append the root node 1 to our stack and update the root to be the left child 0. On the next iteration, we do the same for the 0 node, updating the root to be its left child, which is none since 0 is a leaf node. On the third iteration, our root is none, so we hit the else block, pop off the top of our stack and calculate the min difference. We compare the current min difference against the current node's value minus the previous node's value. We don't have any previous yet, so this will evaluate to stay as positive infinity. After that, we store the 0 as the previous value and update the node to be the right of 0. Next, on the fourth iteration of our while loop, we pop off the 1 node. Then we check the difference between the 1 and the 0 node. This gives us a new minimum difference of 1. We store 1 as the previous value, the last node we've seen in our traversal, and update the root to be the right child of 1, the 48 node. At that point in iteration 5, we add the 48 node to our stack. Take the 12, which is the left child, and add it to the stack. And in the 7th iteration, we evaluate the 12 node before evaluating the 48 node in the next iteration, and then eventually the 49 node in the 10th iteration. Again, left, root, right. And of course, along the way, each time checking if there is a new minimum difference. So now we can see that this works because the smallest absolute difference will of course come from two adjacent nodes when we search in ascending order. Also, the in-order traversal will naturally yield the absolute difference between consecutive values, as the root node will always be bigger than the previous value. Eventually, our stack will be empty and there is no current node to process. We've gone as far right into the tree as possible and checked every difference. So we break and return the min diff variable, which will be our answer. Time complexity is O of n since we visit every node once in our traversal, and space is O of n for our stack, which at the worst point will store the max height of the tree. And so that completes our minimum absolute difference solution. Our next question wants us to balance a binary search tree. We are given the root of a binary search tree, and we are asked to return a balanced version of that tree. Balance meaning the height of the left and right tree at any node does not differ by any more than 1. So give it a go now, remembering that medium questions typically encompass 2 easy questions or 2 smaller problems. In that case, you might find this easy, especially because we've gone over those 2 smaller problems in this section already. So let's take a look at how to solve this. We're going to do this in 2 parts. First, we're going to create an array of the original binary search tree, sorted in ascending order, and we've just seen how to do this in the previous question question, minimum absolute difference, and this sets us up perfectly for the second half. Here we will create the balanced binary search tree from the sorted array. We do this iteratively, finding the middle element as the root of each subtree, using a queue to manage the process. We've seen this in the question which names the logic itself, convert sorted array to binary search tree, where that question specifically asks for a balanced binary search tree. There's also a recursive way to do the second part, which we have in that previous question also. We have already gone through both of these blocks of code in detail, step by step. So if you're unsure of this solution, go back and take a look at these questions. And if you're still confused, try taking pen to paper and drawing it out for this question. Overall time complexity is O of n. The in-order traversal processes each node exactly once, despite the nested while loops. Those just help navigate the in-order traversal. For the converting of the array to the tree, the algorithm processes each element of the array once and inserts it into the new tree. Space complexity of the entire solution is O of n. The in-order traversal uses n space to store elements inside the nodes array, and at most storing the max height of the tree in the stack. For the conversion, the queue can at most hold n elements in the worst case, and n space for the new tree. And that's the balance a binary search tree question. A perfect example of using two previous questions or concepts to come to a solution for a harder question. Deleting a node from a binary search tree. This is another medium and another foundational operation for binary search trees. Personally, working through this operation here is what took me to the next level. Writing the code from scratch, drawing out how it works, writing it out again off memory, this really took my Python skills and data structures knowledge to a very confident level. We're given the root node of a binary search tree and a key or a value of the node that we want to delete while keeping the tree intact. Again, there's two smaller scoped problems in this medium, and this time we're actually told what they are. One, we want to search for the node to remove, a core operation we've gone through a few times now. And two, if we find the node, we want to delete it. So this isn't just as simple as deleting the node, we have to keep the tree intact. So a final hint is that for the second part, when we are deleting the node, we have three cases from the simplest to the most complex. Case 1, we're deleting a leaf node, so it has no children. Case 2, the node has one child. And case 3, the node has both children. So give it a go, it's definitely quite involved, so don't be surprised if you spend a bit longer than expected. Otherwise, let's take a look at our coded solution. We can do this recursively or iteratively. I prefer the recursive in this situation. It's cleaner and, in my opinion, not too difficult to follow. This is the one we went through in the data structures practice in a lot of depth, so I won't cover it again. However, between the two solutions, the core mechanism will be the same. For example, the deleting of a node and rearranging of the tree. And in the data structures video, we covered all three cases of node deletion, so definitely give that another watch. Instead now, let's take a look at the iterative approach. Let's see how it works and compare it to our recursive. This will be a good exercise. So we have our two broader sections. The first smaller problem is to find the node we want to delete, and the second is to delete that node. So this section here is us finding the node. And for the iterative approach, we need to keep track of the parent when looking for the node. So there's a slight difference there already. Of course, in the recursive, the parent is already accessible, since the parent will be the node from which we make the recursive function call, like in this line here. So in a while loop, as long as the current node exists, so we've not reached a non-existent child of a leaf node, and the value is not yet the one we're looking for, then we continue traversing down the tree. We go left if our value is smaller than the current node, and right otherwise, until finally we break from the while loop if we find the value, or of course we reach the end of the tree. If we did not find the value we're looking for, we return the root of the tree as asked. Since there is no node to delete, the tree remains unaffected. Otherwise, we have a current node to delete, and we hit the second section. Here we have our three cases: no children, one child, or both children. If the node has no children and no parent, then it must be the root node. So to delete that, we can just return none. The tree no longer exists. Otherwise, it's pretty simple. We check whether this node is the left or right child of the parent, and then we set that child to be none. That's case 1. Case 2 is for one child. In this line here, we assign the child of the node we want to delete to a variable, checking if it's the left or right child that exists. Again, if the node has no parent, it's the root node, so we can just return the child as the new root node of that tree. Otherwise, again, it's pretty simple. We change the child of the parent of the current node to delete. So for example, if 6 is the current node, then we just set this child variable to be the right child of 6, the 7 node. We do this in this first line here, and in the final line, the parent of 6 is 5. 5's left child is not equal to current. Instead, it's equal to the right child. So in our else block, we assign the right child of the parent, which is the 5, to be the child of the current node we want to delete. So essentially, we're breaking these two lines, and creating a new one like this, removing the 6th node from our tree. And that's case 2. Finally, case 3, both children. In this event, we have to find the next smallest node. We can find the biggest in the left subtree, or what we do here is find the smallest in the right subtree. We went over this function in the data structures video, so in the recursive solution, we reuse that function. And it might be a better idea to create a separate function for this, because it makes the code cleaner and we can reuse this function elsewhere in our code. So I've taken the example from the question here, and I've added this 3.5 node so we can really see how things work. So in this block of code here, we want to find the smallest in the right subtree. We want to traverse down the left subtree of the right child of the node we want to delete as far as possible. So we begin with a successor parent of 3 and the successor 4. One iteration of our while loop, and the successor parent will be 4 and the successor 3.5. The left child of the current successor. At that point, there is no left child of the successor, so our while loop finishes. And then we update the current node's value, the one we want to delete, to be the same value as the successor. This is of course why we created new variables when looking for the successor, so we can come back to the current and update it. Now that we've changed its value, all that's left to do is to delete the successor node. In this case, the successor's parent's left child is equal to the successor. 3.5 is the left child of the parent's successor. So we update the left child of the successor's parent to be the right child of the successor. In this case, it will be none. If the successor did have a child, it must be the right child, since we traverse all the way down the left subtree of the right child when looking for the successor, in this while loop here. Or in the else block, the successor is the right child of the node we want to delete, directly being this 4 node, and this will update the 4 node to be the right child if it exists, or none. And so that's case 3. When we're done, we return the root of the tree, and that completes our solution. Time complexity is linear. For case 1 and 2, we are just updating references. This will be constant time, but for case 3, we traverse to find the successor, which can be up to the height of the tree. And we can also traverse the height of the tree to find the node in the first section of the code. And space is constant since nothing is being stored. And so that's how we can delete a node from a binary search tree. In our final binary search trees question, we are given the root node and an integer k. We want to find and return the kth smallest value in the tree, the smallest starting at index 1, not 0. And it's asking for the value of the node, not the node itself, so be sure to return that. Pause and give it a go, otherwise let's take a look at our solution. You might be surprised by how easy this is for a medium, and that's because all the concepts we've learned so far are coming together. This is why Leetcode and interviewing is not really difficult. We just have to see enough problems until we realize that the solving pattern is applicable and replicate the code for the question. So in this example, it's simple. We start by finding the smallest value node, and from there traverse our tree k times to find the kth smallest node. Well, to find the smallest node is easy. We've seen this before in this section, as well as in the data structures practice along with the other traversal methods. So we traverse in order using the exact same code pattern, a stack to store our nodes, a while loop which executes until the root is none and the stack is empty, an if block for traversing down the left subtree, and the else block for popping nodes, performing our operations, and traversing right. Compare this to the min absolute difference question, and nearly everything is the same. The only thing that's going to change is the operations we're carrying out. No need for any extra variables. All we're going to do is check if we've traversed in order k times from the smallest value node by checking the value of k, minusing 1 from its value after each traversal. So that's the conceptual approach, and here's a step-by-step walkthrough. Again, essentially traversing all the way down the left subtree from the root to the smallest node, adding these values into our stack. This will all occur in the if block. And then we pop the nodes off the stack one by one, reducing k by 1 for each node until k is equal to 0. This will all occur in the else block. In the worst case scenario, the algorithm needs to check every node when the kth smallest element is the largest element in the tree, requiring a full in-order traversal of the entire tree. Additionally, in a tree where we just have one single subtree, something that looks more like a linked list, the algorithm would still need to visit each node to reach the kth smallest element in the first place. Our space is O of n driven by the stack, which can grow up to the height of the tree. So n at max is the height of the tree, as we see in the example after we reach the smallest node. And so with that, we complete this question and the binary search trees section. In our next section, we're looking at heaps, and I do mention it often, but it's so fundamental to answering these questions. If you haven't already, check out the heaps section in the data structures video. You'll see we cover a couple different ways to create heaps and 2 different types of heaps, the max and min heap. And just a quick reminder on what a heap is. Often used to refer to binary heaps, where each node has 2 children at max. We can define it as a complete binary tree, complete being each level is fully filled except for the last level. And it must satisfy the heap property, where for a min heap, every child node is greater than or equal to its parent, and the reverse in a max heap. essentially implementing a priority queue. But again, definitely check out the data structures video or other alternatives on how we can build this using an array, or how we can use libraries to build this, and all the associated functions with heaps. And here is a quick reminder on some of these functions and their time complexities. And in the material, I'll link to some of this stuff. For example, there's a very good explanation on heapify and why it's linear. So if an interviewer asks you, can you implement this heap using an array or the built-in method, which they often will to test your limits, then you'll have no problem. And a heads up that every question in this section is a medium. The code isn't necessarily complex or the problems too difficult. I think it's more so to do with the fact that heaps are a bit more involved than other data structures like arrays, for example. So with that in mind, let's see our first question. Kth largest element in an array is our first heaps question, where we are given an integer array nums and a single integer k. We want to return the kth largest element in the array, a reverse of the last binary search trees question we saw. Since this is an arrays based question, it can easily be done by sorting the array and returning the kth index, but we want to do this without sorting, and using a heap is a very good way to go about this. In this question, I really want to cover a lot of areas on heaps to give us a good foundation for tackling the rest of the section. So let's take a look at the code, and here we have 3 solutions. On the top right, we have the most concise way to do this. The heap qn largest function internally uses a heap to find the k largest elements from the nums array argument input. It sorts the heap in descending order, largest to smallest, returning a list. And you can see from the definition of the heap q module that the n largest function returns a list of the n largest elements from the dataset. And the -1 index at the end is returning the last element in this sorted list, which will of course be the kth largest element. So here's a quick example. We have an array of numbers from 1 to 10 unordered, and if we print the n largest numbers passing in k, which is a value of 3, we get 10, 9 and 8. If I change this to 5, we'll get the 5 largest items, and if we add the index -1 on the end, we'll get the last item, the kth largest item, so in this case the 5th largest item. The time complexity for this is n log k, and let's break it down. The heap construction takes O of k time, and there are 2 parts to this, the initial construction and the heapifying process. Adding the first k elements into an empty array, O of 1 constant per element, giving us O of k to create the heap. Then we order and arrange these k elements into the heap structure using heapify, which is also done in O of k time. And we can see from the documents that heapify is linear in time using no extra space. Without dissecting the inner workings of the heapify operation, we can just say heapify is linear because we start from the bottom non-leaf nodes of the heap/tree and work our way up towards the root, minimizing the number of comparisons and swaps needed. If you want an explanation on the exact inner workings and exactly why it's linear, I'll link some extra reading materials because there's a bit of maths involved and it needs some time to digest. So you can go through it in your own time at your own pace, but I wouldn't expect this level of detail in the interview, so it's not the most necessary thing to learn. So we initially create a heap of the very first k elements. Then we need to check the remaining elements, the n minus k elements, to make sure that our heap contains the k largest elements. So what the code does is for each remaining element, we check and compare it to the root. If the new element is larger than the root, then we replace it, and we reheapify to maintain our heap of the k largest elements. The time complexity for each insertion into the heap is log k. In general, inserting into heaps is log n, since the height of a complete binary tree with n nodes is log n, and a binary heap is a complete binary tree. Then the height of a binary heap is also log n. Since the tree is complete, every level is fully populated with the exception of the last level. Then intuitively, this leads to a tree height that grows logarithmically with the number of nodes. Therefore, inserting into this tree/heap requires adding the element at the end and bubbling it up. This is of course the process of checking the node value with its parent and swapping if necessary. And in the worst case, we swap the node all the way up to the root, covering the height of the tree, requiring log n operations. So that gives us a time complexity of O of k plus n minus k times log k, which in the worst case, n is a lot larger than k, so we can simplify this down to O of n log k. And space is O of k. We have our heap of k length, which we use to create a separate array, which is also k length. So O of 2k, which simplifies to k. Let's now take a look at our second solution. In the middle here, we have the unoptimized approach, where we create our own heap using an array, push all the items into the heap using the built-in heap q heap push function. This will ensure that each value in the array is in the correct index to maintain the parent-child heap property. By default, this creates a min heap. To create a max heap, we have to do some tricks with negative values and it can get very messy. So for now, we'll stick to the min heap. It works fine and the complexity will be the same. So in this first for loop here, we're pushing all of the elements into our heap. Let's take a look at how this first part works. We create our heap, and then for every item inside our nums, we're going to push it into our heap, passing in the heap and the number at each iteration. And when we print at the end, you see we have our ordered heap. 1 being the root node, a left child of 3 and a right child of 2. 3 has the left and right child of 4 and 5. 2 is the parent of 6 and 10. 4 has a left and right child of 7 and 8. And 5 has a left child of 9. That's our heap. Then in the next loop, we pop elements off the heap until the size of the heap is k. We use heap pop to maintain the structure of our heap. So if I change k to be 2, then the length of our nums, which is 10, minus 2, gives us a range of 8. So we'll pop 8 items off our heap. Let's see what that looks like. And here we are popping the 8 smallest items off our heap, leaving us with a heap which is the size of k, which is 2, containing the largest 2 elements. And then we have 9 and 10. So in the final line of our code, we can heap pop one more time to return the kth largest element. The overall time complexity is O of n log n, less efficient than the previous solution. The reason is, heap push operation is n log time. We've explained why in the first solution. And we're creating a heap of all n elements, so constructing the heap is n log n, whereas the first solution maintained a heap of k size, so inserting every time was log k. Not to mention the initial construction in the first solution was also a lot more efficient because we were heapifying. Anyway, in the second part, we're removing n minus k elements from the heap, and each removal takes log n time. We know why inserting is log n, so why is removing log n? Well, it's essentially the same reason. When we insert or heap push, we use sift up or bubble up, placing the item at the end of the heap and swapping upwards towards the root, which could require operations up to the height of the tree, which is log n. To remove or heap pop, we carry out sift down, also known as bubble down or heapify down, removing the root node, the first element in the array or heap. Then we place the last element in the array at that first position, and then we carry out the swaps downwards, again up to the height of the tree, giving us log n also. So that gives us n minus k log n for the n minus k heap removals. And then we have one final heap pop, which is one more log n operation. And of course, space is O of n, since we're maintaining a heap of n size. And then finally, we have our third solution on the left, which is a more optimized approach to create the heap manually with only k elements inside. A hybrid approach to the two previous solutions, following the logic in the first solution but executing the code more manually, similar to the second solution. And this approach is something an interviewer might ask you to write out if initially you gave the first solution, just to make sure you understand exactly what's going on under the hood, and not just that you know the n largest function gives you the n largest elements using a heap, for example. So we create our heap based on the nums array with k elements inside, and in the second line we use the built-in heapify function to turn this array into a heap. So from the first approach, we know that heapify is linear, and it happens in place, which is good for space, but overall that doesn't really matter in comparison. What does matter is this gives us O of k time, which is a lot more efficient than n log n in the second approach with n insertions. So after creating our heap of k length, for each remaining element in the array, so for n minus k elements, if the element is larger than the smallest element in the heap, which is the root node, we replace the root with this element and reheapify. This is our second section here. So we're maintaining our min heap of the k largest elements using heap replace, where at each point the smallest element at the root is the kth largest element. We use heap replace, which performs a heap pop followed by a heap push with the given element. We know each of these operations, heap pop and heap push, is log k. So together that's 2 log k, and we do this for n minus k elements, giving us n minus k times 2 log k. After processing all these elements, we know the root will most definitely be the kth largest element, so we can return this in constant time and finish. For this optimized manual solution, that gives us an overall time complexity of O of n log k due to the mathematical simplification, and space is O of k since we maintain a heap of size k. So that completes this third solution and the entire question. We went over a lot there, but it was a good question to cover a lot of different heap operations and build that knowledge so that in future questions we know exactly what's going on and we don't have to go through the explanation every time. A lot of knowledge that we can use later in this heaps section. K closest points to the origin is the next question, where we are given an array of points on a graph where points I equals x and y, so an index in the points list represents coordinates on a graph. So points is a list of lists, as we see here, where each nested list contains 2 numbers, and we are also given an integer k. This represents the number of points from the list that we should return, which are the closest to the origin 0, 0. They also give us the formula for finding the distance, which you should have been taught in any high school level math class, so I would half expect a candidate to know this one. But it's not a major issue, the formula is just the square root of the summed squares of the differences of x and y. And finally, we're told we can return the answer in any order, and it's guaranteed to be unique, meaning there won't be a case where multiple points have the same distance and we have to choose between these points. For example, if k is 1 and the points are 1, 0 and 0, 1. So knowing we will approach this question with a heap and given the distance function, it becomes pretty clear how we are going to organize our data. Pause now and give it a go, otherwise let's see how it's done. So here's our code, and there's a few different ways to approach this as we've seen in the previous question, but I like this approach the most. We begin with our empty heap, and what we do is loop over all the elements in the points array. For each point, we calculate its distance from the origin. The origin is of course 0, 0, so the distance equation simplifies to the root of x squared plus y squared. If you remember from the last question, I said the built-in heap queue module creates a min heap by default, and the way we create a max heap is to negate the values. This will work regardless if the data is positive, negative, or mixed. So negating the values will make the largest element in the dataset the smallest, and since the heap queue library creates a min heap, that places the largest element, now the smallest, at the root. Having a max heap and knowing the originally largest distance point is at the root is very useful to us, especially since if we use the min heap, the last element is not necessarily going to be the largest. We'll see this max heap in action in a second. But first, a quick note that when we take this somewhat hacky approach to building a max heap, we need to remember to flip the sign back at the end if we use that value, so it can get a bit messy if we're not careful. Luckily, in this solution, we're not going to need that distance value. It's only there to organize our heap. So going back to our code, we're iterating across our points array and calculating the distance. Then we insert into our heap a tuple of 3 items using heap push, the distance and the x and y coordinates. When we use a tuple or a list instead of a single item with these heap queue operations, they will always use the first element when making their comparisons. So we set the distance to be the first item in this tuple. So although we can use lists, I prefer tuples since they are immutable and therefore a bit safer. To make our algorithm as efficient as possible, we limit the size of our heap to k. We do this by checking at each loop if we've hit that limit, and if we have, we use heap push pop with the new tuple. Heap push pop first pushes an item onto the heap, reheapifies, and then pops, returning the smallest item from the heap. This is not to be confused with heap replace, which we've already seen. Heap replace first pops the smallest element and then pushes the new element. Same operations but different order. In this context, heap replace would pop the root and replace it with the new value. Even though the root is the largest distance, we don't yet know if the new value is smaller in distance yet. So if we wanted to use heap replace, we would have to compare the root first, and if the new distance was smaller, then we could replace it. Of course, we check if the new distance is actually greater because we have reversed all our values in the max heap. However, we can avoid all this trouble with heap push pop, which adds a new element onto the heap. So the size is now k plus 1, and again of course it heapifies with the new addition. So after heap push popping, we know for certain the root will be the largest original distance, so we can pop that off and continue. After checking all n elements, we have a heap of the k smallest distances. So using a quick list comprehension at the end here, we can return these points. Time complexity is O of n times log k, since in the worst case for all n elements we are doing a log k insertion, and space is O of k plus 1, which simplifies to O of k for our heap. And so that completes our k closest points solution. Top k frequent elements. Another similar style heaps question. Given an integer array nums and an integer k, return the k most frequent elements. You may return your answer in any order. So a very brute force way to do this might be to manually iterate over the array for each element and store the element and its frequency in a dictionary. Then maybe sort the dictionary based on the frequency values and append the top k elements to an array and return it. But we are way past that now, so I tried to solve this one with a heap, and it shouldn't be too difficult given our practice so far. Otherwise, let's see how it's done. We begin by using the counter class from the collections module. This takes in an iterable, like our input array nums, and it creates a dictionary where the keys are the elements from the given iterable, and the values are their counts or the frequency. Under the hood, this iterates across the input array, counting the values in one pass, so it's linear, O of n. Earlier in this Leetcode practice, I would do this manually, but we are getting more and more advanced now. And if you already know how to create this manually, I would definitely recommend using Counter in your interview. It shows you are comfortable with libraries, which is a big part of software engineering. Similar to how we are using the heap queue library instead of creating a raw heap and heapifying ourselves every time like in the data structures practice. So, after taking the count, we have all the data we need to pick the k most frequent elements. We do this using a heap of course, and we iterate over the items of the dictionary. Remember, we went through the different ways to iterate over a dictionary very early on, so we iterate over the items to get both the key and value pair. For each number and its frequency, until the heap is of size k, we heap push it onto the heap. This is a log k operation that will occur k times. And again, in our tuple of the frequency and the number, we put the frequency first, since this is the value we want our heap operations to use in their comparisons. positions. Then, once our heap is of size k, for the remaining n minus k elements, to make sure that we have the top k frequent elements in our heap, we compare each element with the root node. So we compare the frequency that we pop off from our dictionary with the first item in the heap and the first item in that tuple, which will be the frequency. If the new frequency is greater than the root frequency, we replace the number in our top frequency heap. We do this with heap replace, which will also heapify and maintain our heap. Finally, using a list comparison, we return an array of the top k elements with just the numbers and not the frequencies. And this is O of k to iterate across our heap and append these numbers to the array. Overall, this gives us a time complexity of n log k. When n is large and k is small, our bottleneck is this iteration. We go across the n minus k elements and potentially we replace every element. Space is O of n, dominated by our counter list, although we also have a k-length heap and a k-length results list at the end. So that's top k frequent elements, another k-style heaps question. And now we can begin to see a common style of question where heaps are most useful, as well as a few problem-solving patterns we can reuse to tackle these questions. Here we have our last heaps question, and it's a bit different from the k-type questions we've seen so far. We are given an array of CPU tasks, which is essentially just a list of capital letters in the alphabet, and we are also given a cooling time, which is an integer n. Each cycle or interval allows for the completion of one task. These tasks can be completed in any order, but there's a constraint. Identical letter tasks must be separated by n intervals due to the cooling time. So in the first example, n equals 2, meaning we have to wait 2 intervals to execute a task of the same letter. So the fastest way to execute in this example is to process A, then B, and then wait and repeat. We have to wait because after executing A, there needs to be at least 2 intervals. So in one of the intervals, we can execute B, and in the second interval, there's no other option but to wait. If n is 1, then we can pretty much execute task after task as long as they're not identical. So we need to find a way to get the minimum interval time and return it. And quickly, before looking at the code, let's consider the logic first. This will give you the intuition to write the code yourself if you want to give it a go. If we have a setup like this, with 3 A's, 2 B's and 2 C's, with the cooling time equal to 1, the very most basic approach we can come up with is to process the tasks in random order. This gives us the following: process B, then C, then B, then maybe do A, and then we have to wait before doing A again, then we do C, and then A one more time. This gives us 8 intervals. On the other hand, if we approach this solution by evaluating the most frequent tasks first, then we can avoid the idle time in the previous approach. At the start, A is the most frequent task, so we begin with A, then we can't immediately execute A again because we have a cooling time of 1. So after that, we have 2 A's, 2 B's, and 2 C's. So we can take either B or C, and in this example, we'll take B. Then we have 2 A's, which we can now process, and 2 C's as the most frequent. So we can just take A. After that, C is the most frequent, so we process C, and then at this point there's 1 of each task, so we can just add them in any order. And now we have the minimum possible interval time, which is 7. So we've established this most frequent approach minimizes the total interval time. So how can we do this with our date structures? Well, to keep track of the most frequent task, we can use a max heap, where the root node will maintain the largest element. And we're not actually concerned with the task letters themselves, just the time this all takes. So we'll be adding the frequency of each task, which if you remember from the last question, we found a quick and easy way to get this information. So here's our max heap, and don't forget we need to negate the values since our code defaults to a min heap. 3 lots of A tasks, and 2 B's and 2 C's. So in step 1, we count up the frequencies, and in step 2, we create the max heap. In step 3, let's create some variables that we'll need later. We want to keep track of the time or the interval, which is the same thing in this case, and we begin at 0. And on top of that, we want a queue to process our tasks and handle the waiting time. This will contain a tuple of the task count and the time at which the task will become available again to execute. And finally, in step 4, we're going to process our tasks. The way we do this is by popping off the most frequent task, the root node of our heap. So popping off this -3 means we've processed it. In that case, we need to reduce its value by 1. Obviously, it's a negative value, so we'll be adding 1. Another reminder to pay attention when working with max heaps, because the negation can make things a bit messy. So we remove this task from our heap, add 1 to signify we've processed it, reheapify, and increase our time interval by 1. Although this task is not finished yet, we still have 2 more to execute. So what we can do is add it to our wait queue. As we said before, we add a tuple of the number of tasks left, as well as the time the task is available to execute again. There's a couple ways to do this, but since we are keeping track of the time/interval we are currently on, the cleanest approach I've found is to use this wait queue with tuples where the first element is the task count and the second element is the current time plus the cooling time. So we have 2 more tasks to process, which will become available again at the time 2. After this, we can just repeat the process. Pop off the next most frequent element, which is this 2 or -2, reduce its absolute absolute value by 1, reheapify, increase our time interval by 1. Since the task is not finished yet, we add it to our wait queue, adding it with the current time plus the cooling time. And since we are at time interval 2 now, the task we previously added has become available. So we can add this back to our max heap, ready for processing. In this case, the values are equal, but we shouldn't forget to reheapify. And so that's one more cycle. And that gives us the logic for this problem. Pause and give coding it out a go now. Otherwise, let's see it written up. Here's the code, and in step 1, we collect the frequency of each task, again using the counter class. In step 2, we create our max heap, iterating over just the values in the dictionary since we're not concerned with the task letters, which will be the keys. We add the task counts to the heap, negating the values to build a max heap. Then we heapify in linear time. In step 3, we quickly create our time or interval tracker, as well as our queue for handling the wait times. And finally, in step 4, we process the tasks. We do this with a while loop, which continues as long as our heap has tasks, or we are waiting for tasks in our queue to become available. And in a way, this resembles code similar to our tree sections, where as long as we had nodes to search in our queue, or a current node to process, we would continue. Inside our while loop, we immediately increase the time by 1. Then, if our heap has tasks, they will be available to execute, so we heap pop the most frequent of the root, and we decrease its absolute value by 1 since we processed the task. Then if the current task is not finished yet, so we have more of that letter to process, we add it to the wait queue with the time it will become available again. In this final if block, we check if the task at the front of the queue is available to process again. If so, we add it back to our heap. Of course, we only check the front of the queue since that will always be the next available task. And one thing to notice here that we didn't cover in the intuition is that this while loop condition will automatically process idle time. If our max heap is empty, but our wait queue has items, even if those items are not yet available, the while loop will continue to execute, adding 1 to the interval time, representing idle time, until the next task in the queue becomes available. So that's the code. Time complexity is n log n, since we have a heap of up to n elements, representing all the tasks which we are iterating over, and for each iteration, we are performing heap pushes and pops, which are log n operations, that in the end simplify down to n log n. And spaces of n for our task count dictionary, our heap, and our wait queue. So with that, we complete this question and our heaps section. Next up, we have our graphs section. And a graph is just a collection of vertices connected by edges. A powerful tool for representing data, especially when scaled up. For example, Facebook's social graph to map your network of friends and interactions, and even neural networks used in deep learning are at their very core just graphs. As always, I'd suggest to get comfortable working with the graph data structure and all the associated operations before taking on the problems, creating the graph, inserting, deleting, printing, searching, and all the rest. I've included here a reminder on the basics, creating a graph using a dictionary or a hash map, what this looks like, and how we can iteratively search both breadth and depth first. If you used a different alternative to the data structures video, this might seem foreign to you, since of course there's many different approaches. However, hopefully this isn't too far off. From the code of these traversals, you'll immediately see that graphs are not too far off trees, and even from the diagram, they look pretty similar. So when we face these graph questions, as we've increasingly seen as we progress through this Leetcode practice, we can reuse a lot of the problem solving patterns and the code we've seen before. So I'm not going to go through this slide since the code is from our data structures video, it's just here as a convenient reminder for us. Instead, let's crack on with the first question. For this one, I've added the details in the notes. It seems that the Leetcode website is down right now, but I managed to find some screenshots on the problem. Either way, let's give it a go. In the clone graph question, we're given the node of a connected undirected graph. And let's pause there to see what this means. So we're getting into the weeds a bit here, but I've included this slide on the different types of graphs since the question mentions it. A connected graph is a type of graph where there exists a path between any pair of vertices, meaning it's possible to start at any vertex and reach any other by traversing the edges. For the most part, graphs will be connected. It's not too often you'll see a disconnected graph question. As for the directed graphs, they can be strongly or weakly connected. If they are strongly connected, then by strictly following the edge directions, we can again reach every vertex. Directed graphs will be considered weakly connected if only by ignoring the directions of the edges can we reach any vertex from any starting position. And of course, disconnected if there is no chance whatsoever to reach some vertices from certain starting points. So now that we know what a connected undirected graph is, let's go back to the question. And here we're asked to return a deep copy of the graph. We've already seen deep copies before, basically a clone who has the same properties as the original object but does not share the same references in memory. And that's summarized for us here in this diagram, where the colors are representing if the object is the same in memory. We're also shown what the node in the graph looks like. This is a Java class, so I've added the Python here above. above. So again, nothing too complicated, pretty similar to all the nodes we've seen before, where for example in a binary tree we would have a left and right child, but in this case we just have all the neighbors in a list. And below we're told we'll be given one node from the adjacency list, specifically the first node, and there's some text here to describe the input list. But if we head over to the whiteboard first, we can quickly summarize it. So this list of lists represents our input from the question, and the list at each index represents the neighbors of a node in the graph, and the value of that index is the value in the node. So in our graph, the value node 1 has neighbors of 2 and 4. The node 2 in the graph has neighbors of 1, which we've already added, and a neighbor 3. The node 3 has neighbors 2 and 4, and the node 4 has neighbors 1 and 3, which we already have. And so that's the original graph from the question represented in this adjacency list. So that's the question. Pause now and give it a go, otherwise let's see how it's done. Here's the code, and essentially we're going to be traversing the graph from the given node, breadth first, although depth would work too. We keep a dictionary called clones, mapping each original node to a deep copy. During our traversal, these clone node classes also have their neighbors updated to maintain the graph structure. And before getting into the walkthrough, I put this code side by side with our breadth first traversal framework, so we can see just how identical it is. Something we saw often in the tree sections, where we have our main traversal framework and we adjust it based on the question. So we begin with an edge case check for an empty node, followed by our queue for maintaining our nodes for the traversal. Here we have our clones dictionary, which will keep track of the nodes we create. This would be our traversal list in the main framework. Of course, for trees, this is not necessary since there is no chance of revisiting a node. We have our loop over the queue, popping the current node to be processed. After, we can carry out operations necessary for the question. Here, we add the node to our traversal list, but here we'll be creating a node clone of the neighbor in our dictionary. We're also adding the neighbor vertices or the nodes to our queue, in both these lines here and here. So the core framework is there, but we make some adjustments along the way, like looping over the neighbors in this question, and we'll explain each difference as we walk through the code. So let's begin at the start. A standard deck with the first node passed in. This queue will contain only original nodes. So I've left the original nodes in black and the copies are in purple. And we also have our clones dictionary, again initialized with the first node. This will be a hash map where the keys are the values of the original nodes and the values of the dictionary are the clone node copies. So these two initializations here set up our traversal. Then we have our while loop, which continues as long as our queue has nodes to process. Each while loop iteration is represented in black with the number by the side. We pop off the node from the queue and we assign the clone from the dictionary to this current clone variable. At this point in the code, the clone will always be available to assign, and we'll see why in a second. So then we loop over the neighbors of the original node. This for loop has two main responsibilities. If the neighbor has not yet been visited, so we do this by checking our clones dictionary, we want to ensure it's given an entry, so we can build the correct graph with the copies. We also want to queue up this node for our search, since it's not yet been processed. And although we've created the clone of the neighbor, we've not yet checked if itself has neighbors. And so this leads us into our second responsibility of the for loop. For each of the current node's neighbors we are processing, remember these are the neighbors of the original node, we want to add the same neighbors to the clone. And of course, we want those neighbors to also be clones, and we've just created the clone of the neighbor, so it will definitely exist. This happens outside the if block, since we process every node exactly once. So whether or not the neighbor is in the clones list is not a concern here. We just need to make sure that the neighbor is linked. So these lines in red here indicate every iteration of our for loop. So if we take a look at our adjacency list here, we see that 1 has the neighbors 2 and 4. So in this for loop, the first neighbor we see will be the 2. At this point 2 is not in our clones dictionary, so we create the copy node and add it. Append the node to our queue, and right at the end, make sure that the 1 copy has a neighbor of the 2 copy. And we repeat the process with the 4 node. In the next iteration of our while loop, we'll be popping off the 2 that we just added to the queue. Assign the clone to the current clone variable from the dictionary, and inside our for loop, the first neighbor we process will be 1, as we can see in our adjacency list. 1 is already in our clones, meaning it's already been added to the queue and traversed, so we don't need to traverse it again. We just jump to adding the node 1 clone as a neighbor of the node 2 clone. And in the next iteration, we process the 3 neighbor, adding it to the clones dictionary since it does not yet exist, adding it to the queue for searching, and making sure the node 2 copy has a node 3 copy as a neighbor. Then in our queue, we pop off the node 4. At this point, all the nodes have been added to the clone dictionary, so we just need to update the neighbors, and we do the same in the next while loop iteration, popping off the 3 and making sure it has the correct neighbors. And at the very end, we return the first node in our clones graph using the value from the node that was passed in to find it. And if we quickly scan our code, we can see that everything's correct. 1 has neighbors of 2 and 4. 2 has neighbors of 1 and 3. 4 also has neighbors of 1 and 3. And 3 has neighbors 2 and 4. And they are all copies. So that's our code and that's the walkthrough. Time is O of V plus E. Each node is added to the queue queue and processed exactly once. That's O of V for each vertex. And for each vertex, we are looping over its neighbors. We are checking every edge twice since we are checking every node's neighbors. But this will boil down to give us O of E, overall giving us O of V plus E. And space is O of V. Our queue has at most all the vertices in the graph, and the clone dictionary will also maintain all the vertices. So that's how we can clone a graph. A nice question to experience the traversal concepts we've seen before, but this time in the graph data structure. Here we have some core operations on graphs, something similar to easy questions. We have find the largest node, find a cycle in the graph, and count the number of edges. And we're not going to go through this line by line since they're not too difficult. For example, to find the largest node, we just rework our breadth first search ever so slightly, adding a tracking variable and comparing the value at each node. Of course, we just reverse the greater than operator to a smaller than to find the smallest node. For finding cycles, we perform a depth first search and use a set, which means no duplicates allowed. We traverse across the graph, at each point checking if we have already visited this node. Pretty similar to our framework traversals where we check if a node is in our traversed list to avoid repeating. Except this time we specifically return a boolean based on the check. And finally, this one is really neat. We want to count the number of edges. And you might think the best way to do this is another traversal of the graph, keeping count of the edges as we jump from node to node. But actually, we can just check the adjacency list, so the dictionary that represents our graph, and count the number of neighbors for each vertex. So there's some useful core operations for us to reuse, and I've linked some more here. This should remind us to always look back and see how we can reapply and rework previous patterns to face the current question. Our next graphs question is another medium, but I think this one should be a hard. It's called cheapest flights with k stops. There are n cities, each city is a node in the graph, and we are given an array of flights, which contains nested lists of 3 integers. The starting from node, the going to node, and the price of the flight. Along with that, we are given 3 integers, the source node number, the destination node, and k, which is the max number of stops or layovers we can perform on our journey. Finally, if there is no possible route between the nodes, we should return -1. And we see here from the first example that the cheapest path from 0 to 3 is 700, going over the 1 node, since we are allowed at most 1 stop. If we were allowed more stops, we could have gone from 0 to 1 to 2 to 3, which would have been cheaper. Let's now consider our solutions. The most famous shortest path style algorithm is Dijkstra's. Using it in this problem, we would have to adjust it since we have this k condition, and the solution is less clear and less efficient than this next one. We will use Bellman-Ford. The Bellman-Ford algorithm's primary principle is that it starts with a single source and calculates the distance to each node. The distance is initially unknown and assumed to be infinite, but as time goes on, the algorithm relaxes those paths by identifying a few shorter paths. Hence, it is said that Bellman-Ford is based on the principle of relaxation. And by relaxing, we simply mean updating the shortest path estimate to a vertex if a shorter path is found via that edge. So that was a lot of words, but with this example, hopefully we shall clear it up. For our solution, we're going to start at node 0, and we're going to check all the edges in the graph, on each iteration finding the minimum cost of travel to the nodes we visit. Since we are looking for the minimum price, we begin with our prices list set to infinity, so that when we check later if there's a new minimum, it will for certain update. And since we start at node 0, we initialize the price to be 0, since it costs nothing to travel from 0 to 0. And we're going to perform multiple traversals over our graph, and at the beginning of every traversal over our graph, we update our temporary prices table to match our main prices table. During our traversal, we make changes to the temporary table, and when we finish, we update the main table based off the temporary table. And we'll see why we do it this way as we work through it. In the first traversal, we see we can go from 0 to 1, and it costs 0 plus 100. So there's 2 key things here. When we get the current price to reach a node, we check the main table. And when we compare the minimum cost of travel, we do it against the temporary prices table, since this could be updated multiple times in the same traversal. So for now, this cost to travel from node 0 to node 1 is the cost to travel to node 0, which is 0, checking our main table, plus the 100, which is less than the minimum price we currently see in the temp table, which is infinity. Only when we finish one traversal, which is one loop over all the edges in the graph, then can we update the original prices table. The next edge we search will be from 0 to 2, which is 0 plus 500. Less than infinity, so we update the table. And the last edge we check will be from 1 to 2, so we're checking if we found a new minimum to reach 2. Checking the price to reach 1 from the main table, and plussing to it this 100. The price to reach 1 is infinity, so we already know the minimum price is not going going to update. Since it's infinity, we know that in one loop, when k is 0, it's impossible to reach 2 from 1. And what we can do in that case is, if the from node at any point is infinity, we can just skip the evaluation to make things more efficient, since we know for sure it won't update. So we finished our traversal and we can now update our original travel price table. Now let's take a second to consider how many traversals is necessary. We're going to do k plus 1. Why? Well, because think about the base case. If k is 0, we need at least one traversal to determine the minimum costs, if there is a path that exists. So one traversal gives us 0 stops. So extrapolating it out, k plus 1 will give us the cheapest cost to making k stops. So back to the problem, and on the next iteration, we see going from 0 to 1 will be the price of 0 plus the 100. Well, this already costs 100, so we know from this point forward, any more number of stops will not change the price. Going from 0 to 2 is also 500, and this is also what we have in our temporary prices table, so any more number of stops will not make that cheaper either. This time, however, going from 1 to 2, which we calculate as the price to reach 0, to reach node 1, and then to reach node 2, is going to be 0 plus 100 plus the new 100. Giving us 200, a new minimum for node 2. So we change our temporary prices table, the current traversal is finished, and we can update the original table, and that's 2 traversals in total. So we stop there, and these are our final prices. Hopefully you can see why we need this temporary prices table now. If k was 0, for example, no stops allowed, and we directly updated 1's price to be 100 in the main table, so we have 0 for 0 and 100 for 1 on the first traversal, then checking 1 to 2 would give us a price of 0 plus the price to reach 1 from 0, and then 1 to 2. 0 plus 100 plus 100 giving us 200, which of course when we have no stops is the wrong answer. Here's the code for this, and it's pretty much identical to our explanation, so no need to repeat a walkthrough. We have our prices table that updates at the end of every traversal, all initialized to infinity except for the source starting node. We do our k plus 1 traversals at the beginning of each, creating a new temporary prices table based off of what our original prices table is. When our traversal finishes, we update the original table to keep the temporary prices table intact on the next traversal, and we iterate across our graph checking every node, and we really only have 2 cases. First, remember, if the from node in our traversal is infinity, we can skip it, since at this point in time it will be impossible to reach. For example, when we went from 1 to 2 in the first traversal. So that's our first case. And in the second, if the new cost is less than the current cost in the temporary prices table, just like we did in the walkthrough. Again, the cost is simply calculated as the cost to reach the current node from the main table plus the current cost to reach the next node, the edge we are currently looking at. If this is true, we update the temporary prices table with this new minimum value. When we finish our traversal, all that's left to do is update the main prices table and then return the answer. We either return the minimum value to reach that destination, or if that value is infinity, then we know it's not reachable and we can return -1 like the question asks us. The time complexity for this is O of k times e. Pretty straightforward. We have k loops, we can ignore the +1, and for each loop we check every edge, and space is O of n for both price tables, which in this case we use an array to represent. So that's the cheapest flights with k stops question. Also included are 2 different approaches if you're interested. One using a rework of Dijkstra's algorithm, and another with a breadth first search approach, which we've seen more than a few times now. Our last question in the graph section is called course schedule, and I like this one because it reminds me of that Bill Gates story where in high school he was asked by the teachers to automate the school's class scheduling system, and he jokingly said he put all the girls in his class even though he didn't speak to them. So another benefit of knowing how to program. In this question, we're given an integer called num courses, which is the number of courses a student has to take, and this is 0 indexed. So a num course of 2 will be course 0 and course 1. We are also given an array called prerequisites, which tells us which course we must take first before taking the second. The order is a bit confusing. I would have preferred to have it the other way around, but the first element is the target course and the second is the prerequisite. And in the constraints, we see this is limited to 1 course prerequisite per course. So prerequisites is a list of lists where each nested list has 2 numbers, the prerequisite and the course. And we need to return true if it's possible to complete all the courses. So looking at example 2, for 2 courses total, we see there is a circular dependency. To complete course 1, we have a prerequisite of course 0, and to complete course 0, we have a prerequisite of course 1. Making this impossible. So if you want to solve it, I'll give you a hint now, or you can pause and attempt it solo. We can represent this problem with a graph of courses, where each vertex is a course and the edge indicates a prerequisite. So that's the hint, and there's still a lot more involved, so let's see how it's done. We have two ways to approach this, iterative and recursive. We'll walk through the iterative this time since I think it's easier to follow, but definitely give the recursive a go in the notes since the runtime is a bit faster. And before getting into the code, let's first consider the question. We have a num courses of 5 and this prerequisites list here. Mapping this to a graph and we get the following. To complete course 0, we need to complete 1 and 2, and to complete course 1, we need to complete 3 and 4, and to complete 3, we need to finish course 4. We can also see that 4 and 2 would be our base cases in the recursive, no prerequisites needed. Transitioning over to our code, and we see we can use a dictionary to represent this graph. In the first part of the code, we build an adjacency list, which means our graph. We've already seen this before, for example, as an input in the clone graph question. Each key in the dictionary represents a course, and the values are its prerequisites. For example, course 0 has prerequisites 1 and 2. Also, since we have experienced the usefulness of Python modules a few times now as we get more advanced, I think it's worth mentioning that we can avoid pre-filling the dictionary with empty lists by using the default dictionary from the collections module. This will prevent errors when we look up missing keys in the dictionary by returning an empty object or a base value of the type specified. So after we build our adjacency list, we begin an iterative depth-first search. We go through each course. Since it's 0 indexed, we have no problem going through a simple range, and for each course we look for cycles. A cycle or circular dependency will of course mean that the schedule is impossible, and we've already seen how to check for cycles in our core operations slide earlier. So what this code does is if we begin at course 0, we see it has a prerequisite of 1 and 2. We'll depth first search to the 1, which first has a prerequisite of 3 and then 4. Depth first search to the 3, and that leads us to the 4. Checking course 4's prerequisites, and it's an empty list, meaning we know for certain we can complete course 4. Therefore, when we go back to the 3, we know 3 is possible, and we go back to the 1, 1 is possible. We already know 4 is possible, so now we can complete 1, which takes us back to 0. At 0, we check course 2. Course 2 also has no prerequisites, it's an empty list, so we know we can do 2 for sure, and then we can also do 0. The way we do this in the code is nicely written out for us to follow. A stack as always to maintain our nodes for searching, and this time we add the graph node in a tuple with an empty set. This is in blue to make it clear. At the start of each while loop iteration, we push the current course onto the stack with a set to track which nodes we visited on our search for the current course's completion. So we have in black our large for loop here, and in red is each iteration of this while loop. Of course, the very first while loop in each larger for loop will be the course from the range that we are evaluating. So at the very beginning we add course 0 with an empty set, and then we pop it off and check if it's in our visited set. On the first while loop this will always be empty, so we add the current course to the visited set and add the current course's prerequisites with the updated set, and we continue repeating this process. Pop off the 1, check if it's been visited, and add its children after visiting the 1 and updating the set. This way we explore all the prerequisites of a course before moving on to the next course in our for loop, as well as the prerequisites of those prerequisites. If we encounter a course we've already visited on the same depth first search exploration, then the course is impossible and we return false. And bear in mind we can have different depth first search exploration paths, so we can reach the 4 by visiting 0, 1 and then jumping to the 4 directly, or by going 0 to 1, then 3 and then the 4. At the end of each loop we know for certain that the course is possible to complete without running into cycles, so we can set the adjacency list for that course to an empty list. This optimizes the time of the solution if we have to check this list again, removing redundant explorations. So at the end of this for loop here, no more nodes to search in our stack. In the adjacency list, we give the 0 course no more prerequisites. Time complexity for this solution is O of v plus e, where v is the number of courses, our vertices, and e is the number of prerequisites, our edges. Building the adjacency list takes O of e time since we iterate through all the prerequisites. The iterative depth first search takes O of v plus e time in the worst case, because each vertex, or course, is visited at most once in the outer for loop, which accounts for O of v time. And for each visited vertex, we explore all its neighbors, the prerequisites, in the inner loop, which is proportional to the number of edges, e, giving us overall v plus e, and the space complexity is also v plus e. The adjacency list requires v plus e space in the worst case, where every course has prerequisites. Additionally, the stack in the depth first search has a maximum depth of all the vertices, as well as the visited set, so they will each have v space, but overall we are dominated by the adjacency list, giving us v plus e. And so with that, we complete this course schedule question and our graphs section. So that was the final section of this Leetcode practice, and we are now finished. We've gone over everything in the introduction, so I'll keep this short. By law of nature, if you've made it this far, you're ahead of 99% of people, and you're over the hump of the hard technical coding skills. But definitely continue working on these problems till they become second nature. And don't forget to continue the rest of the work in this journey, learning the ins and outs of software engineering as a field, applying for jobs, behavioral skills, and all the rest. And I would wish you good luck, but if you've made it this far and completed all these questions and put in this much work and effort, I have no doubt in my mind that you don't need the luck.